It is recording now, right? I think so. Shall I continue then? Okay. Dr. Rath, am I still audible?
Yes. You can continue.
Okay.
Now recording started. Yeah.
Okay.
Thank you very much.
Yes. So again, many of you will know the basics of phase change materials, but for the benefit of those who are working in different other areas, let me just give a quick introduction to the basics of phase change material based energy storage systems. So phase change materials are any sort of materials, like it can be an organic material, it can be an inorganic material, it can be a metal. So it can be any material which undergoes a phase change process, typically melting process, but it can be also solid-solid phase transformation, but typically it's a melting or solidification process. And while it undergoes this phase change process, it stores energy as latent energy. So latent energy of fusion during melting. And when it solidifies, it releases the energy as energy of as we need to remove energy for solidification to occur. Okay. So these have been widely used or have been widely researched in last couple of decades for various applications like solar power plants, solar thermal power plants, and cooling applications, different cooling applications, and other energy storage areas, and has a lot of potential because of some good advantages, which are high storage density. High energy storage density means that for a smaller mass, it can store large amount of energy because the mode of energy storage is latent heat storage instead of sensible heat storage. There are other types of energy storage which have even higher energy storage densities, such as thermochemical energy storage systems, but those have other engineering problems, difficulties in storing and removing the energy because they need to undergo reversible chemical reaction. But for this type of latent energy based storage systems, the process is much more simpler. Okay. So one of the major drawback in this area, as many of you will know who have worked in this area, is that most of the phase change materials, or PCMs as we call them, have very low thermal conductivity, except for metallic PCMs. All the other types of PCMs like organic PCMs have low thermal conductivity. And for most general applications, the temperature range is such that we use organic PCMs such as paraffin wax, which is shown here. So generally the temperature is low to moderate temperature, and for these cases we use organic phase change materials, and they suffer from low thermal conductivity. And as a result, a lot of research has been done in this area to improve the effective heat transfer rate for a system which is based on phase change material. So again, many of you will know and must have worked also in some of these areas, such as use of different types of fin configurations. Recently, people have also used nanoparticles to improve the effective thermal conductivity, and other types of say metallic structures or even graphite structures to improve the effective thermal conductivity, or even used encapsulation of PCM to use to increase the effective heat transfer rate. So one of the areas or one of the ideas which has gained lot of traction in recent years is the use of metal foams instead of metallic fins. Okay. So what is a metal foam? As you can see from the picture on the right hand side, where I am showing a picture of aluminium foam. So metallic foam is nothing but a mesh-like structure, which has a very intricate say network of interconnected pores. Okay, so the main advantage is that the average density of this material is very less. So for a large volume, you need a very small amount of metal to encompass the entire area, but still it has metallic presence in all the regions of the domain. So heat can be transferred to any area of the domain quite efficiently using a metallic foam structure, as compared to say a fin structure, where if you use a fin, you will have certain regions where which is far away from the fin, and where the heat transfer will be quite slow. Okay, and this is particularly useful because it has very high surface area to volume ratio because of its very large network-like structure. Okay, and as I have already mentioned, metal foams have low average densities. I mean that I don't mean that the density of the metal is low, because we can also use copper foams, which has very high density, but the density, average density of the entire metallic structure is low because of the large porosity. Okay. And typically for applications in energy storage, high porosity materials are used, which have porosity of the order of 90%. Okay. So what is the, or how can we use this metal foam for improving the effective heat transfer rate of phase change material based systems? Okay. So if we embed, say if you consider a metal foam like this, and if we embed these porous regions with organic phase change material, we will have a composite structure which will consist of a combination of PCM and metal foam. And if you consider any location within this structure, you will have a metallic structure nearby to that region because of this large intricate mesh-like structure that is present. Okay. So as a result, if you have heat transfer in this composite material, the heat transfer will be very effective because no region in PCM is far away from a metallic structure. Okay. So each point in PCM is always going to be near some metallic structure. So as a result, it is going to be, the heat transfer is going to be very effective. Also, because of the large surface area of this metallic foam structure, the effective heat transfer rate is going to be very high. And now this, we want to know, if we want to design such a system with a metal foam structure, what sort of metal foams should be used? Okay, or what should be the design so that we can increase the effective heat transfer rate or energy storage, like the effective energy storage capacity. So this will depend on the metal foam porosity, what is the porosity of the metal foam, as well as the structure of metal foam. And by structure, I mean that what is the average pore size or pore density. So structure is like the pore size or pore density defines, say in a particular area, how many pores are present, or in a particular volume, how many pores are present. And even if the pore density is same, the pore arrangement can be different. So for example, we can have unstructured metal foam as shown here, where there is no particular arrangement, or we can have a very structured arrangement like shown here, where you have the metal foam is arranged in a nice lattice system or a array system. Okay, then it can be hexagonal array or cubic array, depending on again different types of structured metal foams. So in general, depending on the manufacturing process, the metal foam structures can vary, and we will discuss about this a little bit later. Okay. So our focus will be on pore scale models in this discussion, and we will see that pore scale models are very effective in capturing the geometry accurately, which is one of the drawbacks of volume average models. Although volume average models have other advantages. So we have still not defined what are volume average models and pore scale models. I will come to that subsequently. Okay. Before going to that, let us try to understand. So if we are trying to develop a CFD model for this type of system, phase change material system, or in particular phase change material, metal fin or metal foam system, what are our objectives for developing those CFD models? What are we trying to achieve? Okay. So one of the thing, first what we are trying to do is we want to simulate the phase change, how the phase change is occurring, what is the melting pattern in the domain. So if we change the design, how the melting pattern is going to change. Similarly, how the solidification pattern is occurring. If we change the design, how the solidification pattern changes. If we change the boundary condition, how the solidification or melting pattern changes. So the basic phase change process we want to capture by developing CFD models. And what is the purpose of that? We want to basically predict the melting and energy, charging and discharging characteristics. So what I mean is that we want to predict what is the rate of melting or solidification and what is the rate of storage of latent energy and sensible energy. Here we need to also consider the sensible energy because metallic part is present and it will store some energy as sensible energy. Similarly, what is the rate of discharge of this latent energy or sensible energy with time, because these are some time period, maybe 6 hours or 8 hours. Then based on those requirements, we have to predict what is going to be the charging and discharging rates. And accordingly, we have to design the system. What will be the volume of the system? What will be the, say, whether we are going to use metallic foams and what type of structure we are going to use. This type of predictions we need to make. And CFD models are useful tools in regards to this, because if you go for experimental studies, it will be much more costlier because you have to develop prototype for all the cases. But experimental studies are also needed because you need to validate your CFD models using experimental studies. Anyway, coming back to this. So particularly for PCM metal foam systems, we also want to analyze the effect of design parameters such as the porosity of the foam. So what is the effect if we increase the porosity, how it is going to affect the melting and energy storage rates. If we decrease the porosity, what is going to happen? And apart from porosity, we also want to see the effect of other geometrical parameters such as the pore size or pore density and the pore arrangement. If it is a structured arrangement, if it is an unstructured arrangement, then even in unstructured arrangement, there can be different types of unstructured arrangement. Even in structured arrangement, there can be different types of structured arrangements. So what is their effect? Because for each type of arrangement, even for the same pore size or porosity, the heat transfer path is going to vary, and that is going to change the effective heat transfer rate and melting rate. Okay. Some of the other things that need to be analyzed, which we will not focus in this talk, but are important in many applications, is to compare the effect of different types of PCM. Okay, so we want to develop CFD models and we want to see the effect of different PCM, which PCM to select for a particular application, and which metal foam to select, whether we are going to use aluminum foam or copper foam, or we can use even non-metallic foam structures like graphite foams. So which particular combinations are suitable for our applications. So these also are some of the targets of the CFD models that are developed. So I will quickly describe the two main approaches for modeling this type of systems. Okay. So I hope at this point you have an understanding, basic understanding, those of you who have not worked in this area, about what is the system going to consist of. So we will have a metallic foam structure like this, and all the pores will be filled up with this type of phase change material, and this will be enclosed in a metallic box or a container, and it can be heated from one side to melt the phase change material which is present inside, and the metal foam is going to increase the heat transfer rate, leading to faster melting of the phase change material. Okay. So basically we are going to consider a composite of this metal foam and PCMs. Okay. So a composite structure. So the more popular method, which it has been developed and improved over the past few years and is very widely used, is known as volume average model or volume average method. Okay. So what are the main features of this volume average model? So the main features are that we consider in volume average model, we consider that this composite structure of metal foam and PCM is a single unified structure. We do not resolve the geometrical parameters, or we do not resolve the foam structure separately. Okay, we assume that it's a single entity, but with the average property based on the metal and PCM property. Okay. So I will come to how the results look like, but the main idea is that you have a single, we are assuming that it's a single average material, and the properties are averaged based on the metal and PCM properties, and obviously based on how much metal and how much PCM is present, which will be given to us based on the porosity. Okay. Now it can capture a lot of things. It's not that because it's the average model, it's not that it has significant limitations. There are a lot of advantages of this model. So for example, it can capture quite accurately what is the flow that is happening through this porous metallic structure. So one question can be why there is flow in this structure. Okay. So what happens is that, say you are heating it. For example, for this particular case, I have taken it from a reference by Zhang et al. In this case, we have a PCM metal foam composite structure, and for this particular case, they had done an experimental study where they had put a heat source on the left hand side, and as a result, there was melting of PCM from the left hand side, and you can see that the molten region is more clear, and the solidified region is this hazy region, which shows white PCM color here. Okay, it's I hope it is clear, it is visible to you. So for this type of situation, what happens is that because of natural convection in the liquid PCM, wherever the temperature is higher, the liquid PCM rises upward, and as a result, more melting occurs towards the top region. Okay, so this convection pattern can be captured even using volume average models by suitable porous medium approaches like using Darcy's law or Karman-Kozeny law. I will not go into the details. You can go to appropriate references. I think these slides will be shared, or this recording is going to be shared with you, and you can go through the references to see about volume average models. Because our focus is not on volume average models, I will just point it out here that we can use different porous medium approximations such as Darcy law or Karman-Kozeny law, which gives the resistance to the flow in a porous structure. So basically, you can model the flow as if it is occurring through a like there is a resistance to this flow because it is going on through a porous structure, and this resistance will obviously depends on the porosity of the material. Okay. Then the second important aspect which needs to be captured is the heat transfer between the metal and phase change material. Okay. So this is also can be done effectively nowadays using volume average models by assuming that the metal and the phase change material are at different temperatures. Okay. So if you consider a CFD problem for this, or a CFD system for this, as Dr. Rath was explaining in his talk. So if we use volume of fluid metal, like VFM model or FVM model, sorry, finite volume method, we discretize this domain into a certain number of control volumes. Okay. And each of the control volume is represented by a grid point at its center. So for each grid point, we can define two temperature values, one for the phase change material and one for the metal. And we can assume that these two are different. Okay, the metal will, the temperature in the metal will rise faster because of faster heat transfer through the metal, and then the temperature will, as a result of heat transfer from the metal to the PCM, the temperature in the PCM will rise subsequently. So there will be a lag in temperature in the PCM as compared to the metal. So if we define two temperature for each control volume, we can capture the heat transfer between the metal and the PCM. But we need to define appropriate source term again to capture this heat transfer between the metal and the PCM, and this source terms needs to be defined based on heat transfer coefficients, and it is not easy to define these heat transfer coefficients. These are generally defined based on correlations, and if you want to accurately capture the effect of porosity or pore size, you need to develop suitable heat transfer coefficients, and there are various relations for this. Researchers have improved over the past few years so that we can approximate in a better way the experimental results. Okay, but still it is a sort of approximation because you are assuming the heat transfer coefficient for the heat transfer between the metal and the phase change material. There are certain advantages of this volume average models. Main advantage is that you don't need to create a complicated metal foam geometry, because we are assuming that it's an average model. We can just take a square or a cubic domain as per the system requirement, and we can just solve for that domain. Okay. There are certain drawbacks here. The drawback is that because of this approximate nature of this heat transfer between the metal and the PCM, which is captured using a correlation, we cannot exactly capture the effect of pore size. The effect of porosity is captured through the volume averaging part, but the effect of pore size or the pores distribution or the structures for given porosity and pore size cannot be captured accurately. This can be captured somewhat through the correlations, with better and better correlations, but you need to tune your correlations to experimental results to capture them in a better way. Okay. I am going very slowly, so I think I will speed up. Okay. And again, we cannot capture the local heat transfer at the metal foam PCM interface accurately, because we are not capturing the metal foam structure. Okay. So these are captured using heat transfer coefficients. Certain advantages are there, like major advantages. One is that it is numerically less expensive, so you can run an algorithm much faster as compared to pore scale models. And second advantage is that you can simulate large systems. So if you have a large energy storage system, you can develop the model for the entire system and solve for it, and you can find out system level, the effect of system level parameters, like if the system design change or the boundary condition change at the system level, what is the effect of that. So this type of advantages are there for volume average model. As a result, these are very popular. Here I am showing one example from literature. This is from a very good paper by Joshi and Rathod, which has been published in Applied Energy, where you can see how the results from a volume average model looks like. So you can see that the red region here is the liquid PCM and the blue region is the solid PCM, and you can see that the model does not resolve the metal foam structure, and it captures a smooth interface. Okay, it captures a smooth interface between the solid and the liquid PCM. So solid is the blue region, liquid is red is the liquid part, and with time the melting occurs and the volume of liquid increases, but it cannot capture the or it does not capture the local variations of the interface structure or the heat transfer, because it does not capture the metal foam geometry. So in this type of volume average model, the temperature or the melting profile will be a smooth structure like this. But again, I have already stated what are the advantages of this model, and you can see here also that it quite effectively captures the experimental results. So it is similar to the experimental results from literature. Okay. Now we will go to the other type of modeling approach, which is known as pore scale model. Okay. And our main focus in this lecture is to focus or to discuss about pore scale models. Okay. So in contrast to volume average models, the main difference in pore scale model is that the geometry of the metal foam is resolved. Okay. So you have a separate metallic structure and the separate phase change material within the metallic structure. Okay. So these two parts are separately resolved in the CFD model. We will see how it is done for a particular case for our model later on. But this is the main difference. Okay. So as a result of this, we can actually capture the flow pattern through the metal foam gaps instead of using porous medium approximations. Okay. We can also accurately capture the heat transfer between the metal and PCM interface, again because the metal foam geometry is captured. Okay. And as a result of this, the geometrical parameters such as pore density, size distribution, pore structure can also be captured. However, there are certain difficulties in developing this model. One is that it is computationally more expensive, because you need to resolve the geometry of the metal foam structure. You need a very fine grid structure or mesh structure. So you need large number of control volumes or grid points. As a result, it will take much longer time to solve or simulate this type of processes based on these models. And second major point is that creating a realistic form geometry is very difficult. Okay, so realistic form geometry looks like this. Okay, this has been created, like structured form geometries has been created using additive manufacturing. But the main type of manufacturing method which is used for creating metal form geometry is by nucleating or nucleating agents, which creates gas bubbles in a liquid melt pool, which results in unstructured arrangement like this. Okay, not a very nicely arranged structure like this, and this is difficult to model, this type of random arrangement. Okay, so as an approximation, in recent literature, you will find different types of structured arrangement. Researchers have come up with certain types of arrangement, and they have studied effects such as single-centered or face-centered or body-centered cubic or rectangular arrangement, both with fully enclosed type of structures or a very open type of structure. Then some other researchers have used mesh-like structure, regular rectangular mesh-like structure. Similarly, some other innovative structures like fractal designs have been used, but at a very preliminary level. As you can see here, it's a very preliminary metallic structure with disconnected joints, which is not very realistic. Okay, so this type of models have been previously developed. In recent years, some other models have been developed, but all capture mostly structured type of arrangement. Okay, because realistic form geometry creation is quite difficult. And another drawback I have not mentioned here is that because you are capturing this, resolving this geometry, you cannot solve this model for very large scale systems. So you will be only focusing on, or we will be only focusing on a smaller area or a smaller size domain, because capturing a large scale geometry with finely resolved structure is not possible with the computational resources that we have at present. Okay, it may be possible in future, but current computational resources prohibit this type of modeling approach. Okay. So subsequently, so I hope that this gives you a basic idea between the difference basic idea about the difference between pore scale and volume average models. So subsequent talk will just focus on a particular case study or for a particular pore scale model that we have developed here in collaboration with Dr. Rath. And my main idea is that although we will be focusing on this model, it may give you certain ideas of using similar models for other applications related to energy storage, or it can be related to other applications like cooling applications or different aspects of energy storage such as encapsulated PCM systems, other systems like thermocline based systems. Okay. Even I have seen I have some ideas about how this can be used. This type of approaches can be used for biological systems also. So different CFD applications can be related to this approach. Okay. So any question or? I will just continue then. So what we are considering is a cubic domain in 2D or 3D, which contains both the metal form and PCM as a composite material. And as I was saying, we will resolve this metal form, and how we will develop the geometry, that is one important part of the model. Okay, and it can be heated, so you can assume that the domain is heated from any one side, maybe bottom or side, like one of the sides, and it has adiabatic boundary conditions on all the other sides. Okay, and it's a fully enclosed area, so there cannot be any leakage out of this domain. Okay. So now coming to the geometry creation part, so we can divide this CFD model into two parts. One is the geometry creation part, and the second part is on the solution of the phase change process and fluid flow process. Okay, phase change and fluid flow algorithm. So I will focus more here on the I will focus somewhat on the geometry creation part, because there is a lot of novelty in this area. And I will also quickly go through the phase change part, and I will cite some references there so that you can read further in those areas, because those are much more common with volume average models also, or other types of models, CFD models. So the idea here is that we want to develop a geometry, okay, which is unstructured in nature, mimicking real life geometry. So in real life, what happens is that this metal foam is generated by passing some nucleating agents in a liquid melt pool, and this creates gas bubbles, and these gas bubbles can come in contact with each other to create overlapping or non-overlapping porous structure. And when the metal solidifies, it traps the gas bubbles and it creates the metallic structure, metal foam structure. Okay. So to mimic this, we developed an algorithm where we assume that the geometry is generated by inserting spheres of random sizes at random locations in a domain within certain constraints. Okay. So I think again I will just look at the time. I don't have much time left, so I will slightly hurry up. Okay. Still 25 minutes is there, so but we'll try to hurry up. So what we do is, say there's an empty domain. Okay. We first insert a sphere. So what I mean by inserting a sphere in a numerical sense, I mean that we generate the random coordinates for its center. So say random coordinates for its center is x, y, and z0. Okay. So these are generated using some random number generator. You can generate it using any tool like say MATLAB or Fortran, or in whatever language you are coding. We use Fortran for our calculations. Now we also specify a random radius, and this random radius is specified within a given radius range. So the radius is bounded by a minimum and maximum radius. So it cannot go beyond those radius ranges. If it goes beyond that radius range, we discard that value. Okay. So our random number for the radius is between this minimum and maximum radius. So once these four values are determined, the x0, y0, z0, and r0, we can say that one sphere has been generated mathematically. Okay. So we store the value of x0, y0, and z0 and r0 in a matrix. Now we insert a second sphere. So how do we insert a second sphere? We again randomly generate the coordinates of its center and generate the radius of this sphere. Now this sphere can be very far away from the first sphere, or it can be somewhat overlapping the first sphere, or it can be totally within the first sphere. Now we want to avoid a situation where this second sphere is totally within a first sphere, or majorly within the first sphere, because then that does not serve our purpose. Okay, if it is totally within the first sphere, it is not. The second pore is going to be fully engulfed in the first pore, so we will not be able to create a proper geometry. So to check for this, we create we define a parameter which is known as pore overlap. Okay, so I will not go into too much details here, but just briefly define what is this pore overlap. So this pore overlap specifies up to how much extent two spheres can intersect each other. So depending on this pore overlap parameter, which is given by omega here, which is a fraction of the radius of the smaller sphere, we can say that okay, 20% overlap can occur, or 30% overlap can occur, or it can be 0% overlap if we do not want any overlap. So this is the maximum extent of overlap that is allowed in the model. Okay, and this can be an user input. So by changing this pore overlap and this radius ranges, we can create any combination of geometries, random geometries. And one example has been shown here. You can see that there are small pores, large pores, there are intersecting pores also. Okay. So we continue inserting these spheres one after another, and for each case we have to check for the pore overlap with all the existing spheres. And we have to see that whether it satisfies the pore overlap condition or not. Okay. If it satisfies the pore overlap condition, we store the coordinate values of this sphere in the matrix. Otherwise, we discard the sphere. And we keep on doing until we reach a particular porosity. Okay. So how do we do that? We calculate what is the porosity after inserting each sphere, how much volume has been occupied by the pores, and once say our aim is to achieve 80% porosity. Once we see that 80% of the volume of the total domain has been reached by the pores, we stop the pore generation process. Now we store all the coordinates of the center of each of the spheres and their radius and transfer it to the CFD model. Okay, so this is how this generated spheres look like. Now we have to convert these spheres, which are still in mathematical form. Now we have to use this in our CFD algorithm, right? So we have to use it in such a way so that we can solve our CFD problem. So what do I mean by that? I mean that when you are solving your CFD problem, you divide the domain into certain number of control volumes. So we may have say 100 grid points along the X direction, 100 grid points along the Y direction, similarly 100 grid points along the Z direction. So we want to see, based on these grid points, whether there exists a pore or a metallic part there. Okay, so we will assume that wherever there is pore, inside the pore phase change material is present, and any part which is outside all of these pores is metallic part. Okay, so if you subtract these pores from the the spheres from the entire domain, you get a structure like this, and we will call it the metal foam structure. So we can generate both like a regular metallic structure like this, and it will result in a composite material like this, where the blue region shows you the porous region or the PCM region, and the red region shows you the metal region. Or we can generate an unstructured metal foam structure here. So in the unstructured form, you can see that there is no regular arrangement of pores, and there are multiple pore sizes, and there are some pores which are overlapping, some which are not overlapping. And we are assuming that these pores are filled with PCM, and the red regions are the metallic foam structure. Okay. So we need to map this to our CFD grid because otherwise we cannot solve our CFD problem, because our properties for metal and PCM needs to be defined based on the CFD grid. So to map this, what we do is we do a two-step mapping process. Okay. So first we generate a very fine grid structure. For example, we divide this domain into 1000 grid points in each direction. Okay, so 1000 by 1000 by 1000, so 1 billion grid points in total. Okay, and we check for each grid point whether it falls within a sphere or outside a sphere. If it is within a sphere, we assume we provide it a value of 1. If it is outside a sphere, we provide it a value of 0. So basically, we just define a binary number 1010. So if it is in the PCM region, the value of this number is 1. If it is outside in the metal region, the value of this number is 0. But using this type of very fine mesh structure, you cannot solve the CFD problem, because if you want to solve using 1 billion grid points, it will take years for your problem to run. Okay, it is not feasible given the computational resources that are at present possible. Okay. So what we need to do is we need to go for a coarse mesh structure, but keeping the fidelity or the accuracy of the metal foam geometry intact. So what we do is we create a coarse mesh structure, like for example 100 by 100 by 100 control volumes or grid points along each direction. Now each of these coarse grid point or control volume, so if I have 100 control volumes for the coarse mesh in each direction, for each of the coarse grid control volume, I will have 10 fine control volumes. Okay, because I had 1000 control volumes for the fine mesh. So in each direction, I will have 10 control volumes. So for the total control volume, I will have 10 by 10 by 10, 1000 control fine control volume.
I think there is some network issue maybe. Dr. Anirban, can you hear us? Just wait for a while, huh? Wait for a while. He will be joining soon.
Possibly there is a disruption in the
yes,
network.
because
Yeah.
in the office net is very much disturbing. That I know. Sometimes it is going out of order like that.
He'll be shortly. Yeah.
Uh-huh.
I hope he will be shortly connecting.
Yeah.
Connecting.
Give a call. Yes, Dr. Anirban. Yes. Hello.
Can you hear me, Dr. Ram?
Yes. Now we can
Okay.
hear you. Okay.
Can you see the screen also?
Screen is coming. Yes, we can able to see the screen.
Okay, I'm sorry for the interruption.
No problem.
Okay. So what I was explaining is that we basically map the fine mesh to a coarse mesh structure, retaining the fidelity of the geometry, basically, so that instead of the binary numbers, we have a value between 0 and 1 for a parameter. So say if I define a metal volume fraction, this metal volume fraction will be 0 if it is fully within a PCM region, it will be 1 if it is fully in the metal region, and it will be between 0 and 1 if a control volume contains both PCM and metal. Okay. So I cannot go into further details, but if you are interested, you can read our paper on this where we have a detailed algorithm for this. Okay. So these are some examples of the geometries that can be created. These are from 2D model, but similar geometries can also be created in 3D as you have seen here. And as you can see, for the same porosity but for different pore size, we can create geometry. So it is for 50% porosity for each case, but the pore size is varying from very small pore size to a larger pore size. On the other hand, if we have the same pore size but different porosity, that type of geometry also can be captured. For example, here the pore size is kept same from 0.5 to 3 mm, but the porosity is increasing from 50% to 70% to 90%. And you can see that PCM volume is increasing and metallic volume is decreasing significantly. Again, more details are present in the papers. You can go through them later on. So this is one part of the model, the geometry creation part. Once you have the geometry creation totally done, the main output from the geometry creation part is the metal fraction for each control volume. Okay. So depending on the geometry, you will have metal fraction in a control volume either having a value of 0 if it is fully in the PCM, 1 if it is fully in the metal, or between 0 and 1 if it is in the interface region, means both PCM and metal foam are present. Okay. And if you plot this metal fraction, you will get plots like this or plots like this in 3D. Okay. This is from the actual geometry that are created. So the second part of the model is how to solve for the phase change. Okay. So there are again two parts in the phase change. One is without natural convection. If we want to develop a simple model without considering natural convection, we have first developed that part because that also gives quite a bit of insight, and then we have proceeded towards incorporating the effect of natural convection. So the phase change is developed using famous model or method which is known as enthalpy method. So in this method, what we do is we track the interface based on the average enthalpy of each control volume. Okay. So for our particular method, what we are doing is we are defining the energy equation. We need to solve for the energy equation because ultimately by tracking the energy at each control volume, we will be able to find out what is the variation of melting that is occurring. So we define energy equation in terms of the enthalpy at each grid point and the conductive terms. Okay. So let me elaborate a little bit on the what is the enthalpy. Okay. So the enthalpy is the average enthalpy of each grid point. It consists of two parts. First part is the sensible energy for this control volume. Again, the sensible energy consists of two parts. One is the sensible energy of the PCM. So it can be written in terms of the specific heat of the PCM multiplied by the volume fraction of PCM. which is 1 minus phi, where phi is the volume fraction of metal. So if we consider phi to be volume fraction of metal, 1 minus phi is the volume fraction of PCM. And the sensible energy of the metal then is volume fraction of metal into specific heat of metal. So this is the total sensible energy. For the latent energy is only present for the PCM part. So volume fraction of PCM, which is 1 minus phi, into we define another parameter which is known as liquid fraction, FL. Okay, this liquid fraction is the amount of liquid. So out of the amount of PCM, how much is liquid? What is the volume fraction of liquid? Okay, if it is fully solid, FL is 0. If it is fully liquid, FL is 1. So for solid, we assume that the latent energy is 0 because we assume that that is the reference state. And for fully liquid, we assume that the latent energy is the latent energy of melting L. And if it is partially liquid, so based on the amount of liquid that is present, the latent energy will be accordingly modified. So this is the total enthalpy of each control volume H, and the total enthalpy changes because of heat transfer through the different directions of the control volumes, the X, Y, and Z direction because of conductive heat transfer. For this case, we are ignoring the convection, right? And we solve this equation using explicit scheme. Of course, it can be solved also using implicit method. For our case, we solve it using explicit scheme because it is easier to implement. And but we have to take into account that the time step needs to be smaller than time step needs to be such that it satisfies the stability criteria. Okay. So further details about stability criteria or explicit and implicit schemes you can read from the very famous book by Suhas Patankar, which is one of the fundamental books of CFD. Many of you must have already read it. It's a very small book, but it gives us a lot of insight in a very concise manner. Patankar was one of the pioneers in the area of CFD. He actually developed the famous algorithms of simple and simpler for solving the fluid flow equations. So anyway, for our case, we discretize it using finite volume method. I have given a description here due to lack of time. I think I will not go into too much details here, but we use the method finite volume method, which is given by Patankar or Patankar's approach, where basically for each control volume, it is represented by a grid point at its center, and the equations are discretized based on the values of at the grid points and the neighboring grid points. For example, if I consider this first term k, the del x of k dt dx, okay, for this can be represented if we integrate over the entire control volume, okay, this time over the entire control volume, and over the time we can write it in terms of the temperature differences between this grid point temperature Tp and the neighboring temperature Tb. Similarly, on the other hand side, Tp minus neighboring temperature Ta, and other geometrical parameters such as the distance between the grid points and the control volume lengths delta y and delta z. So physically what it means is that what is the heat transfer in the x direction. Similarly, this discretization of this second term will give you the heat transfer along the y direction in the control volume, and the third term discretization will give you the heat transfer along the z direction, and in total you get the total heat transfer, and because of this heat transfer you get the change in enthalpy in the time step del dt. Okay, so in a particular time step dt you get the, or delta t should have been more suitable here. So in a particular time step delta t, how much is the heat transfer that is occurring here. So for explicit scheme, many of you again will know if you have read about CFD, we use previous time step values which are already known to us. So all the temperature values are already known to us from the previous calculation, and only the new enthalpy needs to be calculated, and it can be directly solved instead of needing an iterative process. In one go we can solve this. Okay, so it runs faster, but remember that time step has to be smaller in this case to satisfy the stability criteria. Once we get the enthalpy value from this equation of enthalpy, we can find out the liquid fraction. So if the liquid fraction is between 0 and 1, it means that the cell is at the interface of solid and liquid. So If it is at the interface of solid and liquid, it means that melting is occurring there. So the temperature must be equal to the melting temperature. So if you specify the temperature there equal to melting temperature, from this equation, all the values will be known. H will be known after this calculation, and other values will be known. And the only unknown value will be FL, and FL nu can be calculated based on this. If FL comes out to be greater than 1 or less than 0, it means that melting has either fully completed there or not yet started there. In this case, we just fix the value of FL to be 1 or 0 according to what is the value we are getting. And the only unknown will be the temperature, and the temperature can be calculated from the value of H in those cases. So only one unknown will be there, and it can be calculated from the H value. Okay. So like this, we can get the value of new liquid fraction and temperature. So once you get the new liquid fraction and temperature, you can store them and advance along to the next time step to solve for the next time step and march along the time for the entire simulation duration. And ultimately, we will be able to see how the liquid fraction evolves with time, which will give us the liquid fraction front, and how the temperature evolves with time. Let us see how much time. 5 minutes is left. So actually, I just wanted to focus more on the modeling side. So results are there just for showcasing some of the aspects. So I think it's fine.
Yes. No problem.
Yeah. Okay. I think I can go till 11:55 will be fine.
Yes. No problem.
Okay.
No problem.
Okay.
Yeah.
So now if we want to add the effect of natural convection, which is very important, okay, because in phase change material, the temperature affects the density of the phase change material in liquid state, and this results in a convection pattern which changes the entire melting pattern. You can see here from this example that the melting is not uniform. Although the heating is from this side, the phase front is not perpendicular to this, parallel to this side. More melting is occurring at the top, and this is because of natural convection. So natural convection needs to be accounted for, particularly for high porosity, where there is more chance of flow. For low porosity, we have seen that the area is very restricted and natural convection is not so important. Okay, so then conduction based models are sufficient. So if you want to include natural convection, we need to solve the continuity equation and momentum equation. Again, these equations will be very familiar to you, but I want to highlight just two particular terms in the momentum equation. One is this term 1 minus phi rho PCM G beta T minus Tm. So this is the term to account for the Boussinesq approximation, which accounts for the variation of density due to temperature change. Okay, so we assume that the density is constant while solving the equation, but the effect of temperature is taken into account just by a source term using Boussinesq approximation. Okay, and the second term here, or the last term here, A into U, again is the source term which is needed to suppress the velocity to 0 in the solid region. So for our case, we have two solid regions. One is the solid phase change material, second is the solid metallic region. So we can define a term like this such that if phi is equal to 1, so in this term C has a very large value and S is a very small value just to avoid division by 0. And if you define this term like this, if the metal fraction is 1, phi is 1, in the metal this term should have a very large value. Okay, so if phi is 1, 1 minus 1 is 0, so ultimately you are left with a very large value, C into 1 by some very small value. So the value of A becomes very large, and this dominates over all the other terms that are present in the equation, and as a result suppresses the velocity to 0. Basically AU is equal to, the equation becomes AU is equal to 0. Okay, and in the fully liquid region, this term assumes a value of 0 because FL is equal to 1 and metal is 0, so it is 1 into 1. So 1 minus 1 is 0, so this value of A becomes 0. So we go to the normal Navier-Stokes equation without any resistance due to solid present here. Okay, so one important thing which many students particularly mistake here is that they think that this is the only formulation that is possible for this. Okay, so this we need to know that this is just a particular formulation that we are using here. We can have any formulation of A, which suppresses the velocity to 0, basically which increases the value of A to very large value in the metallic or solid PCM region and makes the value of A to 0 in the liquid PCM region. Okay, it need not be of this form. This is just a derivative of the Karman-Kozeny porous median approach, which is used for regions where both metal and PCM are present, like a mushy type of region is present, or where the PCM solidifies over an extended region, but we generally do not consider that case here. Okay, so this is just a derivative of the Karman-Kozeny model, but we can use any other approximations also here. Okay, apart from this, all the other parts are similar to the conduction based model, and the energy equation has an extra term, which is del dot rho u h, which comes from again from the because of the convective effect. So again, the solution process is exactly similar. We follow the finite volume approach given by Patankar, and the energy equation is solved explicitly, like I have just described, and the momentum and continuity equation is solved. For our particular case, we are using simpler algorithm, which was developed by Patankar. Any other methods can also be used, but simpler algorithm is very popular for this type of problems, and gives a very good convergence rate. Like it is quite robust also. So let me see how much time is there. 4 minutes. Okay, so I will just show you some of the results to give you
3 more minutes are there. Yeah.
Yes, just some of the glimpses of the results instead of going into details. Okay, so I think I have achieved my main part, which was to focus on the modeling part. So this is a result from the present model, and this is a result from experimental work from Chen et al. And you can see that the model captures the asymmetric nature or a non-regular nature, non-uniform nature of the temperature profile because of the geometry that is captured in this model. Okay, and the temperature pattern is also similar to the experimental temperature. And if you plot the central line temperature, we will see that there are fluctuations, and these fluctuations are present because there may be regions where metal is present and there may be regions where PCM is present. So based on this, these fluctuations come, and this is one characteristic of the pore scale models. And you can see here that the pore scale model captures localized regions of low temperature and high temperature based on whether PCM or metal is present. Okay. So I will show you some results just to give you a glimpse in 2-3 minutes. Okay. So these are results without convection. For more details, you can revisit the papers that I have outlined at the end. So this is for structured metal form. This is for unstructured metal form, and you can see how with time the melting continues and how the temperature evolves. And this was for 60% porosity. This is for 80% porosity, and obviously the melting rate is lower because you have more PCM in this case. Okay, although the energy storage will be more. And we have quantified this. Due to lack of time, I cannot go into the details, but the crux of this quantification is that for higher porosity, the rate of energy storage and rate of melting is lower. For lower porosity, the rate of melting is higher because more metal is present in the domain. Okay, this type of results can also be captured using volume average models. I will come into some results which we cannot capture using volume average models. Okay. Again, effect of porosity we have studied with convection, and you can see the convection pattern which is generated. Similar types of results we have observed that for higher porosity, melting is slower, and for lower porosity, melting is faster. Another interesting result that is obtained here is that for higher porosity, the effect of convection is large because of large amount of area which is available for the flow to pass. Okay, for lower porosity, the convection is very much restricted, and this again has been seen through quantified result. Again, I will not go into the details. So if the porosity is same, but the pore size is different. Okay, so this type of models, this type of things can be more effectively captured using pore scale models. So we have a case here where the porosity is kept same, but we have smaller pores, medium sized pores, and larger pores here. Okay, without convection and with convection. And if we compare the results here, even from here also, you will see that melting is much faster for smaller pores and melting is slower. Melting is still completing for the larger pores. And we will see also that for smaller pore, the effect of convection is very less as compared to the effect at the larger pore sizes. Okay. So for smaller pore, the effect of convection, if we consider convection, we get 20% increase in melting rate. But for larger pore sizes, we definitely need to consider convection because the effect of convection is up to 40% of the melting rate. So again, all these results are present in the papers that I will outline at the end. And if you are interested, you can go through more of these results in those papers. So similarly, for energy storage also, for smaller pores, the energy storage is faster. For larger pores, the energy storage is slower. Okay. So I will just conclude this part. Okay. So my main idea was to give you a glimpse of pore scale models for PCM metal foam energy storage system, so that you can use similar types of model or develop similar types of model for other energy storage systems or say other applications like thermochemical energy storage system or cooling systems. Okay. And for this particular model, we have seen that the pore scale models have the advantage that it can show the effect of pore size, or it can capture the effect of pore size even with the same porosity. And some conclusions are that we have seen that the melting time decreases with decrease in porosity and pore size. So if the pore size and porosity decreases, melting time decreases. So we have faster melting. Convection is higher for higher pore size, which is understandable. More area is there for flow to occur. And also for higher porosity, convection is higher because again more area is there. And typically we have seen that for 80 to 90% porosity, convection is very important. But around 50-60% porosity, convection is not important at all. Okay. So these are some of the papers where you can go through. So from our group, where you can go through the details of this modeling if you are interested. And finally, I would like to thank my students Dinesh and Arjun, who has worked on these models, and for the effort provided by Dr. Rath, who provided major contributions on the methodology part of these models. So if there are any questions, I think I have run out of time, but there are still 2-3 minutes. If there are any questions.
Thank you very much, Dr. Anirban, for giving such a nice description of such a complex process within a short span of time. Hope our participants might have enjoyed your lecture content. And if you don't mind, if few of your slides can be shared with the participants, it will be great. Yeah.
Yes, of course it can be.
Yeah.
I will send it to you, and I think you can then share it.
Yeah. Sure. No problem. Thank you. Participants, if you have any question, quickly we can address one or two. Anybody having any query? I think they have no query. So thank you very much, Dr. Anirban. With such a short notice, you could able to deliver lecture today morning.
Thank you, sir,
I'm
for
very
inviting.
much thankful.
Thank you, sir, for inviting me. So I would just again suggest if somebody is interested in this area, they can contact me or Dr. Rath, because we are still working in this area, and can go through the literature also. A lot of interesting work is going on in this area and similar other areas.
Yes.
Thank you, sir, thank you, sir, and thank you, Mahapatra, sir, for inviting me for this talk.
Thank you, presenting nicely, beautiful presentation of yours. I think participants must have enjoyed it, and some of the participants will be contacting you in future for their ongoing research and all. So I once again thank you for supporting the program.
Thank you, sir. Thank you. I will unshare my screen.
Yes. You can stop the recording also. He's working at present here as a director. He has a very vast industrial experience of 17 years in execution of multidisciplinary tasks that include hands-on with project qualification and budget allocation in United States dollar for offshore clients designing the CFD computer-aided engineering simulation architecture of spectroscopic products through laboratory experimentation practice, ensuring thermal stabilization inside the optical system of different spectrometers. Prior to joining Beacon India Private Limited, he worked in several other organizations, companies. Some of them are like Sirtech Solutions Private Limited. He was working as a principal architect since 2020. Prior to that, he was working with, which associated with Amtech India, where he worked for quite a long years, from 2011 to 2020. He was working as a thermal architect in Amtech India Private Limited. Then prior to that, he also worked in Mentor Graphics as a mechanical analysis, as an application engineer in the mechanical analysis division for more than 4 years, from 2007 to 11. And his background education is his PhD in CFD and thermal science from Jadavpur University in the year 2007. And then prior to that, he was did his undergraduate degree in BTech in mechanical engineering from College of Engineering and Technology, Bhubaneswar, under Biju Patnaik University of Technology in 2000. So this is all about the very brief introduction of Professor Dr. Sarkar, and of course I may miss some of his industrial experience. If I miss, please pardon me. And now I would like to request Dr. Sarkar to present his lectures. Dr. Sarkar, please.
Yeah, thank you, Dr. Rath, and good morning to all. Thank you again for a nice introduction. And your introduction actually little made me nostalgic in terms of the spectrometers. Yes, I spent a very long time in the spectrometer and spectroscopic devices. So from there, this actually, I done my PhD in the field of radiation and convection, as you know, but then eventually in the spectroscopic segment, I got introduced to the phase change because I'll just give a brief, which are not there in slide. In a typical spectroscopic equipment, if you see, there are various type of spectroscopic devices. Out of that, the one primarily which does the chemical synthesis of samples, so it runs by a technology called ICP, which is inductively coupled plasma. And during the plasma, so there used to be a torch. Inside the torch, outside the torch, there is a very high voltage electromagnetic coil, and that electromagnetic coil will be excited in a range of somewhere 27 to 40 megahertz. And in that excitation range, the inside, because this coil will be surrounded on the glass torch. It's a quartz torch, and inside the quartz torch, this sample will be, the chemical sample which need to be synthesized, they will be atomized, and in the atomized form they will be injected inside this torch. And now, because of the electromagnetic high voltage induction, so this atomized particle will be getting heated up in the range of somewhere 9,000 to 11,000 degree Kelvin. And obviously it will illuminate with different light spectrums. And the moment these particles will illuminate with the light spectrum, our spectrometer, we have the arrangement of the spectrometer with prism and other optical devices, which takes the exact ray with the respective wavelength to detect that what are the composition behind the sample. But in this whole process, I'm not going to the spectrometric optical system details, but then my interesting area was when this atomized particle, or it will get introduced in this torch through the nebulization process, all the particle doesn't get used to ignite. So a few particle will get ignite, and remaining particle will it will get deposited over the glass surface. And since the temperature of the, you can imagine inside, because of the electromagnetic induction phenomena, the temperature was going up to a plasma level, and because of this temperature, the glass also will be heated up significantly. The quartz surface will get heated up, though we used to have some diamond coating and some graphite, very polished coating, but then since it is too much heated up, any accumulation of the droplet used to crack the glass at the customer's interface, at the customer's places. So we faced a lot of challenges, because one glass torch used to cost us around approximately $2,000. So that's a huge cost, which customers always reluctant to spend, always, because of just a crack. So we had to address this part, and that was the introduction, that we really wanted to understand how the droplet behaves there. That was my introduction to understand the field of droplet dynamics more closely. We used some of the commercial tools, but then the results were not satisfactory, because in commercial tools they supported mostly up to equilibrium plasma, but the non-equilibrium plasma part they did not support. So hence, I developed my own code on that, and I got a significant amount of exposure in that. So that's the exposure. So hence, Dr. Rath, you reminded me that particular period of my laboratory experiments and numerical computation. So with that experience only today, I am, I'm very much happy that I got an invitation from IIT to present my research work carried out then. Thank you very much, and let me start this. So today I will obviously, I will be speaking on mostly on the phase change processes and its potential application. And now I am responsible for promoting the simulation range of products of SolidWorks, and obviously in our SolidWorks simulation, now Simulia and Abacus and Xflow, all the important high-end simulation solvers get introduced inside SolidWorks. So SolidWorks have a huge simulation community. So obviously I'm responsible to put forward that. So a mixture I'm going to present to how the phase change process is and its application, and how SolidWorks represents it in the later section. So this will be today's overall agenda of my presentation, and let me start with the so if you can see, I mean, just a brief understanding about what exactly a phase change process. So if I let me change it to my pen mode. So this is a typical, all the concept what about phase change we generally occur in the class 12 syllabus, a very base level, that is, anything gets converted from solid to liquid, and the state gets changed because of the heat addition, and then from liquid to gas, and then gas to plasma. Okay. And then in the case of sublimation, yes, there are some direct transfers from solid to gas. Now, if I little bit elaborate it on a typical process of solid, liquid and gas, then this diagram will be very much realistic diagram, which will give an understanding how the solid, liquid and gas exactly interact with each other in this pressure versus temperature plot. And you can see the triple point, and then the melting to freezing point, the vaporization to condensation point, everything in a very much compact and very much technical way. This diagram will represent the transformation happens from solid to liquid, liquid to gas, and eventually solid to gas. This is a very famous diagram. I feel it's a self-explanatory. Just I'll tell it. People already understood by seeing it. This is a typical, phase change diagram. I have put it for water. So you can see the moment, we heat up the water, the main thing, it first in the solid state, the temperature will rise as you are inputting the heat. And then it will reach up to the freezing point, and then there it will start melting. So this is the part is the BC part, which takes care of the melting part, and and we say that is the latent heat of fusion, which takes care of the energy absorption part. And exactly when we reach this state, when the transformation happens from solid to liquid, we say it as phase change, and it remains as an isothermal process, because as you are adding the heat, it is being absorbed in the latent heat of fusion. So the temperature remains there. And approximately, I collected a data. It's approximately, it has been seen that it is around 2260 joule per gram. This amount is, and then once the whole ice transform to liquid, and then obviously the whole liquid temperature will go up again, further adding the heat. And then again at the vaporization, the same thing happened. The phase change happens again, the vaporization, and we claim it as the latent heat of vaporization. And this is approximately 334 joule per gram. And from E to F further, the gas will reach, it will go further heated and superheated region. Now the main player of this phase change phenomena, that is interface. If a driver, the main driver of this phenomena is interface. So the study of phase change is nothing but the study of interface. So the interface is a very wide definition. Let me start with, like, interface between the phases has very different properties. Now the basic concept is how we define the interface. In the coming slides, you will get to know that the main concept behind the interface is the change in the property, certain change in the property of the fluid between, certain change in the properties exactly during the interface, because the interface held between two different fluids. Now that's a very important and crucial understanding we have to set up, that how to define that particular interface at every numerical step, so that the property at the interface will be correctly captured at every numerical iteration. And you can see here that interface may control between phases, liquid to liquid, liquid to gas, and gas to gas phases. And because of the small extent of the interface relative to the bulk, small changes in composition of the interface may have large effect in the interfacial properties. Of course, that is obviously we are going to further look at this in the coming slide in a more detailed and descriptive way. And this can be exploited for all kinds of chemical and vaporization process. Now, if you little come down, boils down from interface definition to the little bit micro level further, that is the main role is taken in this interface dynamics is surface tension. Now, let's see what are the forces which are there inside a fluid, especially when it undergoes a phase change. So there are mainly two different types of tension. One is interfacial tension and one is surface tension. Now here we have to understand fundamentally the interfacial tension and surface tension. There is a principally, it is different. The surface tension which act exactly parallel to the surface, okay, exactly which is holding at the interface, you can see this is completely parallel to the surface. But the interfacial tension very near to the interface, if you see the intermolecular forces, that forces prevails across the sphere. Okay, so in every direction these forces exist, in this direction, in this direction. So this part is the interfacial tension, and the difference between the surface tension and interfacial tension, this has to be understood. Now, however, the main forces involved in interfacial tensions are the adhesive forces between liquid phase of one substance, either a solid, liquid, or gas phase of other substance. That is obviously. So this part has to be understood with little more importance. The interaction occurs at the surfaces of the substance involved, that is at their interfaces. This is a very much we played in our childhood days. When we started understanding the natural phenomenon, how the natural phenomena happen in our childhood days, we used to see that yes, if we put some oil on the liquid or any water or something, I used to remember, that's a very crazy part. I used to um, admire that how the oil getting is floating over the water. And yes, I used to try to mingle it. Why it cannot mingle if sugar is getting it's mingling? So we used to try, and then exactly the thing used to happen is the oil will form a small droplet. Okay, and these small droplet will be across. It will look like it has mixed with the whole liquid, but then eventually to regain its surface energy back, because always the the tendency of the nature is to acquire the minimum potential energy, and for that it has to have a minimum surface area. So again, this droplet, if you put for some time, this droplet will aggregate, and then finally it will become the same and the back to square one. So if you can see this and this, they are back to square one. So it is because to acquire the minimum potential energy. So this is a very interesting thing which we see in that immiscible fluid, how the behavior of it to immiscible fluid. So today we are going to discuss why I presented this particular slide. Today mostly the discussion will happen, or mainly the discussion will happen the interface between the two immiscible fluid. So and during the chemical reaction and vaporization. If you see here, the vaporization, the interface is driven by temperature gradient. Okay, that's one of the main thing. And this temperature gradient, if you see the equations which drives this temperature gradient and the interface definition at the vaporization level, is the main equation is Clausius-Clapeyron equation, which calculates both the vaporization and species mass fraction held at the interface. Species mass fraction is for any chemical process which get involved, or chemical reaction which get involved, and the interface shifts. So the same Clausius-Clapeyron equation, only there you have to take the species concentration gradient, and in vaporization we take the temperature gradient. That's how it is. So the mass transfer during both vaporization and chemical reaction generates an imbalance inside the mass conservation. This is a very important statement, because this is the statement which we are going to see in our next slide, and not next slide, I mean the coming slides, that exactly when the evaporation. So there is a different thing between a non-evaporating interface shift and interface deformation, interface stretching, and with vaporization, the interface deformation and interface stretching, they are two different. In the first case, where the interface is it is not non-evaporating case, the interface is stretching, interface is deforming, with making the conservation of the mass conservation with adhering to the mass conservation equation. So basically the continuity equation at every iterative step is getting addressed, and the continuity equation remains that the mass conservation equation remains there, and it is always adhered. But in the vaporization case, exactly, the mass conservation equation is not adhered at every iterative level, and what is happened, that creates an imbalance in the mass, and this imbalance drives the interface phenomena, which we are going to come to the coming slides. So I just wanted to put the highlight of this. Now I would like to take you to the numerical approaches which used to capture the sharp interface. So there are widespread numerical approaches have been taken from ages together. I'm not going to discuss too much of them, but the major computational expenses which already had happened in our last few decades, they are important, and I'm going to discuss mainly that. And if you see, there are three popular approaches. The one is the typical Lagrangian method, and other as the Eulerian method. Eulerian method, if you break down in a roughly, it is level set and the volume of fraction. So the volume of fluid. So now this volume of fluid method is mostly adopted by all the commercial CFD tools nowadays. We'll see all these. The first one is the Lagrangian method, which we say as a boundary element method, because here what we do, the basic steps I have discussed, as you can see here, the grid follows the fluid. This is one important statement, very important statement. Here the grid follows the fluid. So and then few authors who have done the work, Feng and Hu, Oren and Boris, And this is a fairly complex approach, but then this approach was simplified by another author called Tryggvason, by developing the front tracking algorithm in the same, using the boundary element, finite element, one-dimensional finite element method, Lagrangian finite element method. He developed this front tracking algorithm. This front tracking algorithm really stands very powerful in addressing the interface shift, both in the non-evaporating, also in the evaporating component. Now here, the one lacuna is there, since you are defining it here. It is defined like the whole interface of the let's say a droplet. It is broken in different Lagrangian element. Okay, n number of Lagrangian elements. So what we do here basically, if the because this is a Lagrangian Eulerian solver, so the basic thing will be Navier-Stokes equation will be discretized in the Eulerian cell only, but the interface and the surface tension forces will be discretized over the element on the boundary element method, and these are the one-dimensional Lagrangian element will be constructed, which will be constructing the complete interface. Always this Lagrangian element will be one-dimensional lower than the Eulerian element. If you are solving the Eulerian in the 3D, then the surface will be of 2D and the Lagrangian surface element will be of two-dimensional element. And if you are solving in 2D, let's say in this case, I have my code I have developed for 2 dimension. So here the Lagrangian element will be one-dimensional lower, that is nothing but one-dimensional Lagrangian element. Now, but here one important lacuna and the drawback is because of this, the connectivity, already pre-established connectivity, this is 1, this is 2, this is 3, like that n number of Lagrangian element will constitute this, because the list you are preparing this because of the element merging you have already done in the finite element. What will happen, this Lagrangian element will never leave each other. So what will happen in case of a deformation, let's say additional deformation of the surfaces, some extra additional element will be created. But what I wanted to say, this chain will never be broken. Okay, if the interface deforms on a convex way, so there will be more number of elements will be addressed. If it squeeze, then the number of elements will reduce, but it will never break. That means, I mean to say, if a droplet breaks down, so this part you will never get in this front tracking algorithm, because it will not allow you to make this breaking point, because of this the algorithm limitation, that you are not giving an allowance for this Lagrangian boundary element method to get separated, because you have defined it as an integration and the complete energy conservation happening basing on this intervention. So you cannot cut the chain. You cannot cut the chain. So the chain has to be there. More number of elements can be populated, less number of elements can be populated, but the chain has to be complete, the Lagrangian finite element chain. So that's the limitation of this. Hence, for the next level of getting a segregation of the droplet, the coalescence of the droplet, we have to shift to the Eulerian method. And Eulerian method is pretty simple, because you are capturing everything on a single grid, that is Eulerian grid, and that to fixed grid. That is one of the very important technology which have been developed. So that is the first thing on the Eulerian is level set, where a Eulerian computational technique for capturing the moving boundaries or interface you have developed. And here the main driver is the level set function, and we will see how the level set function drives the whole the level set formulation. And this level set function, the most importantly, this level set function will get distorted at every advective equation. When the advective equation will iterate, this level set function will distort, and we will regain or reinitialize this level set function back to the thing by means of a function called sign distance function. This is a very important function which we are going to discuss. In volume of fluid method, you can say it is an elder brother of this level set only. Almost same. Here the thing is that the main concept is here, every cell they are calculating the fraction of the fluid. Okay, the volume of the fluid is there, and divided by the total volume of the cell, by which you are dividing a proportion, and the interface and the normal vector, here they are tracking from this particular this volume of fluid, this fraction, that is alpha. So this is the beauty here. All the normal vector are defined basing on the distance function and the volume of fluid, that exactly how much proportionate percentage of fluid inside a particular volume. So that is almost similar. When we will explain this both the things, you can understand that there is a lot of similarity is there in these two methods. So we will come with pictorial view instead of discussing there. So if you see this, I taken it from a Google, a very beautiful picture of a droplet, and let's understand the front tracking algorithm. So here, what we define is the main Navier-Stokes equation. You have already seen this is the mainstream Navier-Stokes equation, and now the extra part is nothing but this is the surface tension part. This surface tension part, what I exactly said, this particular surface tension, you can see it's an integral over the whole length of the surface energy. So to calculate this particular surface force, and this surface force has to be just it is getting added to the main Navier-Stokes equation. Now, and this total happens now, this individual, if you see, this is happen on the Lagrangian grid, okay, and this is happen on the Eulerian grid, okay. So once the information come to the through Lagrangian grid, and once it is getting added, the the total things finally happen in the Eulerian grid. So this is a very beautiful way. You can see here. Another thing is the interface of the single droplet has been tracked by solving the Navier-Stokes. I have written here, and the main thing here is the jump discontinuity to incorporate the effect of the sudden change in the fluid properties. This is the part which we are defining the jump discontinuity by using Dirac delta function. Okay, so if it is 0, you are on the same phase. If it is 1, means the phases get changed. So, with utilizing that property, and this is a Kronecker delta function, we are making two arguments here. That one is which is at the existing phase, okay, either in the liquid or in the gas, and this x with a subscript of gamma, it represents exactly the space partial coordinate at the interface. So this part is very important here, and how we are addressing this particular change. Now, first, how the Lagrangian elements are defined over the Eulerian cells. Now, you can see at a particular part of the interface, these are the Lagrangian element as I shown, and you can easily understand this part, as we are considering I equal to 1, and this part we are considering as I equal to 0. Now, here one most important part. First, you have to understand this. Any particular droplet, it is undergoing this type of forces. This is the viscous force which is acting upward. Okay, this is the force due to momentum which is coming due to gravity. Consider a droplet is falling in a natural gravitational action. Now here, how the interface being defined here, exactly this integral function, it is defining the sharp interface. Now here, this Kronecker delta function, this is we are calling the discontinuous Heaviside function. Now here, exactly to make you understand how this function works, I just made, because I honestly did not have that much time to put them through equation editor, so I put it in little hand. Kindly excuse me for this. So this Dirac delta function, it exactly okay, let us consider it. Had this Dirac delta function not been there, then what would have happened exactly? Without considering the Dirac delta function, could we not have solved this previous equation, this particular equation, without considering the Dirac delta function? We could have, but the problem was, let's say without the Dirac delta function, if you solve, so your one side, this side, the interface, exactly this is the length of the interface. You can see this is the length of the interface. Okay, I have defined here, I have widened it for your visibility purpose. Now this side is one fluid, heavier, denser fluid, and this side is air, the rarer fluid. Now what happened? If you do not consider the Dirac delta function, what will happen? You will simply have to make a linear interpolation of the interface, because you don't have any other choice. Now linear algebraic interpolation will not hold correct because of the nature in which it gets the vary, and in which the interface gets its updates from all the nonlinear equations. It won't remain linear likewise. So hence we use the Dirac delta function, because this Dirac delta function, it is allowing us to develop, because you see the integral of this whole delta function, okay, over the whole region will be equal to 1. So almost you can consider it's a sort of a finally converging to a Gaussian function which have a probabilistic sort of a distribution, and you can see this probabilistic distribution I have just represented it here. Now what happened? Because you are multiplying these things over the linear interpolation of the densities, what is happening? An approximate interface is getting changed as per the iterative process adapted, because this is the change in the interface you wanted to adapt. Let's say in case of a particular iterative state, your Dirac delta function and because of the x and x prime, I mean to say x gamma location, it got changed over the interface. So let's say the Dirac delta function distribution function will behave like this, then obviously it will pull that time at that particular iterative state, the distribution, it will fall on something like this. It won't fall the previous line. So likewise, this Dirac delta function carries that ability to make the information getting shifted inside the interface to make the jump from one density to other density or one viscosity to other viscosity. So it's a property adjustment we are making by this particular function, and finally we are getting added to the interface equation. Now here already I said the interface is defined by n number of one-dimensional Lagrangian elements which are interconnected to each other, address the stretching and contraction occurring at the interface during the droplet journey. Density and viscosity will be taken as randomly, that already I have told, in the Eulerian cell, whether falling in liquid or gas medium. Upon saying this, now we have to understand the remaining part of the things we solve in typical Eulerian cell. This is, the continuity equation, as I already said. Okay, now here is the catch. Please understand, if it is a I already told it in the around 4 slides before, that for a non-evaporating interface, the continuity equation always adhered to this condition of mass conservation condition, that is, grad of u will be equal to always 0. But the moment the condition will be evaporating, okay, or any chemically reacting, this additional mass will make it, this mass imbalance will have to be addressed by this particular component, and this mass imbalance will be the main driver on the defining the further interface of the evaporation process, okay, or even the condensation also. Now this you can do, I shown here a typical grid management. I used a staggered grid. Okay, you can see here this is the UV are getting shifted accordingly. You can do it on a collocated grid as well. There is no such hard and fast. Only thing in collocated grid, in case you occur, you come across any checkerboarding, then the solver will show some unstable behavior. But then otherwise, lot of my other codes I have developed in collocated grid with adequate safety measures, taking the added dissipation part and all, it worked well. Okay, because some complex geometry, sometimes the staggered grid, it will be challenging for you. But here, since I have developed it on a regular geometric condition on cylindrical system and rectangular system, so I considered this as a regular staggered grid approach. Now here, as I already said, that the moment the evaporation of chemical reaction is happening for the changing the interface, what will happen, the extra amount of fluid which is getting evaporated, you can see this is the fluid, this HLG, it is the latent heat of vaporization, amount of fluid evaporated, this is the gas density, and this is the density of the liquid, and again this is the interface function, the definition of the interface. And this particular thing, the overall thing, it is creating an imbalance, and this imbalance is addressed by this grad dot u. Now this, once this imbalance get addressed, this imbalance has to sit exactly this energy equation. Okay, now otherwise your energy equation used to remain up to this, but now because of this has happened, so you are in the energy component, not the exact one. What I mean to say, this the contribution, not this whole equation will sit, but the contribution, because of this imbalance occurring in the continuity equation, the similar imbalance in the energy part, the thermal energy imbalance, will be calculated on a proportionate basis, and this also has to be added in the mainstream energy equation. So these are the two important changes in the equation level we make it if we are considering the interface getting shifted because of the evaporation process or any chemical reaction process. So only chemical reaction, you have to just mention it through species concentration things. Now here, if you now move to the next slide. Now here, the main thing you can see here clearly the species jump discontinuity condition, how I have mentioned the species jump discontinuity condition. So here you can see on this particular picture, I have considered a node here at this position x plus y plus, x minus y minus. Okay, now these nodes, if it is going out of the domain, because sometimes what will happen when the droplet will go towards the boundary, you may face, you are shortfalling, your boundary may come here. Okay, your boundary may come here. So at that time, on the boundary condition, this node will become then ghost node. Okay, so that also you have to take care. I have not given too much detail on this ghost node part. It is almost in the similar level you have to take care. But the main definition is you can see here, for a normal, if it is lying within very well within the boundaries, this is the main condition what we take, the mass balancing happening through this, the difference in the temperature gradient across the normal direction. That is one important thing. This direction has to be always normal to the interface, because that will drive further interface shift at every Lagrangian element. Okay. Now here what we do, the vapor mass fraction at that interface we have to again capture by means of Clausius-Clapeyron equation, and this vapor mass fraction we have to first calculate, the vapor pressure we have to calculate, which we will calculate from this, we have the interface temperature. Okay, we already mentioned, and this is, we have the fluid bulk temperature. Now the ambient temperature and the interface temperature, obviously it will constitute the temperature gradient, and basing on the temperature gradient, first you have to calculate the vapor pressure. Upon being calculated the vapor pressure, then you kindly calculate the mass fraction of this particular thing, at that particular droplet on that interface, what will be the mass fraction at that iterative step by this particular formula. So this is the equation 7. Having addressed this part, now the adapted solution process, you can please understand here the Navier-Stokes equation we don't solve on a regular simple algorithm, on a regular simplex. We don't put it like that. Here we make it as a predictor corrector type method, because there is a reason for that, because this whole solver is developed first of all on a transient step. Now what happened? The main equation is this one, the continuity equation. You can see at this n plus 1 n denotes the time. So at time step 1, time step n plus 1, we want to calculate this particular, the rho n plus 1 and u n plus 1. And this part is the continuity equation. We understand that. Now here we just break this continuity equation in two different. Finally, if you cut this portion, it is regaining back the original equation only, but then we distribute, and this advective is nothing but it is consisting of this whole advection, diffusion and gravitational and all the other surface tension term. I have dumped it everything in A superscript n. Now here and only the grad P will be here. Now what will happen upon distributing this part in this particular format? What we will obtain is, you can see here, this section, the first section, it is, I can put it as 8 superscript of n, whereas the later section I have put it as this grad P section. Okay, now this reveals an important strategy here. The important strategy is, the basic thing is here. Finally, if I make another gradient operation on that particular last equation, if you see here, okay, on this u star upon, if I make another gradient function, okay, on the gradient operation on this, what it will happen here is this grad dot u star and grad dot u n plus 1. Now we know this is one part, and here it will come as grad square p. Now this forms a typical Poisson equation, and the benefit what we are getting here is, for no evaporation case, we know at the n plus 1th time step this grad dot u component will constitute 0. Okay, but for the with the non-evaporation component, then equation 3 you have to substitute. Okay, please remember. Now here what will happen is that you got, because of this grad dot you formed your velocity at the Eulerian cell as a function of pressure. Okay, you obtained from the Navier-Stokes equation, you have made it at the n plus 1 step. So this is one thing you have obtained from here. And basing on this pressure field obtained from the above equation, now you can see we can update the velocity at the neighboring time step. Now you can see here how we are updating the velocity here. So we are making this un plus 1 will be equal to u star minus this one. Obviously it will happen like this. This is the, I have put it as 11, equation 11. Now here one important catch is there, that these velocities you all obtained in the Eulerian system, now you have to transfer it back to the Lagrangian cell, because finally you have defined the element of the Lagrangian element as a one-dimensional finite element, and the information on the finite element grid has to be shifted from this finite volume to finite element grid, and there are interpolation functions which are used to shift this information. So the most popular interpolation function is Peskin's interpolation function, which I have used particularly to shift from this ij to directly to the interface on the Lagrangian interface function. So this is a very much pure form strategy. Most of the authors, they adapted it, including Tryggvason, the other authors, couple of authors who followed, they all adapted these particular methodologies and this particular shifting function or the interpolation function from shifting the variable information from Eulerian cell to the Lagrangian cell. Now here I have given little detail that you can see here from Eulerian cell, you can see this interpolation function, how they are using it, where this delta sk is nothing but this is the Lagrangian element distance for one particular cell. You can kindly see this one. This particular delta sk is the length which you are measuring at a particular stretched interface at kth cell. Okay, and h is the typical grid size, depending on your, if you consider that your x and y grid having aspect ratio of 1, so h is the specific one, and if it is del x and del y are different, then in algebraic composition have to be made accordingly. So now once it is shifted to the Eulerian grid, from Eulerian grid to the Lagrangian grid, now you are at the interface, and I have just mentioned this is the Peskin's formulation. Kindly see, this is what I have used. This is the Peskin's cosine function, which is the most popularly they used, and I also use the same. Okay, in the interface to define it. Now once you got the things in the Lagrangian coordinate system, and then the Lagrangian system, the interface, exactly the x coordinate of the interface at n plus 1th time step, you are updating, okay, with the from the nth time step by the help of this delta t, and then the calculated the velocity which you already transformed from the Eulerian to Lagrangian by this interpolation function with the normal vector. Okay, so this is the typical, and the solution step, how the most important thing, which are the solution step we adapt for this whole process is calculating. First we are calculating this extra heat flux at the interface if it is a evaporating condition. I made the algorithm considering the evaporation is there. In case it is not there, anyway you are putting the grad dot u at n plus 1th step is equal to 0. So now this will be distributed onto the fixed grid using Peskin's distribution function. Then the interface advection is considered for the next time level n plus 1, as already shown in the by means of the predictor corrector method. And then the energy equation has to be solved to get this new temperature at this particular place for a evaporation condition. And then you can see here this is calculated at the distributed onto the fixed grid. So this is the heat, okay, amount of heat generated, it has to be distributed, and then you have to solve the Navier-Stokes equation to get this u n plus 1. To solve this, you need the surface tension term at each frontal element to the interface location, and we know how the surface tension term has to be added to the mainstream Navier-Stokes equation, which has to be solved on the Eulerian grid. Then updating the material properties, that is very important, because the density and the viscosity will get changed on exactly at the interface at every iterative step, and you have to address that diffused interface. And then reconstructing the Lagrangian interface grid at each time step. So obviously the Lagrangian grid has to be reconstructed based on the information so that it will get shifted at every place. Now, so this is overall, that how a typical front tracking algorithm works on a nutshell, it's a very huge part. It's not small. Actually, everything has to be. Actually, we use another inverse function, which from Lagrangian to Eulerian transformation, we make another inverse function, but it is almost similar. Hence, I have not again presented it separately, because otherwise the things will be very difficult to restrict in time, because we have to discuss a lot of things. So I have used this part, and now on the cylindrical coordinate system, kindly understand, I given a representation in my hand where I have developed from my own code. You can see here there are four basic staggering mechanism followed. One is in blue color, which is representing the pressure coordinates. Okay, the red color is the u velocity coordinate, which are the radial velocities. The v color will be the azimuthal velocities. You can see all the ij, the vij is at this e location, the pressure ij is at this central location, whereas the radial velocity location is in this particular thing, and these are the property updates. Okay, the viscosity and the density update, property update happening at this particular location. Okay, so these are the four different centers. So like this, you have to populate your grid. This is, I made it in a single color because it will be easy for you that how the grid structure you are making basically for this type of calculation, typical calculation holding on even on a spherical coordinate system. The remaining thing will remain same, only the equation you can see it will get changed to the cylindrical coordinate system. So that's the only, and you have to calculate obviously certain extra the Reynolds stress part you have to calculate extra separate, because in cylindrical coordinate system the coordinate expansion takes little longer time. And one important thing here you have to understand very important seriously for the spherical coordinate system is, or any cylindrical coordinate is, here in the xy coordinate system, this the interface which you are defining and the Lagrangian element, the surface tension forces which you are representing in a rectangular coordinate system is much easier to represent, because on a xy coordinate system you are getting a benefit of the balancing the surface tension on a in any type, the balancing of the surface tension happening on a particular element, you can make a resolution much easily basing on the x. Okay, basing on the x and the basing on the y coordinate system, which is pretty much simple here. So this you have to take this, resolve this component over the xy, and the force balancing become very much easier here. But in the cylindrical coordinate system, it will be challenging, because you cannot take the droplet center as your main epicenter. Okay, because there will be the droplet will be inside a box or inside a pipeline. Okay, in the cylindrical system. So what will happen? The pipe center will be somewhere here, and the drop center will be here. Now what will happen is that from here, the main coordinate system will be defined from here, and I faced a lot of challenges in addressing this particular element direction, because let's say the same element here. Okay, let me change a little bit on the ink color. What will happen is, the main challenge is here to represent this particular direction, in this r and theta will be very challenging, because you have to be really careful on every delta theta addition, how this r and theta is getting changed, because in this particular every case you will have a different r. From here to here you are going to have a different r. From here to here, everywhere the respective r will get changed and its component will get changed, and the balancing of the component you have to little struggle, but you can do it. But you have to really balance them very accurately, else your Navier-Stokes equation will be diverging, because I faced this challenge a lot of time while developing this. Hence I thought it is to be told. And for evaporation also, kindly see this particular part. You have to make this balancing, because any time the interface gets shifted in this evaporation, you have to really be careful on the gradient part while calculation of the normal vector. Every time the gradient has to be calculated accordingly, because again you are going to have the things on the r coordinate system, and in r coordinate system so in the r coordinate system, the problem is it will happen every place if in a stretched interface and all, when you want to calculate the exact normal vector which is from this side to this side, you will have the resolution challenges will be much higher. So you have to be very careful, because the big problem is in r theta coordinate system, when you will start increasing the theta, the sine theta part, it will remain positive up to this much. Okay, and sine theta and cos theta, then it will change. The sine theta will remain positive up to this, but then the cos theta will start negative from here. So this part you have to be really careful on the domain and range expansion of the sine theta and cos theta component. This is very important, because otherwise you cannot balance your equation. Please remember, because this sine theta and cos theta you have to put everywhere, literally, to balance this surface tension component which you are going to add to your Eulerian cell. So kind for this part. So just I thought to put it to you. So this is a thing. It is I'm just the code which I have developed by myself, and the best way to exemplify is give some comparison that whether the code is running correct or not. I honestly did not get much time to put forward too many graphs and curves. I was running out of time because of the COVID situation. In office and business also had little challenges. I pardon that excuse, but I presented, however, the situation what I could able to generate. You can see here, this is the condition. I have generated one droplet of, you can see which is there at a 0.2 meter and 0.5 meter of the coordinates system. This is the center of the droplet, and I am blowing air from this particular side on the first droplet, from this droplet. Okay, and these are the simple wall condition, the no slip condition, and this is under the action of gravity, how the droplet will perform. So this droplet is an elastic droplet, and this is a plastic droplet. You should get an understanding that how an elastic droplet and plastic droplet should behave, and whether the behavior is getting replicated over these particular things or not. So kindly see this animation if you are able to see. If you are not able to see, please let me know. My screen is running with the dynamic animation. Someone confirm me if you can able to see this animation part.
Yes, sir, it is visible.
Yeah, so kindly see. Thank you very much. So see, now the left side droplet, this is because of its elastic nature. It is going to, after colliding, it is going to regain back its shape. Because of the surface tension forces will make it back to shape, but because of this plastic nature of this particular droplet, surface tension forces will not be able to make it back to the shape. And you can see it's like a sticky fluid typically. The physics also, if you see from a vertical wall under the action of gravity, how it should trickle down from the things. But whereas the left side, after completely compressed, but then it is getting back to its shape. That is most important. It is making this bouncing back action with this pinching effect. Okay. I made further some study on this pinching effect also, but then because of the lack of time, I did not present it here. And but this droplet will be regaining its shape back. But whereas this particular droplet, it is making it slide, but then it will never be able to, make its shape back. So that is what on this particular part of on the front tracking algorithm, how, but this, as I said in the beginning itself, on the front tracking algorithm, the main disadvantage is that you can't break the chain. That's it. You can't break the chain. Whatever do within this single droplet environment, you can do n number of experiments, and this is very fast also compared to Eulerian algorithm of level set and volume of fluid. This Lagrangian front tracking algorithm, transient algorithm, is much faster because the interface is defined directly by a linked list, which is defined by you. So this is one benefit of this Lagrangian Eulerian element. So I just want to put it forward for 2 minutes. I would give it to the audience back till this, because now we will be shifting to the Eulerian part. If there is any question so far on this particular front tracking algorithm of the Lagrangian element, you can ask so that I can, then I start the next session. Over to you, people.
Yes, participants, if you have any query, you may discuss. You may raise your hand. I think there is no query from the participant side. Yeah, Dr. Sarkari may continue.
Sure. So thank you all. So now, let's get back to the, okay, sorry, another, the same thing, sorry. In front tracking algorithm, now okay, this whatever you seen, this is without evaporation process. Okay, only the interface deformation happening, but the evaporation not happening. Okay, now with the evaporation process, I captured another of my own program. So this is the literature published by Irfan and Martin. You can see here, the drop is falling from here with a high temperature chamber, and the drop eventually getting evaporated and making a crescent shape at this particular location. Okay, and the shape of the droplet is basically driven here by the two important numbers, that is Yotvos number and another is Morton number. These numbers which constitute the shape of the droplet, what it will undergo in case of an evaporation. These are the two non-dimensional numbers. And here initially the droplet temperature is at 373 degree Kelvin, and the temperature in the domain I have considered as 480 degree Kelvin, so that the evaporation should take place. Okay, now as the temperature will be more, the evaporation will be more faster, but then the numerical stability you have to be little careful, because too much faster evaporation, it may need more reduced time step. Okay, because that CFL condition also you have to say that Florent, Frederick and Lewis, the CFL condition has to be also satisfied, because if you put a very high temperature at this particular, let's say some 1800, 1900 Kelvin, it will evaporate, but then there are high chances the solver may also diverge unless and until you reduce the time step in that particular scale to maintain the CFL condition in an optimum position. So this part you have to be sure. So you kindly see this, the evaporation part, how the droplet will reduce in the size as the evaporation is taking place. Okay, I could not take the contours of the evaporated component, but however you can see the main droplet is losing mass, and the interface is you can see accordingly the interface is getting addressed, and the Yotvos number and Morton number, it is properly taken care here, and you can see that the crescent shape is being taken and the droplet is squeezing in its size, and because of this particular free fall on a high temperature chamber. And as much the droplet size will be initially, let's say, as much bigger, the evaporation rate also will be that much bigger, because of the more surface area exposure, more surface area makes the exposure more. Okay, so you can see how the evaporation had taken place and the droplet size shrink. So you had seen that the front tracking algorithm, how it runs or it proves well for both non-evaporating component as well as for evaporating component. You can make it as a condensing component also, the surface condensation also, that it can be taken care all in the same algorithm. Now just excuse me, I'll take some water. Sorry, my throat got dried. Now the introduction to the level set method. Here the concept is completely on the Eulerian cell. Here you have to understand, see, let's go one by one. The level set method is an Eulerian computational technique for capturing moving boundaries. Now here the main function is the level set function. Okay, it is defined in a domain as a signed normal distance function measured from the interface. This is a very important statement. Okay, and the value of phi is less than 0 for liquid phase and greater than 0 for this gas phase. Now please understand one thing. How the definition takes place is, it is by this is a total function, is the implicit function, kindly understand. Okay, so this function is an implicit function which drives the total function, but the distance function is not. You have to get the distance function out. The distance function, let's say here it will be, that means if your coordinate system center is this, the distance function you have to calculate that how much distance the interface is from your exactly the center. So the distance function will work out like the x square plus y square minus 1. Now this is how the distance function will go as per the xy. Okay, so let me write it more accurately as d of x and y. So this is how the distance function. Now when you start plotting this at for every value, so obviously the function will be, it will be represented by concentric circles. Okay, because this is the distance function, and you see here when exactly the xy will go till the interface point where the already the radius of the droplet you have made it as 1. So obviously 1 minus 1 is 0. So what will happen? Basically, the interface, exact interface, because of this distance function will be always holding the phi value as 0. The upper section will, the phi value will be in the increasing mode, you can see here, and the interior section will be, phi value will be in the negative mode. So that is what has been said here. The phi is less than 0 for liquid phase, greater than 0 for the gas phase, and equal to 0 exactly at the interface. So this is how you are going to define, and your distance function is the regular normal function. Hence I have given the normal vector always to the interface. So this function, but please understand the difference between the implicit function, okay, and the distance function. Kindly don't get confused, because a lot of places the color function mainly written as a phi. Now here what we make is the phi we are considering as the level set function. So actually the phi we consider this only. Basically this is which you are calling as distance function. Now what we do is, first this phi will be advected, okay, directly by this equation 13. That's the pattern. We directly advect this color function, okay, in the in a transient mode. So this term, like in the Navier-Stokes equation, it just get advected. Okay. Now in the beginning you can see here it is in the beginning the normal distance function such that the phi at any grid represents the normal distance from the interface and positive and negative values surrounding it. Post advection, now the one is important thing, once the advection over, now the what will happen, the interface in after the advection will get very much in a unpatterned way, and the interface get very much diffused, and the sharpness of the interface deteriorates because of the advective nature of this particular equation. Okay, so because of this advective nature it get deteriorated. So that deterioration has to be repaired. Okay, that deterioration has to be repaired, and the repairment we are doing by means of a reinitializing the thing. Kindly remember, the reinitialization is needed at every particular step. This reinitialization function is important to get this distorted interface back to the shape. Okay, so to regain the sharpness back. So this is the main concept which drives this interface phenomena, and interface phenomena through the level set method. Now here if I tell you, kindly see this. As I said, as the interface deforms, this part always phi will be less than 0 in the inside, and phi will be always greater than 0 outside, and at the interface phi will be equal to 0. First you have to capture the exact curvature, because the curvature is very essential here. Since the curvature is going to directly calculate, it will calculate the surface tension forces and the resolving the surface tension forces on the normal direction, because the surface tension forces, unless and until it get resolved in the normal direction, the further ballooning of the interface or squeezing of the interface will not happen. Hence this curvature calculation is very important, and this curvature is nothing but the grad vector. You can see this grad dot n, so there's a divergence of the normal component of the vector. Now here, kindly understand this, there is a difference, as I said in the last time also. Now here one catch is there, that how we are going to repair this interface after, because the interface is badly damaged because of this advective part. Now we need to first calibrate one, because a calibration needed at the interface, or on a method, a calibration needed so that we can gain back the same interface. Now the calibration cannot happen on the main equation, the implicit equation. So there is a very unique methodology which have been taken for this calibration. Now with an example I will start. What will happen? Consider this example of an implicit function of x square minus 1. Now see, this is the implicit function x square minus 1, but the same Okay, this sign, and you can please remember the same thing. I can represent it by this function also. Okay, if I say phi equal to mod x minus 1 and phi x equal to x square minus 1, basically these two things represent the same set of point, that is nothing but this point. You can see the mod x curve. Okay, and the phi is less than 0. That means this is the inside fluid part and this is the outside fluid part, the air part, the outside component. Now all these areas are outside and the sharp interface is this particular thing. So basically we have mapped the sharp interface by this particular modulus function, or this particular type of implicit function. There is a reason why we taken this particular as a definition of the interface modulation, or we can say we can map the interface tracking method by means of this particular function. It is because in this is a particular function where the grad phi value will be always equal to 1. Okay, because the moment you are calculating the grad phi, so any derivative against x, you are going to get 1. And because of this particular nature, for x equal to all non-zero values, you are going to get this grad phi 1. Because this grad phi 1 is the property which we need to expedite every part, okay, to redefine the interface back. Okay, that is what we are using as, and we are calling as signed distance function. This is a very important terminologies they have used because of this particular characteristics of this nature of equation. That is, this grad phi will be 1 for all non x0 component, x equal to non-zero component, and wherever x equal to 0 there will be a kink, and we, in numerical cases, we smear out over the kink. Okay, so our solvers smear out exactly over the interfaces back and forth, but it doesn't exactly come to the interface because of our numerical iterative values. So we don't really need to bother about the exact x equal to 0. It is indirectly defined and it will be constituted in that form. When the iterative steps will be there, it will eventually come and then redefine the interface back. So that's the concept here taken. Now you can consider here the original implicit function. If I take the implicit function which we taken here, okay, x square plus y square minus 1. In this original explicit function, x square plus y square minus 1, as I said, this is the distance function d of x. Okay, if you see x square plus y square to the power half square root minus 1, this is the distance function. But in this function, if I say the grad phi, this grad phi will not be equal to 1. This is the lacuna, that I cannot repair the interface on basing on these functions, because these functions, whether now it is circular, other time it may be something else, because as the interface will take different shape, depending on that, it may sometimes take the elliptical shape, it may sometimes take the hyperbolic shape. Depending on the situation, okay, we cannot rely on this particular function to repair the interface. Okay, because this function particularly, it doesn't always confirm these characteristics. And how this characteristic is going to help us, because this particular function, what I already told, okay, this implicit function x square minus 1 and mod, which is the same representation by mod x minus 1, this is the very much calibrated function which will exactly define the interface on a very much uniquely, that this part is the inside fluid part and this other remaining, the whole section is the outside part. A very beautiful way, the interface definition has been given, and the beauty of this is we will get always grad phi value as equal to 1. Now if we calibrate, we take the calibration point as this function. Now to any distorted interface, we can give a conditional point that the repairment should happen considering the control or the conditional statement that the grad phi of this function has to be repaired back to as near as 1. So once we will adhere this particular calibrated condition in any of the interface, so the diffused interface eventually will get straightened and will get regained back its shape, which we do by means of defining this particular function, so-called a signed distance function. And kindly see, this is very important, and this equation is called the reinitialization equation, because the reinitialization, what is being done here, please understand, the interface value, we are making a transient step here, that delta phi upon del ts. I will come to this ts later. But what is being done exactly here is basically we are forcing the phi to follow this particular nature, that grad phi has to be as near to 1. So accordingly, you have to reconstruct the phi back. This is one important point to be understand, and this is the sign function we adapted here. This epsilon is nothing but the smearing of the distance, how much you are smearing, okay, on the back and forth direction, okay, exactly on the distributed diffused interface, so to get the interface back in shape. Now you can see here the diffused interface condition, the interface was not very well prepared at this place, but the reinitialized interface, it is very well prepared. You can see here, this is the difference between the reinitialized and the diffused interface. Now here one small catch is there. Okay, you done everything, you done that, your phi will follow this particular mechanism of always it will maintain the grad phi equal to 1, near equal to 1 at to reconstruct back the interface, granted. But how you are going to sweep this epsilon, that how the solver will know that exactly I have to sweep a very small distance over the interface at every place. Okay, I don't need to go too deep, because else the things will go wrong, because the interface definition of the interface or the diffusion of the interface prevails on a very small distance. We define the distance, how we sweep over the distance is nothing but we define a virtual transient step. See, there is a difference between virtual transient step and actual. The actual transient step which you have defined, that is the total, I mean the delta t, which is taking care of the total physical time you are simulating divided by your number of grid. Okay, transient number of grid. This is the delta t, and you are making this delta t to sweep the whole the total number of all the grid to sweep over this particular time. But I am not interested to put this delta t, because if this delta t means the thing is in a particular delta t part, okay, it will because of the velocity component in this delta t, if I take this original delta t, the interface will go too much. Okay, the interface will go too much. So already we obtained what is the interface velocity, the u component we have, approximately u component we have. Now this u, if it is multiplied by delta t, the shifting will be too much, we cannot control. Hence we define a separate transient pseudo transient step, that in this particular pseudo transient step is nothing but it is our control. We are just saying 10 step, depending on your pseudo transient step, how much you have considered. Okay, this 10 step will be exactly taking the value of the 10 small transient step of your choice, delta t, which exactly the u, the velocity of this exactly delta t time should not exceed this small value of epsilon. So that means this transient time step is very well defined within 5 to 10 number of iteration, inner iteration only, which will allow the main solver to navigate a very small distance over this interface. Hence, we are defining this pseudo time step. Okay, so the main time step is going on the main loop. The main time step is going on in the main loop, and this is the main loop where the main time step going on, and this is a small loop, a pseudo time step is going on. This basing on this pseudo time step, this is going to navigate over the small thickness. So that is what is the beauty of this pseudo time step, and this is the the sign distance function, how this is working. Now the most important part, you kindly see this one, the main, as I said, the Lagrangian front tracking algorithm is typically lagging the segregation and the coalescence part of the droplet because of the linked list nature of the defined Lagrangian finite element chain, whereas this particular method can do the neck formation region, it can do the segregation and coalescence because of its, it is completely defined on the Eulerian property. First, let us understand how a neck formation zone will happen on the segregation and coalescence of droplet will happen. So basically there are two different energy which balances this drop. Okay, now what are the two different energies? Potential energy and surface energy. Surface energy is developed by the surface tension. Potential energy is by its own weight. Now if I see, I made this is not a very scaled graph, an approximate understanding. when the droplet size is very small. Okay, consider a droplet size is very small. Now in this condition, what generally happens is always you find its potential, its surface energy. Okay, the surface energy will be always greater than the potential energy. Okay, because of its less mass. The potential energy is a function of mass, and you can see here the potential energy is a function of mass. That's why I have made it mass is nothing but it's a density into volume, and it is proportional to this r cube. Whereas the surface energy, it depends on the surface tension and the area of the surface of a sphere. So I made it as a 4 pi r square. Okay, because it depends on the r square. Now what will happen? Initially, you can see, the potential energy was less and the surface energy was more when the droplet was small, because surface energy is more here, you can see, and potential energy is less. But as the droplet grows in size, so obviously the growth of the r cube will be more compared to the growth of the r square, and that's what is happening here. As the droplet grows in size, this potential energy grows significantly higher, and eventually, one point will come where it will exceed the surface energy, and exactly the breakup happens here. Before breakup, what are the stages? From the beginning, when the droplet size is very small and when the surface energy is much higher than the potential energy, this is a very stable phase. We say it as very stable phase. Okay, then as the size starts growing and the surface energy, the increment of the and the gap between the surface energy and potential energy start reducing, this particular part, the neck formation starts. You can see here the neck formation zone, it begins, the neck formation zone. Further, it is as it grows, this particular gap between surface and potential energy is almost negligible, almost very narrow, and this becomes very unstable zone, and the oscillatory behavior and the oscillatory regimes are found. Though I did not make the study for the oscillatory regime, just informing you, this oscillatory regime will found, and the moment this will happen, the surface energy is going, potential energy is going to exceed the surface energy or equal. Exactly the breakup will happen. It will tear from the original droplet. Okay, so that is how the things will be in this particular condition. Now I will just make you, in my own code, this is a 128 GB RAM in a 32 core processor, with a grid point of almost around 150 by 150 grid points. I have captured these two. So the left side you can see here is the, let me run the animation, and I hope you can able to, Dr. Rath, if you can confirm, if you can see the animation. You can see the left side.
Yes, we can able to see the animation.
Yeah,
yes.
and the left side, one droplet is falling over another droplet, and you see the merging happened between two droplet exactly. And here also two bigger droplet, it fall on a swimming pool, and you can see how the neck formation regions are addressed. Okay, and these neck formation regions, eventually it creates, you can see secondary and tertiary droplet. Now here there are some corrections to be made, which I did not get time to. Actually, I solved this is an upwind method, but the problem is the upwind method. You can see the droplets are getting diffused, and they are eaten up by themselves. Now this can be these droplets, the smaller droplets which are eaten up by the solver. You can recapture them back. Okay, I'll just show it once more so that you can see. So these smaller droplets, you can recapture them back. You have to use a fifth order Venno scheme. That is a very good scheme, which I started developing, but then I stopped in between. I did not get time. But in the Venno scheme, lot of published literature, they reported these smaller droplets which are getting, diffused by, it is eaten up by the solver. It won't. Okay. It will come back to the main, and the mass conservation will help very much strongly. So because of the diffusive nature of this upwind scheme, we are getting this little bit, the smaller droplets are unable to return back to the main mass. So this is only one problem, but here you can see the the coalescence and the segregation of the droplet happens through the level set method. So now, as I said, it's the elder brother is nothing but the volume of fluid method. And in volume of fluid method, it is, I would say, it is pretty much simple. Okay, the thing what they made is that, you know, a function f they defined, and this f function, it is 0 if the cell occupied by fluid 1, if it is 1 if cell occupied by fluid 2, and it is between 0 to 1 if the cell occupied is partially filled. Obviously, you know, if it is half filled, it will be 0.5, it will point, it's like a decimal varying from 0 to 1. It's very easy to understand, and the properties will be varied over this. Okay, and this Fij parameter, this will govern the main property. Excuse me, just I'll take some water. Now, so this is now the same way, this Fij, and in the mu also, this Fij parameter, you know, it you can see the property varies with these Fij parameters. Now here the main catch is the continuum of the surface to CSF model. Okay, what is this CSF model? This surface tension they assume as constant. Okay, so what is happening is this, basically they are taking the surface tension is nothing but they capturing from the curvature. Okay, the dividing the curvature by the surface pressure. Okay, so basically the surface tension, they sorry, I meant to say they are capturing the curvature from this surface tension. You can see here the surface tension is defined, and from the pressure gradient and the surface tension, they are capturing this curvature. And from this curvature, so once the curvature is captured, now from this curvature they captured the normal vector component. This is very important. So because the curvature once is known at every integral point, they capture through this formulation the normal vector component. The normal vectors you represent it by this, you know, del f upon del x and this, and that, you know, this del f upon del x and del f upon del y, once that part is known, from this normal vector, the curvature is already known from this surface tension vector, and you know, you are capturing the normal vectors, n vectors, because you know this f assumption is already with you. This Fij parameters is calculated from a guess value. Okay, so basically you are updating your normal vectors, and they see here they have constituted a Poisson's equation against this part. And what they are making here is at a particular constructed interface, okay, where they have lot of assumption, northeast assumption, southwest assumption, northwest assumption, a lot of assumptions are there. Basically the distance d they are calculating from this nx and ny component, okay, at the coordinate system of space coordinate, when the interception is here x and this interception of this a is y. Okay, so like this they are making this interface exactly addressed, because they could able to know the n values, the normal vector values. The normal vector values are being calculated, and on an iterative basis from these normal vector values, the f values are again iteratively updated. Now there are, in lot of places there are different algorithms adopted. Let's say in one cell you get a the curvature of volume of fluid method given an interface of this, and another near neighboring cell given an interface method of this. So they made a middle point, you know, midpoint section. In the midpoint linear approximation, they merged these two things, and both will be going through this midpoint like this, correct? And later they developed some more you know, improved methodologies with nonlinear interpolation, piecewise interpolation. And I have not personally done much research on this volume of fluid, honestly. I just know it upfront, you know, because I have a very good fair idea about the level set method. But this one, you can see, you know, with a more grid and more improved methodologies, you are basically tracking the interfaces very accurately as on when you are improving the grid quality. So that is, and higher order polynomial approximations are considered for improved matching of the interfaces across adjacent cells. This is what is being done in this, basically in the Navier. Now all this whole thing, now I will expose you to my SolidWorks flow simulation solver, which completely follows this volume of fluid method, and you can see this complete sloshing effect, how it is considered in this volume of fluid method. And you can see the chambers which are getting filled from a particular, you know, tank to a different tank, and how beautifully the sloshing effect is being taken in our solver. So this is, I am talking of the SolidWorks flow simulation software, and in this particular solver, it is very well capable of taking this free surface flow, which is addressed by this volume of fluid method. And we have really a very powerful solver, VOF solver, and which can address lot of problem on a realistic situation in pumps, in valves, in the cavitation part, and a lot of other parts. This free surface has a very strong influence in the CFD fraternity. Now you can see that the tank drainage using free surface flow. Now there is a difference in the tank drainage in using free surface and making the tank drainage using theoretical calculation. In the theoretical calculation, you can be using maximum the Pascal's and the Bernoulli's equation, and the Bernoulli's equation will give you just the gradient based evacuation, but it will never give you the what is the imbalance is created in the surface because of sudden in the meniscus level will get down suddenly if you make the this particular tap open. That cannot be addressed. This meniscus and the changes in the flow, it cannot be addressed by means of Bernoulli's equation, where you need a full level of Navier-Stokes equation with a free surface phenomena to be captured to exactly understand the time of evacuation or time of drainage to be addressed in this particular any chamber you are making the draining system. So here I have considered a typical problem where you can see a tank with a level of 3 meter, and the maximum water level before is, you can see here almost it is full 2995 millimeter, and the orifice have been kept 745 millimeter to the center line. The inner dia is this much and the outer dia is this much. And with this, we have calculated within the SolidWorks flow simulation solver how much time it should take and how much realistic it will look like. Kindly see this. We got a drain time of approximately 47.5 seconds, and you can see with a flow rate of 17,676 liter per minute. And this is the Bernoulli's calculation. Bernoulli's calculation says this, and this is the CFD calculation in our solver, and we got a difference of this much difference, and it's not a small. It's a pretty much a big difference. 296 liters of difference you are getting. So, and you can see here the drain time, we are getting a difference of 2.11%, and outlet flow, you are getting a 1.68%. And if you see here how the draining happens with the free surface, kindly see the address of the surface, how the free surface is important in exactly addressing, and the graph is exactly adhering to this particular constituted curve. So that is what we have shown here in the SolidWorks flow simulation. Another important feature in SolidWorks flow simulation is the Lagrangian approach of the post-processor inside SolidWorks flow simulation. So in our SolidWorks flow simulation, we have a one-way coupling method. Okay, so once the post-processor solves the core Navier-Stokes equation with all the free surface dynamics, so this one-way coupling method, we just consider this equation, and this equation being numerically integrated to get all the particle values, okay, on the solver. So this is how the things are updated. It is one way. So only the fluid to particle interactions are taken care, but the back particle to fluid interactions are not taken care here. So but most of our problems are getting addressed in this one-way coupling very beautifully and very promisingly, I would say. And the same thing on the temperature side, on the thermal energy equation, you can see, this is also numerically integrated to see that exactly the particle temperatures are calculated once the post-processor runs. We just numerically integrate this particular equation so that the particle temperatures will be calculated as on when the fluid distribution happens. So here you can see this is a sort of a cone, this is oil catch can. So here it is there are a lot of particles are entering, and here there is a oil, and then as it will make the rotation, okay, centrifugal action, the particle will get segregated by its centrifugal action, and the oil will basically filter out and it will get drained on this particular lower object, the lower tank. So I'll just make a brief case study of the sewage water treatment plant. That is the most important nowadays study is being made, and the government of India is giving a lot of focus on this sewage treatment plant and their implementation in the apartments, in the commercial blocks, because to save our live water bodies from being polluted because most of the cities are now charged with this particular, the government are charged with this allegation that they are allowing the private contractors, and a lot of private contractors are not adhering to the government norms, and they just like that, they release the raw sewage outlet to the live water bodies, which is very dangerous, and our future generation will suffer for that. And this is the right time when we should cater our research on something to this segment, which will give some value in terms of humanity, or protecting the humanity in future. So the contribution of the SolidWorks flow simulation in addressing this STP. So first let us understand how the STP works basically. So the STP process, the sewage treatment process, works in the aeration. The main concept is here lying in the aeration tank. Actually, first the raw water being collected, and once the raw water being collected, in the raw water there are a huge concentration of methane and carbon monoxide are there, which is very much injurious to the water as well as our health. Now, what in this aeration tank happens is that in the aeration tank they make the oxygenation. So they add the oxygen, and they make the oxygen rich inside the aeration, and the moment upon you put the oxygen, this CH4 reacts with oxygen and it forms CO2 gas is taken off, and also H2O is being formed, and like that, this oxygen helps in the proper oxygenation, and also this poisonous smoke will come, poisonous gases will get turned to the normal gaseous mode. And then there is a classified settler, and in this settler they take the little purified form of this water, and then different by they take the sludge to the different level and making bacterial treatment for the sludge. In that segment we don't cater. Our main concept to work in this aeration tank, because we closely work in Bangalore, lot of companies, because in Bangalore it's the major companies of STP you will find in Bangalore and Pune. So big STP companies like Ecotech, like Green Waterhouse, there are so many, STP companies, I forgot the names, and big STP companies are there. So our main focus being a CFD, this aeration, because why the main thing is not our focus is just because the fluid dynamics is there, our focus is there. It's not like that. The challenge is there in the aeration tank, because all the STP manufacturer, they are facing a challenge is most of the STP manufacturers are not very well equipped with this CFD methodology. And what is the main problem? So in STP, there are basically two different type of STP which are mostly popular in the middle scale segment. Okay, that is EAS segment. EAS, this particular term is this is the most popular segment. This is named as extended aeration activated sludge. Now this extended aeration activated sludge is one method, and another similar method is there, MBBR. Please remember this MBBR. These are the mostly popular methodologies followed in Bangalore and Pune across all mid-size, big-size apartments, because the other method are very much expensive. In US and all, they follow some other methodologies, but then they're pretty expensive. But this works out to be very good and potential for Indian, and the maintenance cost is very low. So this MBBR stands for moving bed biofilm reactor. Now in these two technology, the main challenge these people are facing is the oxygenation does not happen uniformly, because what these people do, these people just put a mixer, and in that mixer, a mixer blade in the huge chamber, and in the huge chamber a simple mixer blade, if they put, they don't even know that whether the oxygen they are pouring in, the oxygen in such a huge chamber with this existing flow rate, how far proportionately or uniformly or homogeneously this oxygen get mixed to this this activated chambers. Without the knowledge, they take out the water for the further treatment. Without the oxygen being mixed properly, they take out the water, and the water stinks with odor, and it looks brownish, and it is actually not advised to leave to the live water bodies in this form also, because the water has not been oxygenated proper, and the major challenges is at this particular. Apart from this, also some small challenges are there, because in the STP system the chambers with wastewater contains lot of immiscible small particles as dust, sand grains and mud particles. Okay, and these sand grains and mud particles, they cause erosion in the pump, because the pump are continuously moving, so many mud particles and all they are pumping out, and the pumps and the other hydraulic equipment, whatever they have, valves and other things, they all will get eroded over time because of this mud particle. So at least we can have an assumption that how much amount of erosion can happen. So our Lagrangian particle tracking solver, okay, it can really simulate well that how much amount of erosion can happen in terms of millimeter per year basis. Okay, if this particular sand grains of this particular micron size are being mixed with this particular flow condition. So that's the one of the benefit in our solver, SolidWorks flow simulation solver we have, and we have used it extensively in our STP segment. And kindly see here, this is a tank. Let's say you have constituted a very big tank and you have only one mixer. This is an example case. This is because as per the agreement, we have some end user agreement. We cannot break that protocol. We cannot show anyone's model here. Hence, we have to. I just made a example model to showcase in front of you what is the exact challenge, so that you can understand. So here what is happening is that they have a mixer. Somehow they have put with the curly blades and some blade arrangement, and they are putting the oxygen bubbles inlet just to make the oxygen to be get mixed. And this chamber is full of water. Okay. Now this chamber is full of water, and this is an atmospheric condition. This is to some other gases and all, CO2 and all. After being trimmed from the methane, the CO2 and all will come out from this chamber. Something in that way. Now they don't know whether these curly blades are enough to generate the particular amount of mixing dynamics inside the water particle, so that the oxygen will be really mixed properly across the chamber. Here, compared to the chamber, I have considered the mixer is pretty big, but they are taking sometimes the chamber will be very big, but the mixer probably, first of all, the mixing location of the mixer somewhere put here. Okay, sometimes the mixer will be put some other end. So there's no, and even if it will be, the mixer will be put at a center, this only one small mixer is not sufficient to uniformly mix the whole sewage water, because it depends sometimes. You may be thinking that what is the problem? We are mixing, we are stirring the sugar inside the tea and it get mixed with a simple action. But here it is not, because depends on the apartment. Let's say some 500 flats are there in an apartment on a particular summer vacation. Okay, the sewage load will be less in terms of gallons per minute, if you see, or in terms of liters per minute. The sewage load will be pretty less. But in the school running season and in after July and this peak season, the loads will be different. So what will happen is that as the load will get changed, and then from morning, let's say from morning time wise also it varies, because we have some observations and literature studied in that field. We've seen those literatures. In the morning 6 o'clock to 9 o'clock, the load of the sewage load will be very heavy. Okay, and that time the input and the output of this particular conditioned water, okay, treated water, has to be same to maintain the uniform content of water inside the chamber. To make that, if in a high loading condition, your mixer should support that homogenization of oxygen. In a low loading condition, maybe your mixer is well capable of making the homogenized mixture, but then when the load will be double and tripled during the morning hours, is your mixer doing the same job efficiently? That's a big question, because if it is not, then our lake bodies and all, where you are finally disposing the polluted or treated water, it is not treated, it is yet to be treated, and some measuring part has to be there. So what we have done, we just considered a flow rate of the oxygen like this and the diameter with this tank of this. So we made our case study and we shown and we proved. Initially we had to struggle a lot with this because people are not ready to understand, but then eventually they respected the methodology and they understood that yes, if in our solver the way we mixation happens and how they understand that a whirlpool, a vortex is being created at this place, and completely the mixation is not happening at this particular region because the low pressure is being constituted here because of this mixture geometry and the container geometry. Now that means, see here, almost 40% of the region of this particular, you can see here, if you take an image, this particular region, blue color, if you shade it, it constitutes 40% of the the container of the chamber is not being properly mixed. Okay, because of this particular low pressure region, it is not mixing properly and the oxygenation is not happening correctly. Okay, so these are the things which you can do by means of using our solid ox flow simulation. Has very robust modeling method. In any number of tank and any type of model, it can generate very easily because of its very powerful 3-dimensional modeling solver. So here what we did is we simulated the transient mixing process by means of Lagrangian bubble flow solver, which is a part of the Lagrangian particle solver, and we seen that how the homogeneity get established across the tank and how much time it will take for your geometry of the impellers or your geometry of the tank and your construction of the tank, and which section of the tank this impeller are mounted. So kindly see, and I hope Dr. Rath, last time you kindly confirm me if the things are visible, because the oxygenation
yes,
is,
it is visible.
yeah. Now you see the oxygenation is happening from this particular part. It is getting poured in, and inside water is there. And please see very carefully that how the mixation happen, how much time, whether the oxygen bubbles are capable enough to being transported each and every corner of the container in an equal concentration manner. Okay, because this oxygenation is a very important step in sewage treatment plant, and if this oxygenation is not done correctly, you cannot remove the methane, you cannot remove the carbon monoxide, which will pollute the environment as well as it will pollute the live water lake body. So this is a very important. So now basing on this solver, you can able to really see how much the oxygen concentration is happening uniformly on this particular tank, and basing on that you can take a decision whether one impeller, let's say you have a restriction of the impeller size, your manufacturers doesn't supply more than this size, then kindly install 2 impeller, or you can make it smaller impeller in mounted in 2 different corner of the the tank, or 2 different elevation of the tank also sometimes, because if it is a very big tank with a very high level of elevation, sometimes putting the impeller only at the bottom may not help you. You may need to make the impeller in a hanging position, so that the mixer impeller should be somewhere in the middle of the elevation, complete elevation of the water. So it depends, because unless and until you have a complete 3-dimensional solution process, you really cannot optimize this process. Hence, our solver, solid ox flow simulation solver, has really been instrumental in this particular aspect in the sewage treatment plant address, and the number of impeller you need to mount at which location, at which elevation of your big container, at which locations at different places, what should be the geometry of the impeller to make the mixing process more healthy, more homogeneously, so that the methane and the carbon monoxide can be completely taken away from the raw water. So this is what our solid ox solver. And the part which I already told, because of the muddy particles, okay, you can see our solver can take the exactly how the particle will continuously bombard against the walls of different, because this mud particle will bombard at different section of different hydraulic assemblies, and you can see the display. They will display the result in terms of millimeter per year. The erosion rate has been given. The font is very small, hence I have written here clearly the erosion rate happening at which corner and which are the places you can expect a maximum erosion because of your flow dynamics inside your given geometry. So basing on this particular thing, you can really calculate well whether, see, we can't stop the erosion, but then we can minimize the erosion by using computational fluid dynamics, and especially our solid ox flow simulation solver, the Lagrangian particle solver, can really address it well, because it can tell you exactly which portion of your given geometry under existing flow condition will undergo maximum corrosion or will prone to undergo maximum corrosion. By changing a little bit on the design, you may reduce that particular erosion concentration on a particular pocket, and you can distribute it well, so that overall erosion you can reduce on a particular segment, so that your component damage can be stopped and prevented. So that is what the solid ox flow simulation solver is made for. And with this, I would like to conclude my presentation on this whole thing. I thought yeah, a lot of things could have been presented more, I agree, but always there is a next time. And because of all this time constraint of because of this COVID, because of all this other business related issues, I could not really make it very extensively bigger, but still I tried my best to present you forward, like, whatever best possible my understanding and my application of the software on this particular tool, to the best possible way. So thank you for all your attention. Thank you, Dr. Rath and Dr. Mohabbat, for
Yeah.
your invitation to this particular. I felt very happy in presenting here. And excuse me for certain handwritten notes what I made to make it faster the interface part, because I did not get chance in the equation editor. So thank you
No,
anyway.
it's fine. It's really a wonderful lecture session where you have very nicely explained actually the droplet dynamics and such a complex transport process. You have explained in such a lucid manner. Any layman can understand. I hope our participants might have enjoyed a lot. So I'd like to request our participant, if you want to have a small interaction, Dr. Anjan Sarkar will be glad to answer your queries. Please.
Dr. Anjan, I have joined. Good morning.
Good morning, sir. How
Swarup
are you?
Mahabat, everything fine. I just heard your lecture. It is really nice. Of course, I couldn't attend full lecture, but the complex phenomena you have addressed in a so simplistic way, and the handwritten part is so good. Means how you are involved in your presentation. That is a reflection of that. So I think participants must have enjoyed your presentation, and really I remembered, 15 years back, this interface phenomena to track the thing. It was so tough, and I, though validated, but it was denied by the reviewer that no, this paper you have referring, that is also not correct. So that is such such a
Oh, I
tough
see.
thing. That interface tracking, and you have really in a very elucidated manner presented. So thanks, Anjan, accepting our invitation, and thanks, Prasanjit, to have you to in this particular platform. A fantastic
It's
presentation. Thank
okay.
you, Anjan. Thank you. Now,
Thank you, sir.
participants, please have your queries, and this is a right opportunity for all of you to
Yeah.
come across Dr. Anjan Sarkar, who is very normally volunteers to present, clarify all your doubts, and also ready for futuristic collaborations and like that. So please come forward to have your queries. Please.
Yes. Participants, any query you can discuss. Yes, Professor Lakveer. Yeah,
Yeah.
please.
Okay.
Yes.
Yes, so thanks a lot for sharing such a good presentation. We really enjoyed it. Okay, in the last part of the slides, as you have shown the bubbles, bubble dynamics we have discussed, was that based on one-way coupling or two-way coupling?
It is, sir, one-way coupling, because the droplet, the bubble dynamics in the Lagrangian solver which we solved, it is a solid-works flow simulation we have used, and that is a one-way coupling, which
Okay,
I
so
mentioned it.
okay, so is there any possibility of two-way coupling, or
in future version you may expect, but honestly, our all users who are using it, they are happy with one way, because see, when we are taking the particles in a very much on the micron level, it really doesn't matter the second way coupling, unless and until your particle size becomes significantly bigger and more than, let's say, somewhere 100 microns plus, or 500 microns, 200 microns plus, it uh, Unless and until it becomes 200 microns or 100 microns plus, the other coupling, the particle to fluid coupling is, I mean, we did not feel it in any of our users who are using these things. They are happy with this one-way coupling, because this one-way is important even for a 5 micron, 10 microns particles. It is very important, because you see our Kent purifier, which we are using in our home, is the most popular purifier. If you see, we talk to the Kent purifier also. We are closely working in a research project, which I cannot reveal at this moment. But you have seen, if you see on the maintenance time of the Kent purifier, after the complete purification process also, you open the tank, which is the 8-liter tank fitted in, and you will see micron level particle settlement are still there on the beneath. Okay, if you open it after 1 year and 2 years, so this micron level particle, it get even slipped over the solid filter membranes. All porous membrane it exceeds, and it can break all the impedances offered by the porous membrane. It can come. So because of the flow dynamics and this, how these micron level particles are really getting settled all over the gadgets of whatever you are using, whether you are using Kent or you are using a sewage treatment plant, or you are using a pump which is taking mud particles. So I mean, the one-way coupling so far given us very good customers, I would say directly, because we are making business out of that. Two-way coupling, maybe it's an additional hand for researcher, but I cannot say immediately how far the corporate bodies will get benefited of the two-way coupling, unless and until some potential application will be really there to use the second coupling method.
Okay, thanks very much, sir.
Hello, Dr. Sarkar. It was a nice presentation. I have one query related to, because I am working on solar thermal applications. In solar thermal applications, mostly forced convection boiling is mostly predominant in the absorber or the receiver tubes, and it's a very complicated thing where the heat flux along the length of the pipe is not constant, and the pressure drop will be there also along the length of the pipe. So there is continuous change of phase as well as change of pressure. So how to deal with these type of problems regarding this forced convection boiling in absorber tubes with net heat flux? It's not, the heat flux is not constant all over the length of the pipe.
No, I feel you can, sir. I feel so far I have, because this particular phenomena, especially this level set method, I have used it for you can see already. You've seen for evaporation, I have used it already. And I have not used it for a complete length of pipe, but then on a length of wall, I have used it. And yes, the heat transfer and the accumulation of the droplet, it is with a changing heat transfer coefficient. I addressed it for a very smaller length, I would say. May not be for a very big length, because I initially, in the beginning of my lecture, if you were there, I did complete this development for sake of addressing the droplet behavior and the heat transfer dynamics happening on a plasma tube, which is a quartz tube. And the tube used to get cracked in our spectrometers because of this droplet accumulation. Suddenly the heat transfer characteristics get changed, and because of a sudden high heating temperature, 9,000 to 11,000 Kelvin, if this droplet will get accumulate on the and small droplet will make finally bigger island. Okay, that is another part we have to address. And this bigger island, two-way it is detrimental. Is that bigger island, because of its sudden jump in the temperature at the glass surface, it used to crack the glass, quartz glass of the plasma torch, and this bigger island used to fall on the exact plasma where the flame is there on the flame, and it used to extinguish the flame. That is another danger part. So two-way it was detrimental for us. So I measured it for few millimeters, I mean around 10 to 20 millimeters, and I got a variation in the heat flux characteristics. Well, but if on a few meters, it may need I feel it's a scale up of the computation ability, but the mechanism should be same only. Because here the complete evaporation have been modeled, and the adhesion, and you've seen in the adherence, the plastic fluid part which I explained, how the droplet is sticking to the wall, and the adherence of the plant, and the time with which it trickles down finally. So this complete heat transfer you can address on the wall to fluid part. I believe just you have to extend it to the computational ability part, since you know this phase change solver consumes a lot of computational effort, because I solved all this problem in 128. I mean, especially these Eulerian cells. I'm talking of mainly level set method. I solved it in 128 GB RAM with a 32-bit processor. You know, and it taken 56 hours of time to simulate those things what you have seen. So you have to scale up the processing ability, and then you know, you can able to solve with this model.
Yes, thank you very much. But how to deal with this net? I mean, different heat flux, various heat flux in the length of the pipe. So I told you the heat flux is not constant all over the length of the pipe. It varies
See,
from inlet to outlet.
absolutely. And you had seen, I had, can you see my screen? If I go back here, exactly the thing which I defined here. If you see this particular slide, sorry. See the heat flux, you know, automatically you will get it different, because kindly see this, because the temp, so here the moment it will be near boundary, this node will act like a ghost node. Okay, and what will happen on the wall, if a wall will be there on this particular location, and your droplet will get stick over this impinge. Let's say it got impinged over this part, right? So here you have it, the property of the droplet and the property of the wall you have already mentioned. Okay, so what will happen, the complete temperature, the temperature gradient what you are calculating from here, which is constituting this heat, right? This is coming from the droplet evaporation, and from this constituting this heat eventually you have to make another equation of the heat getting transferred, finally conducted back to the wall. So that equation you have to just supply there, so that the energy balance at the boundary will obtain. So this Q will be equal to, you have to write one another line is about that, you know, K into the thermal conductivity of the wall and into the temperature gradient it will constitute on the wall side. And then this balancing you have to establish, because I did the same thing, and on the plasma tube I got a variable heat flux only over the 10 or 20 millimeter length, because I will just exactly tell you how the plasma torch was. It was just like, see, this particular portion, the coil was there, only 2-3 turn. Okay, so the flame used to happen here. Okay, but the nebulizer, all the atomized small droplets used to get enter from here. Okay, now what will happen, this droplet will get stick over here, here, and also here. So like this, over a span, this droplet used to get stick. And here the droplet will be highly evaporative, because of it is coming under the flame range. Okay, and here the droplet will be less evaporative. So always when I used to take the accumulation and the heat transfer coefficient, always this heat transfer coefficient will be varying, you know, from higher to lower only, you know, with this few millimeter length. I hope I could able to clear, I mean, that point. What do you
Okay, sir. Okay, thank you.
Thank you.
Anybody is having any other query? Yeah, I think there is no further query. So I'd like to thank Dr. Anjan for sparing his out of his busy schedule, sparing some time with us, and giving this lecture on such a complex process of phase change involving droplet dynamics. So hope to have a strong collaboration with his company in our near future. And I'd like to request our participants also, please be in touch with him for any future collaborative work or any help if you need in future.
Yeah, sure. I'll
Thank
be
you
very
very
happy. Yes. Thank you, sir. Thank you, Dr.
Thank you, Anjan. Thank you,
very much.
Anjan. It's a very nice talk you have given and accepted our invitation. That is also another great part of you.
My pleasure, sir. My pleasure, sir. I mean, and nice to see both of you after a very long time, because in this COVID, seriously, I mean, we probably lost touch.
Yeah.
All this.
Hope to have you in the campus sometime. Let's the
Yes,
normalcy
definitely.
resumes. Yeah.
Right. We will definitely catch up sometime. And thanks to all our participants also, who waited and observed, seen the presentation.
Yeah.
Thank you very much.
I hope I have ended the session at the right time, because Dr. Sarkar is having another meeting, which is starting, I think, by 11:30.
Yeah, we have a training session. Yeah, we have a
Yeah.
training session of of some of our updates, of software updates.
Yeah,
So
yeah,
which
yeah.
will start from 11:45. So
Okay.
hence I got to complete it by 11:30. So in
Yes,
case
yes.
question answer round get drifted till another 15
Yeah,
minutes,
yeah,
I
yeah,
kept
yeah,
that
right,
factor of safety. So it really get ended well.
yeah. Very nice.
Thank you,
Yeah,
sir.
thank you very
And
much.
thank you, Dr. Rath. Thank you all, and have a great day. Please take your vaccines in the right time, COVID vaccine.
Yes, I've
And
already taken both
we
the
have to
doses of
make
my
our
vaccine.
country COVID free. That is more important.
Yes, definitely.
Okay. Thank you.
Okay,
Thank you all.
okay. You can
Bye.
make a leave now.
Bye.
Yes, thank you. He has given one of his lecture, so where I have introduced him regarding his research area. He's basically interested in phase change problem. Basic research work is on phase change problem involving microstructural evolution. So today we'll be delivering lecture in that respect on his core research area, phase change associated with microstructure evolution in material processing. So I'd like to request Dr. Anirban to share his slides and give his start his lecture. Dr. Anirban, please.
Thank you, Dr. Rath. Am I audible?
Yes, it is audible. I have started recording. You have no problem, right?
Yes.
Yeah.
No problem.
Okay. Thank you very much.
So let me share my screen.
Yes.
So I hope all of you can see my screen. Dr. Rath, can you
Yes,
come?
it is.
Yes.
Yes. It is visible. Participants, everybody can see this slide.
Yes, sir.
Okay. Very nice.
Okay.
Yes.
So a very good morning to all of you, and I hope all of you are all right in this difficult pandemic situation. Anyway, we will directly jump into the topic of today's discussion, which is on CFD-based modeling of microscale solidification, and then how it is extended for predicting microstructure evolution. Okay. So before going into today's discussion, just I would like to state what is the importance of this area. So many of you are already working in CFD related areas, and you know that CFD is used pretty much in every aspect of say engineering and sciences. So for example, in fluid mechanics problems, then say in heat transfer problems, then in industries, various types of industries, for example, wherever there is phase change involved, then heat like air conditioning, refrigeration types of problems, any aerodynamics problem. So all these areas are quite important, and and CFD is actually a very useful tool to predict different aspects of say different designs in these areas. So one of the important areas where CFD is widely used is manufacturing processes. Okay, if we go more specifically into depth, many of the manufacturing processes involve phase change, such as solidification or melting, mainly solidification. So, for example, casting, welding, or even advanced processes like rapid solidification or 3D printing. So all these processes involve a phase change from liquid to solid. And in these areas, if you want to improve the properties of the material, The option is either to do a lot of experiments and go with trial and error method to improve the properties, or we can predict something based on analytical solution, but at a very basic level, or the favorable option nowadays is to develop a CFD-based model for predicting the effect of various design and operating parameters on the on the basic structure that is obtained after solidification. We will discuss about the basics of solidification in more depth in a few slides. But basically, what we want to do is we want to predict how will the solidification proceed depending on the different operating and design parameters, and how the final properties ultimately will evolve, so that we can achieve better and better properties. Okay. So coming to the outline of the talk, so we'll start with some basics of solidification, because many of you may not be from the area of solidification. Just a couple of slides are there on basics of alloy solidification. When we call alloy solidification, it means that there are at least two components, like for example, aluminum and copper. So aluminum copper alloy, or aluminum and silicon, aluminum silicon alloy, or steel, which is an alloy of iron and carbon. There may be other minor elements, but two major elements are there. If two major elements are there, it is called binary alloy. If more than two are there, say 3 elements are there, it is called ternary alloy, and so on. If it's a single component, single constituent, then we call it as a pure metal or pure material. And before going into the basics, I will also, what happened? Action is still there. Okay, before going into the basics, I will also like to emphasize a little bit more on the importance of solidification modeling. Okay, with some one or two examples from industry. One or two examples which I am familiar with because I worked in those areas previously. And then we will go into modeling of growth of a single dendrite. So dendrites are basic, say, particles. When solidification proceeds, we will see how solidification proceeds. So it proceeds with the formation of large number of dendrites. So how this occurs will be explained in a bit. But if we want to study solidification, we want to know how a single dendrite grows and how to model that growth of the single dendrite. So we will see a popular CFD-based model for single dendrite growth for alloys. And then a few examples of parametric studies for dendrite growth. And here I would actually go a little bit slowly on the modeling part and the mathematical modeling part of the dendritic solidification, because this is the core portion which needs to be understood to develop a CFD model for alloy solidification. Okay. Then in the final part of the discussion, we will go into the extension of the single dendrite model for microstructure evolution. Okay, when we say microstructure evolution, we will see later that it comprises of large number of dendrites, and certain extra parameters need to be incorporated in the model to accurately predict the microstructure. Okay. These are still evolving fields, so these are very complex model involving heat transfer, mass transfer, fluid flow, various types of fluid flow, like due to natural convection, and electromagnetic convections are sometimes used to induce forced convection within the domain. Okay. And then there are sometimes shrinkage driven convection also. So all these are coupled together. Then phase change processes, there are sometimes evolution of gas bubbles are also there, which leads to defect formation. It's a very complicated process. So still models are being developed in this area at a rapid pace, and a lot of things are still to be explored, particularly from this microstructure point of view. And then we will just quickly go towards the end. We'll just quickly go through a few results from the model, from our research, to show the different capabilities which are possible using CFD-based model. Remember that there are other types of models also for prediction of solidification. Analytical models are there, and then there are other empirical relations and there are some other ad hoc type of models which do not use CFD, but some kind of mathematical formulation and calibration with experimental results. But our focus will be on CFD model, and we will see a particular type of CFD model which is known as enthalpy based modeling. And finally, I will show you a couple of slides on one of the applications which can be very important in future, which is in 3D printing. So which is laser based melting and solidification of powder substances. But these are just a preliminary kind of results. So the main part of the talk will be focused on the modeling of the single dendrite, and some part then towards the end on the microstructure evolution. So let us start with what is the importance of solidification modeling. Okay. Please feel free to ask questions in between also if you have some queries. So let us take a particular example. Okay, there are lots of application areas of solidification, as I was saying, casting, welding, then additive manufacturing. Any process which involves solidification is important in manufacturing processes, for example. But to give you a concrete example, let us consider the case of turbines or turbine blades in particular. Okay. So those of you who are working in the area of say thermal area will know that if we want to increase the efficiency of a gas turbine or a jet engine, keeping everything else constant, one way to increase the efficiency is to increase the maximum temperature of the cycle. So gas turbines or jet engines operate on Brayton cycle, based on Brayton cycle. And we want to increase the maximum temperature of the Brayton cycle to increase the efficiency of the engine. Okay. So the maximum temperature in the cycle is obtained just after the combustion chamber and just before the entry to the first stage of turbine. Okay. So the first stage turbine blades face very high temperature combustion products. Okay. And that is the limiting factor which limits the maximum temperature in the cycle. So these material properties of the turbine blades are the limiting factor which governs the maximum temperature of the cycle and ultimately the efficiency of the cycle. So if we can somehow improve the maximum temperature which can be sustained by the blades, we can increase the efficiency, and a small increase in efficiency can lead to dramatic increase in the cost savings if you consider jet engines. So because fuel is one of the most costliest say component of aviation if you think about it. So anyway, so there are different ways to improve the maximum temperature that can be sustained by turbine blade. One way is to have some cooling mechanism. For example, here you may be able to see some perforations. So basically these blades like these turbine blades are hollow in nature, and some air is taken out from the compressor and is passed through the turbine blades for cooling of the turbine blades. But there are other ways to improve the maximum temperature sustain, and that is through the improvement of the material itself. Okay. Now there are two ways to improve the material. One is that if you consider a same alloy, for example, if I consider the turbine blade is made of nickel based alloy, okay. So I can improve the structure of the material, keeping the alloy same. I can improve the structure. So structure here you cannot see any structure of the material. But if you go at the microscopic level, you will be able to see that there is a particular structure of the material which we call as grain structure. Okay, it depends on how the solidification had occurred when we had casted the blades. So these blades are casted using investment casting in a process which is known as continuous casting process. Okay. Based on our requirement, we want to improve the microstructure or grain structure of this blades so that it can sustain more amount of temperature, means higher temperature. Okay. So how it is done? Let us take a look at an example. So initially, when turbine blades were developed a few decades back, they used to have a microstructure like this. So if I zoom in on it, like if you see using a microscope, you will see that there are a large number of particles which are present, which are shown here by different grayscale. And each of these particles is actually called a grain, as we will see later. So there were a large number of grains in the entire blade. And remember that these blades actually undergo a lot of centrifugal stress because they are rotating at a very high speed, and they are facing large like high temperature fluid. So at high temperature, their resistance to the stress decreases. Okay. And the blade elongates. So over long time, under constant load, it elongates, which is known as creep. And as a result, there may be a case when the blades collide with the casing, leading to catastrophic failure. So that actually limits the maximum temperature that can be sustained by the blade, not the melting temperature. So it is much lower than the melting temperature. Okay. So initial blades could only sustain up to 500-600 degrees centigrade. Because of this presence of grain boundaries, blades used to elongate in the longitudinal direction along the axis and at high temperature, and then they had to be limited to lower temperature. So then through clever change in the solidification process using something which is known as directional solidification, the grains could be aligned along the longitudinal direction. Okay, so there is a process which is known as directional solidification or Bridgman solidification, and in this process we can obtain grains which are elongated along the direction of the blades. So what happens is that if you take any cross section, along that cross section in the longitudinal direction, there are no grain boundaries. Okay, the grain boundaries are only along the transverse direction. So all the grains are very long grains. So that because there are no grain boundaries along the longitudinal direction, it leads to much higher creep resistance along the longitudinal direction. And remember that the stress is mainly along the longitudinal direction, along the length of the blade, the centrifugal stress. So by using this technique or by optimizing the microstructure, you can say, we could achieve much higher temperature in the turbine blades. Nowadays, even better type of systems or even better types of blades are used, where the grain boundaries are totally eliminated. Again, I will not go into the details how it is done, but it is also similar to directional solidification. But what happens is there is a downward region, and although multiple grains are present, only one of the grain passes through a narrow constriction and then fills up the entire mold of the investment casting process. So there are no grain boundaries and it has very high creep resistance. So aviation blades currently have single crystals, so that they can withstand very high temperature up to 1200-1300 degrees centigrade. Steam turbine blades, which are much larger in size and encounters lesser temperature, generally around 600 degrees centigrade. So steam turbine blades means for Rankine cycle, for power plants. In those type of blades, still this type of longitudinal grain structure is used, because it is very costly to make very large blades with the single crystals, defect-free single crystals. So, so my point here is that we can improve the properties even for a same alloy composition just by designing new type of microstructure. And here, instead of doing it by trial and error, or even if we do it by trial and error, we can do the trial and error using simulation based on CFD instead of costly experiments, because these experiments are very costly to be performed. So if we use, if we can develop a CFD model to predict how these grains will grow based on different operating and like boundary conditions, what will be the effect of temperature and say insulation, and what is the effect of the flow pattern inside. So if based on these things, if we can predict the microstructure, we can say for which conditions we will obtain better microstructure and better properties. So this is one area where a lot of research is going on. If you go to any aerospace company like GE or Rolls-Royce, which work in the design of the engines, so you will see there are teams which work on CFD modeling of this type of microstructures of turbine blades. So one example is that to improve properties for the same material. There is another way to improve the properties, which is to actually develop new materials themselves. Okay. So not to use the same material, but if we can develop a better material, it will be better. So nowadays, so previously, initially, some nickel-based alloys were used for the use for turbine blades, but nowadays, for last few decades, innovative type of material which is known as super alloy is used. So what is this super alloy? It consists of a large number of so around 8 to 10 different elements which are present, and typically one base material like nickel, which is around 50%, and all the other elements are have 4 to 5% weightage. So the importance comes here from the peculiar structure that can be obtained after heat treatment for these materials at a very small length scale. You can see that this length bar is 5 micron. It means that these structures that you are seeing are of the nanometer level. And because of this structure, it leads to very large creep resistance because they resist something called dislocation moment. And as a result, they resist creep in the longitudinal direction. So these structures are present within the microstructure, within the grain structure. So each grain internally will have again smaller nanoscale structure like this. So this formation of these nanoscale structures, okay, these are known as gamma prime structures. Not very relevant for us in this CFD course, but it's still good to know. So these structures actually depend on the diffusion during the heat treatment process, and that diffusion depends on the initial microstructure that is developed during solidification. So in a way, solidification is still the major player here in determining the final the nanoscale structure after heat treatment. So that's why it becomes very important to again study the microstructure that is formed after solidification of superalloys or other types of material, and then we can say for which composition we can have better microstructure so that we can get better properties after heat treatment. So this is another area where we can, like CFD can help a lot. Okay, again, a lot of research is going on in this. Each company have their own say own type of superalloys, and they guard the composition very like aggressively, so that other companies cannot, other organizations cannot know what is the exact composition. Okay. So, apart from this, in general, there are many other areas. For example, if we take the example of continuous casting, so steel is actually steel sheets are manufactured using a process which is known as continuous casting. So where the molten metal is poured through some rollers, and it actually passes over the rollers and goes out as a slab, and initially starts with molten, like it starts in a molten form, but gradually because of heat transfer, it solidifies into a steel sheet, and then it undergoes various heat treatment and other processes like galvanization. But the properties of the steel sheet again depends on the solidification process, this solid that is formed, and how fast the cooling is happening. So which is imposed based on a imposed cooling rate. Then what is the width of the strip? What is the convection pattern that develops in the inside liquid region? These things govern the final properties of the steel. Okay, and once the final microstructure is developed, it does not matter how many heat treatments you do. The effect of solidification will still remain. So any major defect that forms during solidification, say there is a porosity that has formed, it will be very difficult to eliminate or impossible to eliminate that type of defect, even if you do other like extra processing after casting. So the only way will be to just machine off that part or just reject that part if there are too many defects. So again, this is another area where also CFD plays a very important role. There are hundreds of other areas, but like CFD for solidification, these are some areas, particularly where the microstructure plays an important role. Obviously, solidification is also encountered in phase change materials for energy storage and many other areas. But in those cases, the microstructure is not prominent, use of microstructure. But these are the areas where the microstructure plays a very important role. And that's why we need to study how to develop CFD models to predict microstructures. Okay. So what we will do is, with this small introduction on the importance of microstructure modeling using CFD, I will just go through some very basic stuff. Okay, many of you will know all these things. It can be like a recap of the basics, but all of us needs to be on the same page, because without knowing these basics, there is no point in going through the modeling. So because we will not understand the equations in those cases. So the specific equations that are required for solidification. So let us go through some basics, 2-3 slides on the basics of solidification. What is that sound that comes frequently? That is of people joining, is it? Like some pink type of sound is coming. Okay. So again, this is very, very basic. So for many of you, this may be very familiar, but still it is good to know these things, because based on this, we will have to think about our model. Okay. So if we will focus on alloys, particularly binary alloys, because that is the most common type of alloy that we encounter. What is a binary alloy? It consists of two constituents. For example, aluminium copper alloy, aluminium silicon alloy, iron carbon alloy. So like this copper zinc alloy. So when there are two major constituents, we call it a binary alloy. Okay. So the solidification process of binary alloy is slightly different from the solidification process for a pure material. Okay. We will go to the depth in the next slide, but let us see how things look like at a microscopic and lower length scales. Okay. So if we consider a pure material at the microscopic level, it consists of this type of structure as shown here. So these are known as grains. Okay. I will explain after a couple of slides how the grains evolve. But what happens is that the solidification does not occur uniformly in the domain. Like many particles start forming in the liquid at different locations, and each of the particles, solid particles basically, start growing. Ultimately, they come in contact with each other, and then there is no space for further growing, and the solidification is complete. So each of the particles have a certain atomic arrangement. So if we zoom in further using a say electron microscope, transmission electron microscope, we will be able to see the atomic structure, and the atomic structure for one particle may be aligned in the say 90-degree direction. For the next particle, it may be in the 77-degree direction. So all these are randomly oriented based on how they initially started. So when they meet together, there is a mismatch between these grains, which are known as grain boundaries. Okay. So these grain boundaries play a prominent role in the properties of ultimately the properties of the material. The grains and grain size and the grain boundaries play an important role in the property of the material. So somehow if we can predict what will be the grain size, grain morphology, and the grain boundaries, and say how they are affected by the thermal evolution and flow pattern within the domain, it will be very helpful for us to improve the property of the material. So same thing, if you look for an alloy at the microscopic level, again you will see grains which are similar to the grains of the pure material. But if we zoom in using a transmission electron microscope, you will see that because now there are two types of elements, there can be two types of alloys. So let us consider a case, aluminium copper. Okay, see if aluminium is 90% and copper is 10%, so you will see that most of the atoms are of aluminium and few of the atoms have been replaced by copper atoms. Similarly, if copper is 90% and aluminium is 10%, we'll see that most of the atoms are copper atoms and few copper atoms have been replaced by aluminium atoms. Okay, so these are known as solid solution, or what we commonly call as alloys. Okay, they are intermittently mixed together. They are not intermittently. They are say intrinsically mixed together at the atomic level itself. Okay, so at the grain level, we do not see any distinction. But what will happen at the grain level is that at some location the percentage of copper will be higher. At some location the percentage of copper will be lower. So there will be a variation of concentration of the elements. Okay, so the element which is in lesser amount is known as solute, and with the element which is in higher amount is known as solvent. So when we define the equations, which we will do later, we define in terms of the solute concentration. So for example, if we have a 90% aluminum, 10% copper alloy, we'll say that solute concentration is 10%. And it may not be constant over the entire domain. So at one point it may be 9% and another point it may be 11%. And this is one important important feature of alloys which needs to be accounted for in the CFD model. So how the variation of concentration occurs, that needs to be predicted. And it is also important not only from the point of view of properties, because the properties will depend on the concentration variation, but also the concentration itself directly influences the solidification temperature and the solidification process. So when we develop a CFD model, we need to know how the solidification gets influenced by the concentration. And so the equations are actually coupled equations, as we will see later. So this type of so what we need to predict basically is the grain structure which is formed, and also the concentration variation. Obviously temperature variation also based on the boundary conditions, and the operating or system conditions, design parameters which are provided to us. So I hope up to this point it's very clear. We are going very slowly because this part is crucial for developing the equations. So here I am showing again very familiar to many of us, which this is a typical binary alloy phase diagram. A phase diagram is a diagram which shows us which phases are present at, say, at a certain temperature and concentration. So for binary alloys, actually you can fix the state of an alloy by fixing any three parameters. So for example, if we fix temperature, concentration, and pressure, we can fix the state of the material, and we can find out all the other properties. For a pure material, you know that we can fix the state by using two independent properties, like say temperature and pressure. So for binary alloy, where there are two components, we need three parameters, three independent parameters. So these are generally taken as temperature and concentration, and it is assumed that pressure is equal to 1 atmospheric pressure. So based on this and based on experimental data, diagrams are developed which are known as phase diagrams, which shows us for what temperature there will be liquid, for what temperature there will be solid. For example, we see that at high temperature we have liquid here. Okay? And if we go down, so if we have some concentration, say 10% concentration, I cannot draw a line here, but you have to imagine with me here that there is a vertical line at 10% concentration. And so if we start cooling from say 1300 degrees centigrade, initially there will be liquid until we reach this blue line. Okay. And once we reach this blue line, what will happen is that some amount of solid will start forming. And this solid, for this particular case, this solid is alpha aluminum. Okay, although it is shown as aluminum, this will be alpha aluminum. Alpha aluminum is an alloy where aluminum has a very high concentration and little bit of silicon is present. Okay, so maybe say 99% aluminum and 1% silicon is present. So depending on different temperature, the composition will change. So if we keep on decreasing the temperature, the concentration will keep on changing, and the liquid concentration will follow this blue line, which is known as the liquidus line, and the concentration in the solid will follow this pink line, which is known as the solidus line. Okay, so these lines, liquidus and solidus lines, are actually very important in developing our model. So that's why we are studying this part. Okay, so after a certain temperature, when we go below the eutectic temperature, rest of the solidification occurs as eutectic solidification. We don't need to know right now what is eutectic solidification, because we'll not go into details of eutectic solidification, but we can just note that solidification will get completed at that temperature, and below this we will only have solid phase. So it will be a mixture of alpha aluminum and the beta phase, which is silicon in this case. This is similar to many other materials. Say for example, aluminum, copper will also have similar behavior, only the values will change. Okay, but we will have liquidus line, solidus line, eutectic point, but the composition and the temperatures will change depending on the alloys. Okay, some binary alloy phase diagrams are much more complicated. For example, iron carbon diagrams, where you have multiple solid phases, different types of solids are there. But this is the simplest type of phase diagram, and this actually governs how the solidification process from when we start from a high temperature liquid and finally go to a fully solid state. So we'll see more about this using a hypothetical phase diagram in the next couple of slides. You are free to ask any questions anytime, okay, in case these things are not familiar, but this should be very familiar to all of us, very basics things. So now coming to some more details of binary alloy solidification. So if we start with a liquid, okay, say we have a domain like this, rectangular or square domain, rectangular domain like this, which is filled with liquid binary alloy. Remember what is a binary alloy? It is a composition. It consists of two constituents. For our example, we will consider say 90% aluminum, 10% copper. Okay, so let us start with such a liquid, 90% aluminum, 10% copper, and apply a cold boundary condition on one side. So it can be applied by using say some chiller on this side or some metallic block like say copper block, or you can actively extract heat from this direction by using say water cooled chiller. So what will happen is that solidification will start, and we will see that there are three regions which are formed. Okay, so these three regions are, one is a solid region, one is a purely liquid region, and in between there is a mixture of solid and liquid. Okay, so at the macroscopic level, this mixture of solid and liquid appears as a porous region, which is known as mushy region. It is as a basically a mushy structure. But if we go into microscopic length scales, we will see that actually there are distinct solid and liquid phases here, and they can be resolved. But at the system level, we just consider that it's a single entity which is known as the mushy region. Okay. So why this mushy region is present? Because the solidification of alloys does not occur at a single temperature, unlike pure material, where the solidification occurs at the solidification temperature, fixed solidification temperature. For the alloy, the solidification starts at the liquidus temperature. I will show you another phase diagram. Okay, we'll go back to that discussion, but let me show this. So we have, this is a hypothetical binary alloy phase diagram. Okay. So if you follow this vertical dashed line, which says that concentration is C0, the solidification will start at the temperature Tm. Okay, this is corresponding to the concentration C0. What is the temperature of this upper line, which is the liquidus line? So this temperature is the start of the solidification temperature, and solidification will end. So if you keep on cooling, the final solid will form at this temperature, where it intersects with the lower line. This line is known as solidus line, and here the final solid will form. And so what I mean to say here is that the solidification process over a range of temperatures, starting from this Tm up to this temperature. Okay, in this case. So again, depending on, so it's for equilibrium solidification. For non-equilibrium solidification, again things will change. But let us just focus on equilibrium solidification right now. Equilibrium solidification means there is infinite time for diffusion and say to reach equilibrium basically. In real life, things are at non-equilibrium, but phase diagrams are drawn at equilibrium conditions, and equilibrium states exist at near the solidification interface even in real life situation. Anyway, we will not digress, but the point is that solidification occurs over a range of temperatures starting from TL to TS. Okay, so as a result, if we consider the temperature gradient in this, so the lowest temperature is near the cold boundary, highest temperature is far away, and there the temperature varies from very low temperature to up to TS, and then up to TL, and then higher temperature than TL. So between this temperature TS and TL, there is a mixture of both solid and liquid because solidification is progressing, and there the mushy region exists. So let us define some more terminologies. Okay. So as I have already defined, for defining the equations, we will use the concentration of the constituent which has lower proportion. For example, if we have a 90% aluminum, 10% copper, so we will call the copper as solute. Okay, and the solute concentration generally is denoted by some parameter C, so concentration of copper, and the solute concentration at for our case, say at this point is equal to Cl. This is the concentration of solute in the liquid, and the corresponding concentration in the solid is Cs. Okay. So one important thing to note here is that at equilibrium, when you have certain amount of solid in contact with liquid, the concentration of the liquid and solid cannot be independent. Okay. If the liquid concentration is given by Cl, it means that it exists at a certain temperature given by this line. So if this line intersects the temperature, so that is the temperature at which this material exists. So as a result, at that temperature, the concentration of the solid will be what is given by this solidus line. So it will be equal to Cs. Now, if you change the temperature to some lower temperature, the liquid concentration will change. So it will be a new concentration. Say, let us call it Cl1, okay, or Cl dash. But while it is changing, the concentration of the solid will also change. Okay, and this, if we assume that these two lines are straight lines, so this is known as linearized phase diagram. If these lines are straight lines, then they will have a constant proportion. So Cs will vary as a ratio of Cl. Okay, so this ratio of Cs by Cl is given by a parameter which is called as partition coefficient, generally denoted by K or Kp. This is known as partition coefficient. So the importance of the parameter is that if you can somehow predict what is the value of Cl anywhere based on the temperature, automatically you know that the concentration of the solid will be Kp into Cl. So Cs will be Kp into Cl. So we don't need to solve for both Cs and Cl. We can just solve for Cl in our calculation. Okay. So let us keep this also in mind while which we will use while developing our governing equations later on. Okay. So apart from this, let us try to also look at what are different length scales at which solidification. So when we are looking at the system level here, we just see solidification as a macro scale process. Like as I was saying, that there is solid, there is liquid, and there is a mushy region. But lot of phenomena occurs at different length scales, which are important and which can be modeled using various types of models. Not all of them are CFD models. Okay. CFD model can be used at the system level. So we can do a CFD model of this casting process, for example. And there are many research which have been done for a long time in this area. Like very well developed models are there for the last 20-30 years. Then CFD models can be used at the microscopic level. A lot of models are being developed in recent years. But there are other types of models for lower length scales. Okay. So let us look at the same casting process, and let us focus on the mushy region because that is the region where the solidification is occurring. So the solid part is already solidified and the liquid part has still not started solidification. So most of the important dynamics is present in the mushy region. Okay. If we zoom on in the mushy region, so at a millimeter length scale, what we will see is that there are large number of structures like this. These are known as dendrites. Okay, there can be these types of free floating dendrites. These are actually tree-like structure or branch structures which can float freely in the liquid. These are called as equiax dendrites, or there can be branch tree-like structure which grow from one side, which are known as columnar dendrites. So there can be columnar dendrites or equiax dendrites. It may not be always possible to resolve them at the millimeter length scales. Depending on the material, they can be of millimeter length or say 100 micron, of the order of 100 to 500 micron. Again, they can be very small also, 10 microns for very rapid solidification, which we nowadays encounter in 3D printing. If we go to lower length scales, you can go to individual dendrites. So each of these dendrites will grow into a single grain. The grains that I was showing here are ultimately one solidified dendrite. Okay. So we will see how these dendrites grow in the next slide, but let us consider that at the millimeter or sub-millimeter level, say 500 micron, around those levels, dendrites are the important structures. So if we want to develop a CFD model for dendrite solidification, we have to focus at this length scale, 100 micron to 1000 micron. Okay. If we go to even lower length scale, less than 100 micron, then the diffusion process becomes very important. Okay. So how the concentration varies in the solid and in the liquid, and how that influences the interface. So if I just zoom in on, say, one interface like it has been shown here, this slide is actually a very popular slide. It has been taken by one of the pioneers of solidification modeling, Professor Waller from University of Minnesota. So I borrowed this slide from him. So he has nicely shown here, so all the different length scales. So we can see that how the concentration gradient sets up in the solid and in the liquid. So this type of things also can be predicted using CFD models, okay, as we will see later. If we go to even lower length scale, so of the order of 10 micron to 1 micron, then the important things which are which has like most prominence are the interfacial energy, and this interfacial energy actually depends on the curvature of the tip and other areas. So the tip radius plays a very important role. Okay, this can be captured by some of the CFD models, but there is scope for improvement because this is at a very small length scale. It can be captured roughly. We will see how to capture this in our CFD models. But again, there can be improvements in this area. Okay, or there can, if a study is solely focused in area on the surface tension effect, other types of analytical models can be developed. If we go to even much lower length scale, much lower length scale, at the interface length scale, the interface is of the order of 1 nanometer, like the atomic exchange that is going on is of the order of around nanometer length scale, 1 nanometer. Okay, so this type of study has to be done using first principles or say using molecular dynamic simulations, okay, which is beyond these are beyond the scope of CFD models. So CFD models are very widely used for macro scale solidification. Nowadays, they are also prominently used for micro scale solidification simulations. For other length scale, there are other types of model, because at this length scale, the assumptions that you take in CFD, like continuum assumptions, those type of assumptions break down. So individual atoms actually play a very important role, and we cannot assume that we have a continuous material. So the individual atomic characteristics are more important. Forces between individual atoms are more important. We have other types of models here. And all the, again, Professor Waller has nicely shown all the important physics at different length scale. For example, at the system level, heat and mass transfer is very important. I will also add here that this heat and mass transfer is strongly influenced by the convection pattern that is generated. So we not only need to model the heat and mass transfer, but we need to model the flow pattern also. Then at the microscopic level, these are the time scale and these are the length scale. So at this microscopic length scale, like sub-millimeter level, dendrite growth and the grain formation is important. At lower length scale, solid diffusion is important. So up to this, CFD models nowadays can tackle. If you go to some micron level, how each dendrite forms, this process is known as nucleation. So this occurs at a few nanometer length scale. This cannot be captured using CFD models. So we use some ad hoc methods, like some statistical methods or random number generation to closely approximate this nucleation phenomena. But we cannot exactly predict how the nucleation will occur. So if you want to model nucleation, you have to go with molecular dynamic simulations, MD simulations. And at even lower length scale, we have interface kinetics. Okay. We have to solve using first principles, analytical solutions calculated based on, say, forces. So finally, I will just conclude this part, the basics part. What is the time? I think today I'm going on time because I kept less number of slides. And my main emphasis was to focus on the basics and on the simple modeling part. So I will conclude this part by summarizing the important features that occur, the important phenomena that occur at the macroscopic and microscopic level, because these are required to be captured by our CFD models or any CFD model. Some of these can be captured using our model. Some of these we may not be able to capture. Some other researchers are able to capture. Some of these are still beyond the scope. Maybe models will be developed in future to capture those phenomena. But let us try to look at this casting process schematically in somewhat more depth. So if you consider a typical casting process, you have a liquid alloy and say it is cooled from 3 directions. Okay. So as I was saying, we have a solid region shown by the black region here. We have the liquid region here. And in between the solid and liquid region, we have the mushy region, which is a mixture of solid and liquid. So if you look at the system level, you will not be able to distinguish the mushy region, what is happening at the mushy region. So what are the important parameters or important phenomena that are occurring in the system level or macroscopic scale? So one is the heat transfer from the boundary conditions, based on the boundary conditions. So if we have cold boundaries here, what is the heat transfer? Then large scale mass transfer. Large scale mass transfer means how the concentration of the alloy, say copper, if we have aluminum copper, how the copper concentration changes within the domain. Then what are the large scale flow patterns that are developed? So flow is generated in the domain because of various reasons. One reason can be buoyancy effect. So hotter fluid will rise upward because of lower density. So this is we know as thermal buoyancy. But there is another source of buoyancy in alloys, which is known as solutal buoyancy. What happens is that the constituents do not have equal density. So for example, in aluminum copper has higher density. So if at some location, the percentage of copper is higher, that portion will try to go downward because the average density there will be higher. Okay. So if at some location the concentration of copper is lower, that portion will try to rise up. So this is known as solutal convection. Okay, both are natural convection. One is thermal buoyancy driven convection, one is solutal buoyancy driven convection, and both actually can assist each other or can oppose each other depending on the density of the individual components and the boundary conditions, temperature boundary conditions. Then there can be shrinkage related flow also. So if the density of the solid is generally higher than the density of the liquid, so what happens is that to compensate for the higher density of solid, what happens, solid volume is lower when a certain amount of liquid solidifies. So some flow has to come towards that solid to compensate for that lost volume. So as a result, there is flow due to shrinkage also. So these are some of the important things that needs to be modeled at the macroscopic level. Now, if we zoom in on the microscopic level, so remember our discussion for today is focused on the microscale modeling. So I'm just giving you a glimpse of the macroscopic level because we want to relate the microscopic phenomena to this macroscopic phenomena which are occurring. If we zoom into the mushy region, what we will see is that there are individual solid and liquid regions. So there are free floating particles like that, which are known as dendrites. I have already told, these are known as equiax dendrites. Each of them form just from the formation of a small particle, which is known as a nucleus. Okay, so this nucleus can form randomly, just a few atoms coming together, or they can form over impurities, like a small impurity particle is there, and they can form over that. So once a nuclei is formed, it can be either stable or unstable. If it is unstable, it will again melt back. If it is stable, it will start growing, and a solid particle like this will form. And these solid particles, if they are free to float around, these are known as equiax dendrites. If the solid particles grow from one side of the solid, like this wall of the solid, then they form in a directional manner from the solid towards the liquid. These are known as columnar dendrites. Okay, so equiax dendrites and columnar dendrites are these two types of dendrites, and they may have more number of branches. So I am showing only the primary branches. There can be secondary branches, so small branches over this, and then there can be even sub branches which are known as tertiary branches. Okay, so to model microstructure, final microstructure like we were seeing here, we need to model how this type of dendrites grow and solidify, and finally how they will occupy the entire domain. So if we can model that, we can find out what is the influence of various system level parameters on the final microstructure. Okay. Now, how many minutes are there for the break? Still time is there. There are some other things which are important at the microscopic length scale. One is that the flow is still prominent here. The macroscopic flow that was there, that plays an important role at the microscopic level also. Okay, that governs the dendrite growth and brings in or changes the solute concentration pattern. Then there is shrinkage driven flow, which I have shown here. Okay, then formation of gas porosity, eutectic formation. So all these are important phenomena at the microscopic scale. So what do we need to consider at the microscopic level if you want to develop a model? We need to consider again heat transfer, obviously, because there is heat transfer occurring. Without heat transfer, there cannot be phase change. Then there is mass transfer. Mass transfer means change in solute concentration. So copper is going from one place to the other, or aluminum is going from one place to the other. So there is mass transfer. Then we have to solve for the flow. So we have to solve the flow equations. If we want to incorporate other types of things like gas porosity, those things also need to be solved for. We will not consider them in our preliminary study today. Okay, but people are trying models which involve gas porosity also. Then shrinkage is another thing. So flow due to shrinkage, and even shrinkage itself, those things are also very complicated to capture. One thing before I go into the equations, one thing I would like to mention here is that why these dendrites grow in these particular directions. Like you can see that they are going, I have shown schematically that they are going in a 4-way direction. So in 3D, they will be growing in 6-way direction. Okay. So this happens because of the atomic structure. Okay. So if I go back to the atomic structure, say if this is the atomic structure of a pure material or say alloy. So we know that the atomic structure can be defined in different ways, like say body centered cubic BCC structure, then face centered cubic FCC structure. So these are the different basic structure, like basic building block for the atom, basic structure at the lowest resolved level. So it is much easier to add more atoms during solidification along the planes of the structure. So if we have a cubic structure, it is much easier to add more atoms along the planes of the cube as compared to say the diagonal direction or any other direction. So the solidification generally proceeds at the microscopic level aligned with the planes of the structure, cubic structure, or they align with the atomic directions. So when the nucleus forms, they form in any random direction of like atomic arrangement. So as a result, these dendrite arms actually are growing in various random directions based on the initial atomic arrangement in them. So once the initial atomic arrangement is fixed, the dendrite will follow that direction only. So each of them will have an individual orientation and they will not match with the other say, neighboring dendrite. So when they come in contact with each other, there will be a mismatch of the atomic structure in between them that will lead to grain boundaries. So this is important because this is one thing that needs to be incorporated in the microscale solidification model, which people do not incorporate in the macroscopic models because we do not resolve dendrites in the macroscopic model. How the dendrites are going. Otherwise, what we will see is that if we just solve heat transfer and mass transfer, we'll see that always we get a circular structure which is going. We'll not be able to capture the dendritic nature or the growth in particular directions. So it has to be explicitly given to the model that dendrite should grow in this pattern by some type of mathematical construction. So again, as I was saying, the most important thing about microstructure modeling is that microstructure governs the final properties of the material, and the microstructure, by microstructure modeling, we can determine how the growth rate and pattern, microstructure pattern, is influenced by the thermosolutal say distribution at the thermal say heat transfer and solute transfer adjacent to the solid interface. This governs the grain growth, solidification, and the solute pattern. So this is strongly influenced by the nature of convection. Then something called undercooling, which is the temperature below the melting temperature. Okay, I will define later. Partitioning, which I have already defined, partitioning coefficient. So we need to understand the role of these parameters in the final microstructure. Okay. And these are from some real life X-ray experiments where you can see how the dendrites grow. These are equiax dendrites, these are columnar dendrites, again some other equiax dendrites you can see here. So these are actually, this show that the dendrites grow in particular direction and there are secondary branches formed, even tertiary branches. And we need to very good, say, exhaustive model or very generalized model should be able to capture all these phenomena, but it is not possible in all models. Okay. And this is how, this is again an experimental result, although it looks like a modeling result. This is actually a SEM EBSD image of the grain structure, which is shown by different colors because each color corresponds to a grain orientation, like the dendrite angle that I was saying, orientation of the atomic structure. So what this image shows us is that what is the number of grains that are present, so which will give us the average grain size or grain density. And it's a very important parameter because it governs the strength of the material. Then what is the morphology of the grain, whether they are circular in nature or whether they are very, say, needle shaped or have sharp edges. This also determines the properties. So whether there are chances of fatigue failure or whether there are chances of low ductility, high ductility, that will be governed by the shape of the grains. Okay. Then also what is the concentration variation within the grains and in between the grains in the intergranular region, which is known as grain boundary. So how the concentration varies. Okay. We need to determine the effect of various operating and design parameters on these important parameters which influence the final mechanical properties of a structure, solidified structure. And ultimately our aim is to be able to predict this type of grain structure by starting with dendritic solidification model. Finally, if we can predict this type of large scale grain structure, that will be fantastic because that will lead us to design better and better properties, materials with better and better properties. I think we can take a break here, Dr. Rath. Can we take a 5 minutes break here? Dr. Rath is there. He's not, he's here. And then continue after 5 minutes. We'll go into the modeling details. So we will take a 5-minute break, and so it's 10:51. So we'll again start at 10:56. Okay, and jump into the modeling details. So we have covered some of the basics, which that is the required background that is needed for developing the CFD models.
Okay.
So, okay, we will continue our discussion after this short break. What is this message? So let me continue our discussion. So can somebody confirm whether the slides are visible?
Yes, sir, it is visible.
Okay, okay. So before going into towards the last part of our discussion, means final hour, we will go into the details of microstructure model. At least we will try to see whether we can predict this type of large scale grain structure and large scale dendritic solidification. But to develop those models, the basic building block is that we need to develop a model for the growth of a single dendrite. Okay, without that we cannot achieve this type of large scale microstructure evolution model. Okay. So we will put the major emphasis for today's lecture on the modeling of single dendrite, because this is the important part. If we can do this, the other parts can be taken care of using minor modifications. Means lot of modifications are needed, but the important physics is included in the growth of a single dendrite. It's more about other things related to microstructure. Let us see how a single dendrite growth can be modeled using CFD. Okay. So when we call a single dendrite model, so we will be using something known as enthalpy based model. So enthalpy based model is a type of model where the phase change process or the solid liquid interface is tracked using the enthalpy of each discretized cell. In a say CFD grid, you have control volumes or grids, grid points. So based on the enthalpy of each grid point or control volume, we can predict whether there is a solid cell or it's a liquid cell or interface cell. So by tracking the enthalpy or by calculating the enthalpy, the solidification can be tracked, and it is very widely used for macro scale solidification processes. But has been recently means still say last more than one decade, people have started using it for microstructure modeling also. There are other types of microstructure prediction models, but not all of them are CFD based. They are more like mathematical models or some physics based models are there, but do not use CFD type of calculations in many cases. And there are a lot of analytical models, but those can only predict dendrite growth at a simplistic level, like what is the say steady state growth rate, things like that. Overall size of a grain, but not the entire microstructure or entire structure of a single dendrite. So when we say about microstructure modeling, so we have to consider two separate things. One is that there is flow occurring, so we need to model the flow, which means that we need to solve the momentum conservation equations, okay, and the continuity equation. Then we need to solve for the grain growth, which is basically a phase change process. So phase change is governed by heat transfer, so we need to solve for the energy conservation equation. And because it is an alloy, there are two constituents, aluminum and copper, and the composition will vary at different locations based on diffusion and convection. So we need to also solve for so the governing equation for that is known as species conservation equation. So we need to solve for the species conservation equation for any one of these species. So if we solve for the copper concentration, automatically we know what is the concentration of aluminum, because the summation of the total concentration should be 100%. If we know that at somewhere copper concentration 9%, it means that there the aluminum concentration is 91%. Apart from this, particular to the microscale model, CFD models, we also need to incorporate something which are related to the interface. Okay, so the interfacial energy or the surface tension effects are very prominent at microscopic level. These are not important at macroscopic level. So researchers among you who have done or have some experience in macroscopic modeling of solidification generally do not consider this interfacial energy. They are more focused on other aspects, like how to model the mushy region, porous medium effects. But at the microscopic level, we cannot ignore interfacial energy, and that actually depends on the interface profile or the curvature of the interface. And then there are other effects which are known as constitutional effects, which is basically the change in temperature, melting temperature due to change in concentration based on the phase diagram, as we will see later. Okay. Let us take a simple problem. We have a domain like this, say it's a square domain or a rectangular domain, which is filled with a binary alloy liquid with an initial concentration C0. Okay. It can be some say 10%. Or say in non-dimensional number 0.1, and it is initially at a temperature which is lower than the melting temperature. So for this type of dendritic solidification to occur, or any solidification which occurs, actually occurs at a temperature which is lower than the melting temperature or solidification temperature. If the temperature is just equal to the solidification temperature, the solidification will not proceed. Some temperature gradient, some temperature difference is required to overcome the effect of surface tension and other constitutional effects so that solidification can proceed. So as a result, when you start cooling, say we initially start with a domain like this, and we are at a temperature of 150 or whatever. Say if it is aluminum, we are at a temperature of 900 degrees centigrade, and we know that solidification temperature for aluminum is 660 degrees centigrade. If we start cooling this, when we reach 660 degrees centigrade, we will not start solidification process. So for solidification to start, we need to go below 660 degrees centigrade to some lower temperature, say 640 degrees centigrade or 650 degrees centigrade or some 653 degrees centigrade. So this temperature, which is lower than the solidification temperature, is known as the amount by which it is lower is known as the undercooling, and the liquid is known as undercooled liquid. And this undercooling or delta T, which we will call later, is the driving force for the solidification to occur. Okay, to overcome the interface surface energy, that extra energy that is required for the additional surface to form. So for this model, we will start with we will assume that already the liquid is at an undercooled temperature, below the melting temperature. And we are starting the solidification by putting a small single crystal of solid at the center. How we define it in CFD? We just make the properties of one control volume or one grid point equal to the solid properties, and all the other properties, all the other control volumes have liquid properties. Okay, so like this, so this is just artificially introducing a nucleus. Okay, so for this control volume, we make the property concentration is equal to Kp into C0. Remember the relation that if the concentration in the liquid is Cl, the concentration of the solid has to be equal to Kp into Cl. So Cs is always equal to Kp into Cl, because that is the ratio of Cs and Cl. So because here the concentration of liquid is C0 initially, the initial concentration of solid is assumed to be Kp into C0. Okay. And the solid will be, we will assume that it is at melting temperature, the prescribed melting temperature for that alloy. So at C0, the melting temperature of the alloy according to the phase diagram is Tm, okay, for that concentration. So that is the melting temperature. So if the concentration increases later on, the melting temperature will also change. Okay, that needs to be accounted for. We will see about that later. Okay, how it is accounted for. So there can be convection in the domain, or there may not be convection. There can be convection due to some forced convection, like some flow coming from outside, as shown here by the arrows. Or there may not be some flow coming from outside, but internally their flow can occur because of thermal or solutal buoyancy, as we have discussed previously. Okay. So these also needs to be modeled, and we can make them zero by appropriately changing the terms to zero in the governing equations. So a general model should also account for that. And this is the typical binary alloy phase diagram that is considered for this type of modeling. As we have said, initially we start with a concentration C0, and later when the concentration changes at any particular concentration Cl, the concentration of the solid will be Cs, which is equal to Kp into Cl. And the temperature at that point will be some temperature T, which is different from Tm by a temperature delta Ts. This is known as solutal undercooling. This can be easily obtained from the slope of this line M. If we call the slope of this line as M, So based on the slope of this line and the change in concentration from C0 to Cl, we can find out what will be the delta Ts. Okay. So if the concentration is higher, then the delta Ts increases. The difference between original temperature and the actual melting temperature changes. Okay. So this is an important part which we will have to consider. So what it means is that you cannot just solve the energy equation and find out what is the phase change process, because the melting temperature itself changes based on the concentration at the microscopic level. So the interface temperature, melting temperature or the interface temperature has to be calculated after calculating the concentration. So first the concentration equation has to be solved, and then it is coupled with the interface temperature that needs to be solved to find out the phase change that is occurring. So now let us look at the mathematical formulation. This is the most important part of today's discussion. So how this and subsequent few slides, how to mathematically formulate this problem. Okay. So again, like all CFD problems that you must have encountered these equations, some of these equations at least. So because heat transfer is occurring, we need to solve for the energy conservation. And that can be solved in different forms. The form that typically for microscale models that is used, initially that was developed by Waller and it has been followed by other researchers, is of this form. So we keep it in terms of enthalpy. We do not convert it in terms of temperature. So now this can be, so this is the form. So del del T of rho H plus del dot rho UH plus del dot K del T. Okay. So first term you know is the transient term, second term is the advective term, and third term is the diffusive term. Now this instead of H, so what is this H? H is the enthalpy at each grid point. Okay. So this is known as volume average enthalpy, and this can be written as sum of the sensible energy and the latent energy. Sensible energy can be taken from any reference point. If we take the reference point to be melting temperature, sensible energy is Cp into current temperature T minus the reference temperature Tm. And latent energy is, say if we take the latent energy reference state to be 0 at solid, in the liquid the latent energy is given by L. This is the energy required for melting, latent energy for melting. Okay. So we defined another fraction which is known as liquid fraction. Okay, this is the volume fraction of liquid in any control volume. I will show you what in the subsequent slide what it means. But say if you have any grid point or control volume, there will be, say, it can be fully liquid, fully solid, or part of it can be liquid or solid. So how much is liquid is given by this fraction Fl. Okay, so it can be 0. It will be between 0 and 1 for an interface. If it is 0, it means that it's fully liquid, a solid. If it is 1, it means that it is fully liquid. Okay. So for a partially liquid control volume, the latent energy is Fl into Fl gives the amount of liquid into the latent energy of liquid. Plus, obviously, there will be Fs, which is the solid fraction, 1 minus Fl into 0, because latent energy of solid is 0. So if we consider Fs to be the solid fraction, remember that Fl plus Fs has to be equal to 1, because the total amount of liquid plus solid in a control volume total fraction is equal to 1. So basically we just need one volume fraction, and automatically we will be able to find the amount of solid, which will be equal to 1 minus Fl. Okay. So based on this volume average enthalpy, we can define our energy equation. Now this energy equation can be solved in different forms. We can write it in terms of temperature. Then all the extra terms will go into the source term if we want to solve implicitly. But typical procedure in this type of microstructure model is to, or enthalpy-based microstructure model is to solve directly in this form in terms of enthalpy using explicit method. Okay. So based on previous time step value of temperature. I will come into the algorithm a little bit later. But this is how we formulate the energy equation. Rho is the average density of each grid point. U is the velocity which needs to be obtained by solving the momentum equations. K is the average conductivity at each grid point. Okay. So which is Fl into Kl plus 1 minus Fl into Ks, where Kl and Ks are the liquid and solid conductivity. This is the average at each of the grid point. So the interface value of conductivity is different. That needs to be accounted for using harmonic mean, which will not go into details. Those type of formulations are present in the book by CFD book by Patankar, as I had discussed. Might have been discussed also in other lectures. Very fundamental book by Patankar. There all these intricate details of finite volume method is given. So this is the control volume conductivity, volume average control volume conductivity. Then so for solving this equation, what do we need to do? We need to have the value of U, which can be obtained if we are solving using explicit scheme. We can use previous time step values, which we already know. So say at any time, we already know all the values, okay, from previous calculation. So for calculating for the next time step, if we want to calculate the value of H for the next time step, we can use the previous time step value of U, which was obtained by solving the momentum equation in the previous time step. Then temperature also can be used from the previous time step. It will be known from previous calculation. And for calculating the conductivity and density, we need to use the averaging. So the liquid fraction value needs to be used, and that also can be obtained from the previous time step. So all values will be known except, and this H also can be written in terms of previous time step. So only this term can be written in terms of H nu minus H old, or rho H nu minus rho H old, from which we can find out the new enthalpy value in a time step. Okay. So similar to the energy equation, we also need to solve for the concentration of the solute. Remember that for a binary array, one concentration is sufficient, because for the other element, we can just subtract from 100% to get the concentration of the other element. So which the concentration is typically called as solute concentration or species concentration. Okay. So this is given by, generally it is given as a volume average concentration C, which depends on the concentration of the liquid Cl and the concentration of the solid Cs. So in a control volume, if we have certain amount of liquid Fl, so Fl into Cl will be the amount of solute that is present in the liquid part, and 1 minus Fl will be the volume of solid, and multiplied by Cs will give us the amount of solute that is present in the solid part. So the total amount of solute that is present in the control volume is C, okay, which is given by this volume average concentration. Okay. So this again, we define another parameter. Okay, another parameter. We means not I, means the enthalpy models that have been developed, which was pioneered by Waller. So another parameter is defined, which is known as concentration potential. Okay, what is this concentration potential? So this is nothing but something analogous to this liquid concentration. If you see, if we calculate Cl from this expression, okay, so in place of Cs, we can write, remember that Cs is equal to Kp into Cl, which we have already noted here. Cs is equal to Kp into Cl at all conditions. Okay, so we can replace this Cs by Kp into Cl, and we can write this Cl. We can take all the Cl in one side. We will obtain this expression for Cl. Okay, now this expression of Cl is valid in the liquid region, because in liquid region Cl is defined. But what about the solid region? In the solid, there cannot be liquid concentration. In the solid, the concentration is solid concentration, right? So for the solid, a pseudo liquid concentration is defined, which is known as concentration potential. And this needs to be defined because at the interface, this pseudo liquid concentration or the concentration potential determines what is the direction of diffusion of solute. Okay, so if the concentration potential is higher in the solid as compared to that in the liquid, the diffusion will occur from the solid to the liquid. Although the concentration in the solid may be lower, it will depend on the concentration potential. Okay, so this is analog. You can, for our simple case, you can just consider this to be analogous to liquid concentration. So we can write the conservation equation, species conservation equation, in terms of concentration, and for the convective term, for the only the liquid part will have velocity, solid part will not have velocity. We will assume that there is no movement of the solid. If there is movement in the solid, it becomes much more complicated. So for this simple type of models, we will assume that solid phase is fixed. So velocity in the solid is 0, so only liquid term is there. As a result, Cl we can replace by V. Similarly, in this case, actually diffusion is present in both solid and liquid, can be present in both solid and liquid, although the diffusion in solid is very less. Okay, but what we can do is, I don't have the details here, but we can average this, we can write this in terms of volume averaging. So there will be two terms for the diffusion. For the liquid part, there will be rho dl, gradient of Cl, and for the solid part, there will be rho ds, gradient of Cs. Okay, so that Cs can be replaced by Kp into Cl, and all the Cl terms can be replaced by V. So ultimately, we can have a single term like this, del dot rho d into gradient of V, and this d considers both the diffusivities. Okay, so Fl into dl and Kp into 1 minus Fl into ds. This Kp comes because we are replacing Cs by Kp into Cl. So that extra Kp will come into the equation of diffusivity. This is known as volume average diffusivity. Okay. So again, this now if you look at this equation, yes.
Sir, your slide is not changing.
It's not changing. Which slide you can see now?
Problem description, we are there.
No, you should have told me earlier. I will unshare and share again. So solve the problem. Now can you see the mathematical formulation?
No, sir.
Equation. Which slide you are seeing now?
Problem description.
Still?
Yes, sir.
Sir, for us.
Sir, we can see the mathematical formulation.
Okay. Then I will leave in again.
Yes, yes. Okay. I will continue. Okay. So ultimately, if you see, the form of the equation is exactly same as the form of the energy equation and can be solved in exactly the same way using explicit method or explicit finite volume method. So if we want to calculate C, we can use previous time step value of U, previous time step value of V. We can assume that we have somehow found the value of V in the previous time step, and previous time step value of D, because D will depend on liquid fraction, and liquid fraction has to be will be changing with time. So we will use previous time step value. So all these values will be previous time step value. Then we can calculate rho C new minus rho C old in terms of these old values. This can be discretized using finite volume method, using any method. So for example, these convective terms can be discretized using upwind scheme, okay, or power law scheme or any other scheme. And these are again there in the basics, any basic CFD book like Patankar's book you will see. And these diffusive terms also can be discretized very easily, okay, using the standard methods. So standard finite volume method. So ultimately we will get new value of C and new value of H after solving these equations. So after this, what is still unknown? Okay, if we just consider, let us for this moment forget about the flow part. If we just consider the solidification part, there were five unknown variables. Okay, the enthalpy H, the concentration C, but there are three more unknowns. One is the liquid fraction itself, Fl. One is the concentration potential V, and one is the temperature T. These are coupled together. Okay, so they are not independent, and they need to be obtained based on the calculated H and C. Okay. Apart from this, we need to also solve for the velocity using the continuity and momentum equation. So I will come to this part a little bit later, but let us first see how to solve. If we just assume that there is no flow, still we can have gradient growth. So how to solve for that? So remember, we have already found new H value and new C value. Okay. Now we are going to use those values to find the other parameters: temperature, liquid fraction, and concentration potential. Okay. I have changed the slide. I hope you can see the next slide now. There is a diagram which shows solid region, liquid region, and interface region. Okay. And interface curvature, anisotropy, and undercooling. So if we consider the typical control volumes for our CFD problems, there will be some cells like this shown in dark color, which are solid cells. Here, the liquid fraction is known. It has a value equal to 0. Then there are some cells shown with white color here. Here also the liquid fraction is known. If it is fully liquid, FL will be equal to 1. Then there are some cells shown here in the light gray color. These are the interface cells. Okay, we do not know the exact shape of the interface, although I am showing a curve here, but this may not be the curve. Means you are not resolving the actual interface. You just have the value of liquid fraction here. The previous value of liquid fraction is known here, FL. Okay, so it can be 0.5, 0.3. It is between 0. What we know is that the liquid fraction is between 0 and 1. That's why we are calling these as interface cells. And we want to find out the new liquid fraction value after the, like in this time step. How much solidification has progressed, that can be obtained if we calculate what is the new liquid fraction value at each cell. Okay. Now this, to calculate the new liquid fraction value here. Okay, before that, let us assume how to calculate temperature and concentration potential. This is wrongly written as C. So T and V, how to calculate T and V here, which are unknown. C is already known. Okay. So if liquid fraction is known, we can just calculate temperature using this equation. So if liquid fraction is 0, this term will become 0. And H is already calculated, so you can calculate temperature from here. If liquid fraction is 1, this term will be equal to L. Again, H is already known, so you can calculate T from here. Similarly, concentration potential you can calculate. If liquid fraction is 0 or 1, you can just replace here, because C is already known. V can be calculated from here. The only problem arises at the interface cell where liquid fraction value is not known. Okay, there we cannot calculate temperature or concentration potential. So other places we can directly calculate. Now what is the difficulty in this interface cells? So this is the part which is different from general macro scale models. Okay, so one extra relation has to be found here, and that extra relation is that we can calculate what is the temperature at the interface. Okay, so typically what do we expect? What is the temperature at the interface when there is solidification? Typically we expect that the interface temperature is equal to the melting or solidification temperature. Okay, that is what we know from our day-to-day experience. But in real life, what happens is that the temperature is, as I was saying, it is lower than the melting temperature or solidification temperature, prescribed solidification temperature, because of two factors. One is that the concentration is changing from the original concentration. So if the original concentration, as you can see here, was C0, and now it has become Cl, the melting temperature will change from this temperature to this lower temperature. Okay, so this extra decrease needs to be taken into account. If I go back to our diagram, phase diagram here, I am now in the problem description slide. Initial melting temperature was Tm, but because the new concentration is Cl, now the melting temperature has to be reduced by this delta Ts amount. Okay, so the interface temperature will be Tm minus delta Ts if we just consider this effect of concentration. So, but we do not know the Cl value. Remember, Cl is unknown. Cl is corresponding to V. Because V is unknown, we do not know what is the V value, and we do not know what is the delta Ts value. If we use the previous time step value of V, we can calculate the approximate value of delta Ts. Okay, from the previous time step value of V or previous iteration value of V. So, what happened? Am I still audible? Slides are visible? Can somebody confirm?
Yes, sir.
Yes.
Okay.
Yes, sir.
Okay. So this term can be written like this: minus m C0 minus V. M is the slope of this line. So this is known as liquid slope of liquidus line. It is a property of the alloy. It's known parameter. C0 is the initial concentration, and V is the unknown concentration of the liquid. It was known in the previous time step. For the current time step, it is not known. So we will assume the previous time step value, and we can find out what is delta Ts. Okay, or previous iteration value, and we can find out what is delta Ts. So this is one factor. The temperature will be even lower than Tm minus delta Ts because some extra energy is required to generate new interface. Okay, and that extra energy depends on the surface energy, surface tension effect, or it is known as, in more scientific term, it is called as interfacial energy. And this actually depends on the curvature of the interface. Curvature, if the interface is more curved, it means that more surface is there in a particular control volume and more energy is required. Okay, so it will depend on the curvature of the interface. If it's a flat interface, this term will go to 0 because for creating new interface, the length is not going to change. It will be the same length will be there. So if the interface is curved only, then there will be a term. And this is given by this expression. We will not go into depth of this expression. I will just state the physical significance of this expression. So this equation is known as curvature undercooling. This takes into account the effect of interfacial energy, gamma. So gamma is the interfacial energy between the solid and liquid. And this also takes into account the curvature. Okay, so the gamma is the interfacial energy per unit length multiplied by the curvature will give you the interfacial energy, and some other terms are needed to make it write it in terms of a temperature term. Okay, so if we can calculate delta Tc based on the interfacial energy will vary for different materials, obviously, and curvature needs to be calculated. We will see how to calculate, but if we can calculate curvature and all the other things are known, we can find out delta Tc. So if we know delta Tc and delta Ts, we can find the interface temperature by this equation. Tm minus delta Tc, this is the delta Tc. Sorry, Tm plus delta Tc in this form, in the form we have written, plus delta Ts. Okay, in the form we have written. So Ti will be less than Tm. Okay, because of the interfacial energy and the increase in concentration. So this, once you can find this, once you can calculate these two values based on previous values, we know that the temperature here should be all the interface cell. We can find out the Ti value. Ti will be different for each interface cell. Why? Because the curvature is different for each cell and the concentration is also different for each cell. So accordingly, this curvature and solutal undercooling will be different for each cell and Ti will be different for each cell. So for each cell, Ti needs to be calculated. Once you calculate Ti for each cell, we can now assume that the temperature is Ti, okay, for that interface cell, and H is already known, so we can find out the new liquid fraction for that cell, okay. And once the new liquid fraction can be obtained, we can find out the new concentration for that cell based on the new liquid fraction. So we need an iterative scheme because for calculating the curvature and solutal undercooling, we are using previous iteration value, okay. So this interface temperature is not correct, not updated. So once we find the new V and new liquid fraction, we have to again go and again calculate the new curvature and new delta Ts and new interface temperature, and again use that interface temperature to find the new value of liquid fraction and concentration potential. And we have to go on iterating until the three values are consistent: the interface temperature, the concentration potential, and liquid fraction. So once this convergence occurs, we can assume that we have obtained the correct value of temperature, concentration potential, and liquid fraction for the current time step. So this new liquid fraction will give us, if we plot the new liquid fraction, it will give us the new interface location. Okay, so we can now say that we have obtained how much solidification will occur in each cell based on the new liquid fraction value. So only one point that is left to be discussed here is that how to calculate the curvature. So that can be calculated. There are different ways again. So one famous method is to use, so based on the derivatives of the liquid fraction. Okay, so if I have a control volume structure like this, so for the interface cells, the curvature here can be calculated based on the derivatives, and the derivatives can be calculated based on the neighboring grid point values. I will show you one case later on how to calculate the derivatives, but this can be based on the derivatives. Okay, so FLX is the derivative of liquid fraction along the x direction, FLY in the y direction, FLXX is the double derivative, FLXY is the mixed derivative. So using this expression, we can calculate the curvature. Okay, and this is a very well-known equation in mathematics. It's given in the book by Sethian, and for any field which can be described with some volume fraction like this, we can calculate the curvature of any interface based on the derivative of the volume fraction. We also need to calculate the angle theta of the interface. So at each control volume, we can assume that the interface is just like a straight line. And what is the theta angle, interface angle that can be given again in terms of derivatives FLX and FLY. So tan theta is equal to FLX by FLY. So from this theta can be obtained. Theta is the angle with respect to the x direction. Okay. If theta is equal to 0, it means that the interface is the normal to the interface is aligned with the x direction. Not the interface angle, the normal to the interface. Why this theta is important? Because this surface tension is modeled in terms of theta. Why, you can ask why will the surface tension change at a different location with angle? In real life, it is not going to change. But as we were discussing, in real life, we have dendritic growth in particular directions, right? These preferred directions are there. So these are known as dendrite arms. And this occurs because the atoms are arranged in this direction. The atomic structure is in this direction. Now at our CFD length scale, which is of the order of 100 micron to 1 millimeter, we cannot capture the atomic physics. We will not be able to resolve the atomic physics. Anyway, which is not possible also because the continuum assumptions break down. So we cannot capture the effect of this directionality. So we have to impose this directionality in some form, some realistic form. We cannot say that. We can say that these are the preferred direction of growth, and that is given by making this interfacial energy as a function of theta. Again, we will not go into too much details, but in non-dimensional form, this can be written as, so the same expression, interface temperature in non-dimensional form, we generally solve, it can be written in this form. So non-dimensional curvature is there, which can be again calculated like this, and all the other values are non-dimensional. But this interface energy comes out as something called d theta, okay, which is a function of theta, and it can be written as some constant d0. It is a length scale. It is known as capillary length scale. Depends on the surface tension effect. Or into 1 minus 15 epsilon cos 4 theta. This is a very well-known model. This is widely used in all grain structure modeling. And what it represents is that cos 4 theta says that the interfacial energy will be maximum along 4 angles and minimum along 4 angles. Okay. So it means that the chances of growth is highest along 4 directions. Means the undercooling will be maximum in 4 directions and minimum in 4 directions. Wherever the undercooling is minimum, the growth rate will be maximum, and wherever the undercooling is maximum, growth rate will be minimum. This curvature undercooling. So we are explicitly specifying that dendrite growth has to be in 4 directions. If I say that cos 6 theta, our dendrite will grow in the model, it will grow in 6 directions. If we say that cos 3 theta, it will try to grow in 3 directions. Okay. So this is explicitly specified because we cannot capture the atomic level physics here. Okay. So it is how we are capturing the arm formation of the dendrites. And this epsilon is the strength of how much is the variation of this interfacial energy along different directions. This is known as anisotropic strength. If we increase this value, it means that it will lead to more pointed growth of the dendrite arms. Means more growth is there, more anisotropy is there. And if it goes towards 0, it will become more and more like a spherical structure. So this is how the interface, this anisotropy of the dendrite growth means that the dendrite goes faster in some direction and slower in some direction. This is incorporated through the interfacial temperature term, or in the interfacial temperature through the interfacial energy term. Okay, so these equations, once we solve together, we now have a good understanding. I hope you now have a good understanding how to solve this together to find out Ti, V, and liquid fraction. Okay, so all the 5 unknowns are known. So once these are solved, we can consider this as a separate problem, the growth part. So now we can solve the momentum and continuity equation using any method. For our case, we use simpler algorithm, but other algorithms can be used. Simpler is the very famous algorithm which was developed by Patankar long back and widely used. So we use simpler algorithm and we use a explicit implicit coupling. So these energy and species conservation equations are solved explicitly because it is easier to solve this equation in this form explicitly, and no convergence issues are there, and momentum equation and the continuity are solved using the simpler algorithm implicitly. And for these cases again, liquid fraction values will be needed because density will be average density and all many other parameters also depend on liquid fraction. Okay, let us take a look at some of the terms here which are relevant for us. Continuity equation is the general continuity equation, assuming that there is no like compressibility effect or no density change. Then we have the standard transient term, advective term, inertial term, then viscous term, pressure term. So there are two additional terms. One is written here is SB and second is minus K into U. Okay. So this SB term is the source term which may or may not be present. So it is up to us to define this term. So this can be defined to accommodate the effect of thermal or solutal buoyancy. So it can be written as a function of, using Boussinesq approximation, this can be written as a function of the local temperature and local concentration, and in terms of some reference temperature and concentration, and that will give us some like either positive or negative source term based on the temperature or concentration, so which will result in flow because of thermal buoyancy effect or solutal buoyancy effect. So the exact form of these equations are there in the second reference. You can go to the second reference and you can take a look. In some other references also it is there. In the Waller's preliminary model, flow was not considered, so it is not there. So that was just a diffusion-based model. But that was the initial framework based on which the other models have been developed. So this is for the Boussinesq term or the buoyancy term. The other term, so till now in the momentum equation, if you look at it, it's like a normal momentum equation. But we know that in the solid part, there should not be any flow, right? Solid, how can there be flow? So something needs to be done in the solid to suppress the flow. So this K actually is a very large resistance. It's a function of liquid fraction, and it goes to a value of 0 if liquid fraction is 1. And it goes to a very large value if liquid fraction is 0. It can be any function of liquid fraction. It can be a linear function, or it can be, sometimes it is taken as based on Karman-Kozeny approximation, which is a derivative of macro scale models. But I would like to highlight here that it can be any function for this, because it's a sharp interface model and there is no mushy region. So it can be just a simple function of liquid fraction. The only purpose is to make this K value 0 when FL is equal to 1, and K should be very large value when FL is equal to 0, means in solid region. So when in the solid region, if this term becomes very high, all the other terms will vanish and it will suppress this term will dominate as compared to the other terms, and it will suppress the velocity. Basically, Ku will be the dominant term and it will suppress the velocity to 0 there in the solid region. Okay. The other way to model the solid region would be to put the viscosity of solid as a very high value. That can also be used, and that is another way to, in the viscosity term, we can use average viscosity as a function of liquid fraction, and we can assume a hypothetical solid viscosity, which is a very high viscosity, which can suppress the velocity to 0 in the solid. So by solving this momentum equations, we can update the velocities, and these velocities will be again used in the next time step for solving the energy and species conservation equation. And again, the liquid fraction will be used for updating this Boussinesq term and not the Boussinesq, sorry, this K term and density term, and like this we can march along in time. Okay. One other point, couple of small points before we complete the discussion on the modeling part. Okay. And I will show you quickly some results, but my main emphasis was to describe in the slowly the modeling part, so that if somebody is interested, they can develop the model by reading the papers also, similar types of CFD models. So for calculation of these derivatives, any of the derivative, let us consider this FLX or FLXS. Okay. So if you just consider the interface, this type of interface is known as sharp interface, because within a single control volume, the solid changes to liquid. So you have solid here, you have liquid here, and the change or the interface is located within a single control volume. Okay, as opposed to diffuse interface models, where the interfaces are spread over multiple control volumes. Gradually, these change, the properties change. So in the sharp interface models, what happens is that although you can calculate the curvature accurately, but for calculating the curvature accurately, you need to calculate the derivatives accurately, and that calculation of the derivatives is very difficult because there is a sudden jump in the value. Okay. So to calculate the derivatives, one technique was proposed by Waller, which is widely used, is that we spread the interface just for calculating the derivatives. We spread the interface instead of a single line, it is spread over multiple lines, like over 3 lines here, the pink line, orange line, and the light orange line. So instead of writing FLXij as FL, so it's wrongly written here, it should be FLI plus 1 comma j minus FLI minus 1 comma j by 2 dx. We can spread it over and we can put some weightage of the neighboring cells. So this weightage is alpha. So we can put some weightage alpha of the neighboring cells, and we can calculate the weighted difference, calculate the derivative. Okay. Again, I will not go into too much details due to lack of time, but again, this is described in detail in all of the papers, in Waller paper or in the subsequent papers by many of the groups. Okay, how to use this technique? This is known as smearing technique. This is required for resolving the sharp interface, because otherwise curvature calculation is not possible. Okay. Similarly, for the other derivatives also it can be used. Typically, a weightage of alpha of 0.5 is taken, which is found to be suitable for this type of problems. The only other part that is left, so if you follow the discussion that has gone till now, if we develop a model based on that, we should be able to solve for solidification. The only problem will arise because in one point is that when a certain cell, so solidification is occurring means that liquid fraction in a cell goes to 0 and solid fraction goes to 1. Okay, so liquid fraction goes to 0 from a high value. So once the cell is fully solid, liquid fraction has become fully 0. The loop will not, the way the calculations are done, there is a loop for this iterative solution. And this loop runs only when the liquid fraction is between 0 and 1, not when it is fully 0 or fully 1, because it only needs to be run for the interface. So it will not enter, the calculations will not start for the next cells unless you explicitly make them interface cells. So once the liquid is, like once a cell has become fully solid, we look for all the neighboring cells where it is fully liquid, means FL is 1, and we seed it with a very small amount of solid, very small amount, just to make it an interface cell. And this does not change the, like because of the small amount and because the enthalpy anyway is conserved, it does not change the calculation or the interface speed, but it helps us in propagating the solidification front into the next cells. Okay, this is known as numerical seeding of the interface cells. This is needed because of the way the algorithm is developed. So this is an example of a typical algorithm. This is widely used now. This has been used by many groups. It is used by our group in IISc also. This is used. There are some groups in UK which use this algorithm. And for other type of studies like magnetohydrodynamic studies of dendrite growth and things like that, how magnetohydrodynamic flow influences dendrite growth. And these are used for semi-solid forming studies. But this is the basic framework on which, or CFD framework on which we can develop the code for a growth of single dendrite. Okay. So because I'm running out of time for this part, I will just quickly go through the numerical scheme. I have already discussed all this. So we have an explicit scheme for the, so it's not finite difference. We can use finite difference, but we are using finite volume. It's wrongly written as finite difference here. For enthalpy and solute concentration, and iterative process is required for calculating the value liquid fraction and then concentration potential and temperature at the interface. Momentum equations can be solved using any method. We are using simpler method. And once you discretize the equation using simpler method, you can solve the discretized equation using any type of solver. We use a line by line TDMA solver based on Patankar's original method. And for calculating the curvature, liquid fraction is treated as a level set function using this, and curvature is calculated using this equation. And for each of the derivatives, this type of calculation is needed. Okay. And the crystal anisotropy is explicitly imposed. What it means is that we are saying that the dendrite has to grow in 4 directions. If we change it to cos 6 theta, we are saying that dendrite has to grow in 6 directions. It is explicitly mentioned. Otherwise, the code will not understand that it has to grow in 4 directions, because atomic level things are not accounted for in the code, cannot be captured at this length scale. Okay. So we have already discussed the algorithm. I will not go into these details. It's there in the papers. The model also. So I think we have run out of time for this part, but I will continue for 10 more minutes so that we can start the next part in the next hour. Okay. We'll show you some results here. This is how a typical single dendrite growth looks like. So growth of a single dendrite using the model. The inner thicker line is from our model, CFD-based model. The outer line also is from a similar model, but using another method which is known as phase fill method. We see that this type of models are able to capture the dendrite shape very accurately. Even the theoretical calculations also agree well with the type of, like, there are theoretical theory for what will be the steady state velocity of the tip of the dendrite. These are known as the arms of the dendrite. There are 4 arms of the dendrite, and these are the tip of the dendrite. And the steady state velocity of the tip can be calculated using theory, and it depends on the undercooling. Undercooling is the difference of temperature from the interface to the faraway liquid. Okay. So based on the undercooling, we can calculate the steady state temperature, and our models also predict similar steady state temperature. The dotted lines is for our model, and the horizontal line is the steady state temperature, which is equal to 0.017 for dimension, like in dimensionless form, or undercooling of 0.55, again in dimensionless form. Again, if you want to see the concentration plots, this is not a very nice looking graph. It's a very old graph from our group, but it shows you how the concentration varies. Concentration is very high near the dendrite. Why this is very high near the dendrite? Because in the solid, if you remember, the concentration has to be low, because CS is CL into Kp, and Kp, this partition coefficient, you can see that it will be much less than 1. CL is much higher than CS. Typically, partition coefficients are of the order of 0.1, 0.15, like this. So CS is much less than CL. Okay. So when a solid forms from a liquid, most of the solute that was present cannot be accommodated in the solid. So it has to go in the liquid itself. Okay. So just near the solidification interface, the solute gets accumulated. It is similar to, say, if you have a water and salt solution. So you can dissolve a lot of salt in water, but when you freeze that water and salt solution, the ice that will form will have only a limited amount of salt. It cannot accommodate too much salt. So most of the salt will accumulate in the water, liquid water, and the concentration of salt in the liquid water will keep on increasing. Same thing happens here. The concentration of the solute keeps on increasing in the liquid just near the interface, and based on the diffusivity of the solute, it then transfers to the bulk liquid. So bulk liquid far away concentration is non-dimensional form, it is 1, and near the interface it is much higher than 1, maybe 3 or 4, like 4 times higher. So it diffuses away. Due to diffusion, it moves away from the interface. And this can be seen very easily if you plot the concentration along a central line. If you plot the concentration along this central line, you can see that this is the point of the solidification interface. So just at the interface, concentration is very high, and far away in the liquid, it goes to 1. Okay, and in the solid, it is much less than 1. Okay. Initial variation is when it was reaching steady state. The solute concentration rapidly increased. Initially, the liquid concentration was C0. So the solid concentration was much less. But now, because the liquid concentration has increased, solid concentration has also increased from the initial value, and ratio is still Kp. Okay, CS by CL is still Kp at the interface. So this point by this point will still be Kp. Similarly, if you draw along concentration along the diagonal, we can see that at the interface, the concentration is very high. So most of the solute gets trapped along these regions. Okay, not at much at the tip. The tip cuts away fast through the solute, but the solute gets accumulated in these regions. So as a result, the concentration becomes very high in this region. And remember, if the concentration is high, what happens to the temperature? We have discussed, if the concentration is high, the melting temperature will reduce or interface temperature will reduce. So far away temperature, say far away temperature is some temperature 500 degrees centigrade. Okay, and interface temperature initially was 650, but because of higher concentration, it has become 600. So the driving force has reduced. So instead of 150 degrees centigrade difference in temperature, now the driving force is 100 degrees centigrade difference in temperature. So if the concentration increases, the driving force for solidification decreases. So the solidification rate slows down. So wherever concentration is higher, solidification rate will be tend to be slower. Okay, so that is also an important output from this type of single dendrite study. Similarly, we can look at the temperature profile. This is not a temperature control. This just shows the dendrite shape. But if we plot the temperature along the say x direction, we see that far away liquid, the temperature is much lower. Okay, it has increased from 0.6 because a lot of latent heat has been rejected in the liquid. In the solid, which forms at the interface temperature, the interface temperature is quite higher. So it is around minus 0.1. Initial solid was at 0 temperature, but because of conduction of heat from the center towards the interface, some amount of decrease in temperature occurs, but still the solid is at higher temperature and liquid is at lower temperature. Okay. Same thing can be obtained if you see along the 45-degree line. Okay. Some other things which we can study from single dendrite. For example, if the undercooling is higher, undercooling is the difference between the temperature given initial temperature and the temperature of the melting temperature of the solid. So say melting temperature is 650 and initial temperature is 500. So this 150-degree difference is the undercooling. So in non-dimensional forms, it can be written as 0.6, 0.7, something like that. So higher undercooling means that more potential for more driving force for solidification to occur. So it strongly affects the dendrite growth, and dendrite will grow much faster depending on the undercooling. Similarly, another important parameter is the solute diffusivity in the liquid, okay, which is defined in terms of non-dimensional number, which is known as Lewis number. So Lewis number is ratio of thermal diffusivity by solid diffusivity. If Lewis number is higher, keeping thermal diffusivity constant, it means that solute diffusivity is lower. Okay, so LE equal to 20 means diffusivity of solute in the liquid is lower. Okay, so what will happen if the diffusivity is lower? It means that more solute will accumulate near the interface. It cannot diffuse easily. So concentration will increase near the interface, which will lead to lowering of the interface temperature, and hence the driving force for growth will decrease and the growth rate will decrease. So as a result, you can see that for lower diffusivity, which is shown by the red line, the growth rate is lower, and for higher diffusivity, the growth rate is higher. Okay. So this type of things can be obtained. Again, the effect of convection also can be obtained. So if you solve the momentum equations, you can see that the flow comes in, forced convection is there from one side of the domain to the other side, as shown by the vectors here. The growth is higher, much higher along the upstream direction. This is because the flow quickly removes the thermal energy and the solute from this upstream direction. So both contribute to faster growth rate. If you remove heat quickly, it will removal of latent heat is faster, so it will grow quickly. And if you remove solute quickly, the concentration at the interface will be less, and as a result, the temperature of the interface will be higher. So the difference of temperature of the interface with the faraway liquid will be higher, and more heat transfer can occur. So growth will be faster. So this type of things also can be predicted, all from single dendrite cases. And we can see that we can quantify it basically, that without convection, the solid line is the growth rate. With convection, the upstream side growth rate is higher. Downstream side growth rate is actually lower than without convection, because most of the heat and solute gets accumulated at the downstream side, and the perpendicular sides are not affected much. So they have similar type of growth rate. So we will pause here And in the final part, we will discuss about microstructure modeling. Okay. So most of the important part has already been discussed. So now we will see how to extend this model for microstructure, and a few examples we will see. So my main emphasis was to describe the equations, governing equations, and other things related to single dendrite growth, because somebody may be interested in developing similar types of models based on CFD. Okay, so, okay, that's Dr. Rath. So we'll take a break. Yeah.
Yes. Sure. Thank you very
much. That is the basic or the crux of the microstructure evolution model, or the basic building block of the microstructure evolution model. So if we can solve for a single dendrite, the hard part is done. Now it is we have to add some additional features so that we can derive something like this type of, say, grain structure, this type of grain structure, large scale grain structure. But each of these grain is basically a dendrite, single dendrite, like you see here. This single dendrite will grow on if we continue, and there is another dendrite will grow. Each of them will form a grain. Now we have to consider a large domain and multiple dendrites to form. Again, I will go back. There may be some lag with my voice because of poor internet connectivity. So you have to bear with that. So each of this you have to think of it means as a single dendrite. Each of the grain is formed from a single dendrite. So what are the additional things that needs to be considered for capturing this effect? Okay, let us try to see how to extend our single dendrite model or multiple dendrites. So the basic part is still same. So I've just written it here just as a repetition, but the equations are still same energy, species, interface energy, non-dimensional energy, everything is same. So the growth, the conservation equation for the growth and the means basically the energy conservation, species conservation equation, the interface temperature calculation, and the flow equations remain exactly same. Okay, what new thing is there? The new thing that is there is, in the previous case we were just considering a single grain at the center. So there were a couple of assumptions. One was that there was a single grain at the center, and another was that we were seeing that all the grains are growing in this direction, means it is aligned with the axis. All the grains are aligned with the axis, so along the x and y direction. But in real life, what will happen? Depending on how the initial nucleation occurs, the grains will have different orientation, they will be at different angles. Each grain will be at a different angle. Each dendrite will grow at a different angle. Okay. Now this initial angle depends on how the nuclei has formed, how the nuclei has formed from the atoms. Obviously, we cannot capture that at this length scale because that occurs at nanometer level, and it is beyond the resolution, and also the physics is different. It is our assumptions break down at that level. So this has to be incorporated generally using probabilistic measures. So what is done is that there are two things. One is what will be the grain orientation, means what will be the direction of growth of the grains. Second is how many grains will be there and where they will be located. Okay. So we can fix the number of grains. Artificial, I can say that 50 grains will be there, and I can randomly generate the x and y coordinates for the initial position of this 50 nucleus, like we were doing here. I go back again. We are specifying that there is a single solid. Instead of that, I can randomly assign 50 nucleus at 50 different points. I can, using random number generator, I can calculate the x and y coordinates randomly for each crystal, and I can just assign the the properties of the solid. But that is just we are artificially. That is one way of doing it, and many people do like that, like studying 5 dendrites or 10 dendrites, how they interact. But in real life, what happens? The number of nuclei that will form will vary, and that depends on the cooling rate. If the cooling rate is higher, then generally nuclei formed will be higher, and the cooling rate is lower, the number of nuclei that is formed is lower. So from experimental evidence, it has been seen that, I will come back to this, that the number of nuclei that is formed, this is wrong. This will be D and D. This is the rate of nucleation, not nucleation. D and D delta T. It's wrongly written as N. So the rate of nucleation initially it is very low, means with low undercooling. Remember what is undercooling? Undercooling is the temperature below the melting temperature. If the melting temperature is 650 degree and the actual temperature of the liquid is 640 degree, undercooling is 10 degree. If you increase the undercooling, it means that the liquid temperature is decreasing. So if we keep on decreasing the liquid temperature, undercooling keeps on increasing. So at higher undercooling, there is more driving force for nucleus to form. Okay, so the nucleation rate increases with higher undercooling until a point where the very large amount of nuclei forms, and as a result, a large amount of latent heat is generated when they start growing, and again the nucleation rate drops down at when you keep on cooling further. So basically, it can be fitted with a curve which is similar to a Gaussian or normal distribution. Okay. So this is based on experimental data and was initially used by Rappaz and Ganding long back for their model, which was not a CFD based model, but a simple probabilistic model of grain growth. But the nucleation part is actually captured very nicely in this. So what happens is that if you keep on increasing the undercooling for various undercooling, the nucleation rate will change, and it will depend on what is the mean nucleation temperature, undercooling temperature delta Tn, and the standard deviation. So three parameters are required to fix this plot. One is delta Tn, which is the mean. One is the sigma standard deviation, and third is the peak value, maximum value, Nmax. Okay, Nmax is the total value, means the total number of grains that can form. So based on this, we can actually calculate at different delta T what will be the number of grains that are formed. And this is please remember that this is dn d delta T, not n. Okay, this is the rate of nucleation. This term dn d delta T, okay, not n. It's wrongly written as n here. So now how to incorporate this in the CFD model? So say we impose, what we do is we change the energy equation with an additional source term. Okay, see how to impose a cooling rate in real life. What happens? You say that we are cooling this mold at with a certain cooling rate, so 10 degrees centigrade per second. Okay, but because we are solving directly for the temperature in our code, we cannot again say that the temperature will decrease by 10 degree per second. Okay, we cannot impose the directly the cooling rate, because that will interfere with the actual temperature calculation, because localized temperature we are already calculating based on the CFD model. So this cooling rate can be imposed as a negative source term in the energy equation, as if some energy is being taken out at a constant rate, and the source term can be defined based on any prescribed cooling rate. So if we say that 10 degree per second cooling has to be there, so accordingly the source term can be defined. It will be a negative source term, such that if we solve the equation, we will find that the temperature, if there is no solidification, if it is only liquid, still the temperature will decrease by 10 degree per second. Okay, so the cooling rate is imposed through an additional source term in the energy equation. Now, if you start with a liquid at a certain temperature, and if the cooling rate keeps on decreasing, if the temperature keeps on decreasing because of the cooling rate, at any time we can calculate what is delta T. After each time step, we can calculate what is delta T and how many nuclei should be there at that time step. So we know what is the number of nuclei in the previous time step and what will be the number of nuclei at the present time step. So this extra number of nuclei can be incorporated it can be added in the domain at random locations. Okay, so again in the next time step we can find out how many new nuclei should form, and again they can be added at random locations. Like this we can proceed, and this will actually capture nicely the effect of cooling rate on the number of nuclei that is formed. And these values delta T and delta T sigma and this will be delta T sigma and Nmax, these are material dependent properties. For different materials, they can be calibrated from experimental results. This will depend on different materials. And this can be also modified for the same materials by using some grain refiners. So for example, if we want to create more nucleus, we can put some grain refiners. Grain refiners are artificially added some impurities. Okay, so they will act as nucleation sites so that more nucleus will form. So that will actually shift the curve towards the left side. So at low undercooling, more nuclei will form if you add grain refiners. So a lot of things can be done, and all this can be modeled also by using this type of equation. So this is one part. This will take care of. We cannot capture at what direction the atoms are coming together. So what is done is that each nuclei is given a random orientation based on a random number. Okay. As a result, the basic equation that was there, I had discussed briefly. It might be confusing somewhat to you, but we had imposed the anisotropy as 15 epsilon cos 4 theta previously. So instead of that, we have to write this as now as cos 4 theta minus alpha, where alpha is the angle of the dendrite. This alpha is randomly generated angle of the dendrite. So it means that now this arms will grow at an angle alpha as compared to the horizontal or vertical axis. Okay, so this angle is the crystallographic, is known as the crystallographic orientation. So instead of cos 4 theta, we can write this as cos 4 theta minus alpha, and alpha will be defined for each dendrite. So each will grow with a certain orientation, and that can be generated using random numbers. There are other features which can be incorporated, like secondary and tertiary branches, which can be done through some random noises in the thermal model. Random noise means that some fluctuation, perturbation is introduced. So what happens is that if you see the dendrite is going very smoothly. If I introduce a small perturbation here randomly, the perturbations will try to grow, and ultimately some of the perturbations will lead to formation of secondary branches. Now the number of branches will not depend on the number of perturbations given. It will depend on the actual thermal and solutal say temperature and solute concentration, temperature and the solute concentration near the interface. So it will depend on the thermal and solutal field ahead of the interface, but it can be induced by putting some perturbation or noise using random number generator at the interface. Okay, this is how it can be modeled, secondary and branches. And the model can also be extended to 3D. It's slightly complicated to do it in 3D. Obviously, computational expenses also increase, and the equations become much more complex. For example, the curvature equation can be calculated like that. Now you have to calculate derivatives and double derivatives, mixed derivatives along all the 3 directions. And the anisotropy also has to be calculated using somewhat more complicated relation based on the normal directions of the interface. We'll not go into details, but it can be done, the 3D, and it has it can be extended. Many groups have done it recently. Okay, so with this not minor, but with these changes, the model will approach a microstructure evolution model. Okay, so some more things can also be added. This itself will lead to a microstructure evolution model, the grain nucleation part. Now, if you want primary or secondary branches, we can use this random noise thing, but without that also it will be microstructure evolution model. If you want a 3D model, you can add this. All these are individual separate things, like separate functionalities, which can be added to the CFD code as different modules. Now, if we want to study shrinkage also, that also can be added. And to do that is actually somewhat tricky, because the basic code that is developed is based on the assumption that density is constant. Okay, so if density is not constant, density of the solid and liquid changes at the interface, this del rho del T term needs to be calculated and added as a source term during the calculation. So the way we solve the simpler algorithm, the continuity equation leads to the pressure correction equation. So this source term will go into the pressure correction equation. So an additional source term will come into the pressure correction equation, and this source term will be given in terms of, so I will not go into too much details here, these are available in the paper, but this source term will be in terms of the solid density rho s, liquid density rho l, and in terms of volume fractions. So now in this case, we will need two different volume fractions, two different fractions. One is the volume fraction, one is the mass fraction. because volume fraction of liquid will be different from mass fraction of liquid because of difference in density. Okay, so for example, say if the liquid is lighter than the solid, so for the same mass fraction, the volume fraction of the, for a certain mass fraction, the liquid will have a larger volume because it is lighter, so its volume fraction will be larger as compared to mass fraction. So now two fractions are actually denoted. One is the volume fraction GL and one is the mass fraction FL, and they can be related to the densities. So based on these parameters, an additional source term can be implemented. This comes from the del rho del T term, and it can be implemented in the pressure correction equation and pressure and pressure correction equation, and this will lead to shrinkage driven flow. So what will happen? This will influence the pressure field, and negative pressure will be created near the interface, which will attract the flow from farther away. So a flow will come from far away liquid towards the interface to compensate for the shrinkage that is occurring, like shown here. Okay, this is also quite interesting and can be captured. So this is about the modeling part. Let me show you some cases, some results, starting from basic results to more capabilities. What can be done using CFD models like this, and what can be done in future also, like what are the ongoing work. Other groups have also done some good results. You can study like from Chaos group or Pericles, who have done on magnetohydrodynamic flows, the effect of magnetohydrodynamic flows on dendrite growth. They have extensively studied. Voller has studied effect of magnetohydrodynamic flows. Then using similar types of models, enthalpy-based models. We are also in process of developing grain structure models for laser melting processes and other types of processes. So just to show you, starting from some basic cases, if we do not use the nucleation model, preliminary model for multiple dendrites will look like this. So you specify the location of the 5 dendrites, and they will just grow based on the specified locations. Still, some interesting results can be obtained, as you can see here, that once the dendrites come in close proximity of each other, the neighboring dendrites hinders the growth of the central dendrite. What happens is the solute concentration becomes very high in this region. And remember, what if the solute concentration becomes high, what happens? The growth rate is reduced. We have seen it previously for the single dendrite case. So here the red color shows that concentration is very high, and far away it is quite low. So in this region, concentration is high and the growth rate is lower. That's why these branches are growing very slowly, and these parts are growing fast. And also the flow is affecting also. So the upstream parts are growing even faster. So the dendrite morphology will depend on neighboring dendrites and the flow pattern. Okay, this is very important. And the final concentration field also. Similarly, if we have less number of dendrites and large number of dendrites artificially imposed, then we see that for less number of dendrites, we get more dendritic kind of structure. For large number of dendrites, it will lead to more globular kind of structure. Globular means circular kind of structure. Okay, so this is seen in real life also. If you do casting without grain refiners, less number of nucleation occurs, and it is more dendritic structure. If you use grain refiner, more nucleation occurs and it leads to globular structure. Qualitatively, it is similar, and this actually means if you have more globular structure, this improves the ductility of the material. So in some cases, so this type of structures can also be formed using semi-solid forming, so which can also be predicted using this type of model. Similarly, if you want to solve in 3D, that can also be done, but it depends on computational resources. We cannot go to very large number of very large grid size. And if you have a small grid size or number of grid points are small, the curvature cannot be very accurately captured. That is one difficulty. So in future, maybe this type of models, if somebody is working on this type of models, it can be done by using parallel programming. But still, we can capture very nicely the 6-way growth of the dendrite, as you can see here. Nicely, the 6-way growth of the dendrite is captured, and multiple dendrite growth is also captured. Similarly, flow pattern due to shrinkage. So for example, if there is a single dendrite, how the flow comes in from different direction. If we assume that the sides are open, how the flow comes in, and as a result, how the dendrite growth pattern change, that also can be captured. And what happens if shrinkage is there? Shrinkage driven flow will be generated. Shrinkage means solid has higher density as compared to liquid. So when some liquid solidifies, the volume is reduced and some flow comes in from the outside, as can be seen from the simulation result. As a result of this flow, the concentration, so there are two opposing mechanisms for the solute transport. One is the diffusion away from the interface and one is the flow towards the interface due to shrinkage driven flow. So as a result, more accumulation of solute happens near the interface, and this reduces the growth rate even further. And this can be nicely captured that without, so with shrinkage driven flow, the growth rate is the smallest, means growth rate is lowest. Okay. Even for one other important thing is that if you have large scale nucleation and growth, the shrinkage flow from the neighboring cells, from overall shrinkage flow pattern will strongly influence local grain growth pattern. For some grains will be influenced by the flow that is occurring because of shrinkage of other grains. So that also needs to be taken into account for accurate modeling. Okay. So then, as I was saying, to get very accurate or more realistic grain structure, as go back here. Initially, if you have seen the dendritic structures, this type of branches are formed, right? This type of branches are formed. These are columnar dendrites and these are equiax dendrites. These are known as secondary branches. And secondary branches, distance between the secondary branches is a very important parameter in materials. It is known as secondary arm spacing. And why it is important? Because this affects the heat treatment process strongly. The heat treatment actually occurs due to diffusion, and if the secondary arm spacing or the distance between the secondary arms is less, the diffusion can occur much easily. So depending on the secondary arm spacing, the heat treatment process and the final strength of a material can be determined. So if we can predict what will be the secondary arm spacing based on the cooling rate and other conditions, it is actually very advantageous in predicting the final properties. So this type of things also can be captured if you use random. These are still difficult, but it can be captured. So for example, for the single dendrite, we are able to capture secondary arms and tertiary arms, and it almost looks like a real dendrite. Like real dendrites will be of this nature. And we can also see the effect of flow on suppressing the secondary dendrites in this region. The vortex type flow actually suppresses the brings back some solute, and as a result, it suppresses the flow in the secondary region. So CFD-based models have a lot of capability. That is my main point of this. Now, if we want to see the effect of cooling rate, we can impose different cooling rates. These are all non-dimensional forms. This is a very low cooling rate. This is 100 times higher cooling rate, and you can see the this is the grain structure. For the low cooling rate, we have large grains. For the high cooling rate, we have large number of small grains. This is very realistic. In real life scenario also same thing happens. For small cooling rate, we get large grains. For larger cooling rates, larger and larger cooling rates, the grains will become smaller and smaller. The other important factor that happens is that the concentration for small at lower cooling rate, you have large segregation. Segregation means that the grains will be at low concentration, and most of the solute, if it is say aluminum or copper, most of the copper will get accumulated in between the dendrites. So in the interdendritic region or at the grain boundaries. Okay. When the cooling rate becomes very large, because the growth is so fast, the solute cannot diffuse away fast enough. Most of it gets trapped within the solid. So we get although there is segregation is a variation. Although there is variation of concentration, we get a much more uniform pattern. So these things also can be predicted by this type of models, and this actually determines the property of the ultimate property of the product and also the effect of heat treatment and other things. So depending on like initial or boundary condition, we will be able to predict this type of thing. And you can see how the grains are going. This actually leads to this type of grain structure finally. And here you can see also small dendrites are growing. So this domain is quite large, and these results you can see that are very similar to this real life grains that can be obtained using SEM EBSD images. For example, this type of images. Okay, it's not quantitatively same, it can predict the similar type of behavior qualitatively, and almost it gives similar type of image. This is an experimental image, and the microstructure model. Remember that we have discussed so much on the single dendrite part, but on the extension of the single dendrite to the microstructure model is not so difficult. Once the single dendrite part is done, single dendrite part is the difficult part. Once it is there, then we can get a lot of benefits just by modeling, adding some more details to account for the nucleation and orientation and things like that. But we can get much more realistic results. Okay, so the initial step is hard, but finally it can lead to very nice results. Similarly, if you remember the columnar dendrites I was showing from experimental results, X-ray results, that type of things also can be captured here. What is the time? We are on time. And not only the columnar growth can be captured, but the effect of diffusion field on the columnar growth can also be captured. What do I mean by that? For example, if I start with 20 nuclei at the bottom, in another case, if I start with 100 nuclei at the bottom, so it does not mean that in one case there will be 20 columnar branches, in another case 100 columnar branches. The spacing between this is governed by the solutal field ahead of the interface. Okay, so you cannot, and cooling rate, so, or undercooling. Okay, so so the model accurately captures whether it is 20 nuclei or 100 nuclei or 50 nuclei. It's shown in the study. If you go to the study, you can see in more detail. Whatever is the number of nuclei, ultimately the number of branches that are there are of the same order. So the arm spacing, the different distance between these two adjacent columnar dendrites is known as primary arm spacing. So the primary arm spacing can also be predicted. Secondary arm spacing also can be predicted based on the cooling rate. Okay, but it is more tricky. The other thing is that if the cooling rate, undercooling is changed, we have a low undercooling and high undercooling, but the number of nuclei is kept same. So it can be seen that for low undercooling, the number of surviving columnar grains is much lower as compared to the high undercooling case. This is also, although this is quantitatively not exact, but qualitatively this is similar to experimental results. Okay. Some other features which can be captured at a preliminary level is formation of columnar plus equiax grains, which is known as columnar to equiax transition. These things also can be captured by this type of CFD model. So the grains which comes from the sides are known are columnar grains, and the other part is filled up with the equiax part. This can be fine-tuned using nucleation parameter. Remember how this for different alloys can be captured, effect of different alloys, by changing the nucleation parameters, delta T and delta T sigma and N max. All these parameters will change for different types of materials, then addition of grain refiners, things like that. So they will control the nucleation rate and the columnar to equiax transition also. Then solutal buoyancy effect, as I was saying. So wherever there is, so for example, this case, the solute is lighter. So wherever there is solute is lighter, or it looks like not clear from this. So because we have modeled both of them, it's not clear from here, but it creates a flow pattern. Okay, and this type of flow pattern sometimes leads to defect formation. This is known as freckle formation. What happens is that there will be sometimes some channels will be formed because of convection pattern, which will solidify at the last, and that there will be some shrinkage type effects that will remain. So which is actually harmful. So this also can be somewhat predicted using this type of CFD models. So finally, I will end it with a very preliminary type of result for laser-based melting. So for example, if you have a powder sample, and same thing. So ultimately the equations are same. The model is same. Only added thing is through the boundary condition. Okay, or a volumetric source term at one point, or a boundary condition, which accounts for the laser heat transfer, or the heat transfer due to laser, or the heat addition due to laser. So as a result, we can see that. And the second part that is difficult to also add to the model is all the models that we have discussed till now had solidification, But to capture simultaneous melting and solidification is tricky. Means the equations have to be slightly modified, because during melting the partitioning effect is not there. So the equations are slightly different during melting. It is not similar to the solidification equation. Okay. So here you can see how the melting is proceeding, and then the subsequent solidification is occurring. Melting proceeds with a smooth circular flow pattern. We are ignoring the flow here, so it is just like a semicircle, hemispherical pattern, and the final grain structure you can see here, and this is the concentration pattern. And if we consider flow, so because of flow, the melt pool shape changes. So if you see, this was semicircular, but now it is more flat shape, and this is because of surface tension effect. These are very well known, like macroscopic level, people have studied extensively. Marangoni, this is known as Marangoni convection. Then there can be thermal or solitary convection. So surface tension driven convection is very strong. This occurs because of temperature gradient at the top, which leads to variation of surface tension at the top, and that variation of surface tension leads to flow from the middle towards the side. And as a result, the more melting occurs near the top, and the melt pool gets flattened out. So this type of things also can be captured, and as a result, the final microstructure will be different. So that can be also captured using this type of models. Again, these are preliminary microstructure. These are like from some like couple of years back, but we have now proceeded with much more improved models at present. And if you want to capture moving melt pool, you can add a moving heat source term, and as a result, we should be able to capture the final dendrite, like what is the grain structure. And now using this type of model, we can study what will be the effect of power, what will be the effect of laser speed, okay, or what will be the effect of laser power or laser spot size on the final microstructure, and that can also lead to quite important predictions. Okay, but some drawbacks are still there. These models are still not very suitable for exact complex alloys. These are more like mathematical models or hypothetical models. Unlike say macroscopic models, which can capture say aluminum, copper alloy, aluminum, silicon alloy, all this type of behavior. They are more like hypothetical materials. Alloy properties can be captured, but there are some drawbacks which needs to be avoided. So this brings us to the end of this. So I will just summarize what we have discussed today. We have basically discussed how to develop a CFD-based model for grain structure prediction, and the crux of the model was the single dendrite prediction model, the growth of a single dendrite based on solution of energy equation, species conservation equation, interface temperature, and curvature of the interface, constitutional undercooling and curvature undercooling. And from that single dendrite prediction, then we could predict a few things like what will be the concentration variation in the domain, what is the effect of flow, and then by adding nucleation model, we can extend it to microstructure model. We can add branchings, primary, secondary branching, to make it more realistic, and it can be extended to 3D. More simulations could have been possible, but it takes a long time for the 3D simulations to run. And if there is more computational resources, those can be also done. These large-scale simulations are done in 2D. So this if to do this in 3D will take huge amount of computational resources, because the domain is very large. And some of the things that are still difficult to address using this type of models is extension to multi-component system. Multi-component means more than two components, like ternary alloy, aluminum, copper, silicon, aluminum, copper, zinc, like this. Okay. Then some other things which are not exactly CFD related, but it can be a CFD coupled CFD finite element type of model, which can calculate the stress that are generated and deformation and breakage, which are also important. So coupled CFD FEM type of models can be developed in future. Some other things like intermetallics or eutectic solidification, where the physics is different, and similarly effect of say porosity formation and shrinkage defects. These things also can be accommodated. So that is all. So if there are any questions, feel free to ask me.
Yeah, thank you very much, Dr. Anirban, for taking such a long session and elaborating all details of the this complex material processing technique, especially this complex multi-physics phenomena involved in material processing, especially this microstructure evolution. We can understand how difficult is modeling such a complex process. And you have very nicely presented with all details of the mathematical model, numerical approach, followed by some sample results also. So thank you very much. And I'd like to request our participants, if they have any query, they can discuss.
Dr. Rath, thank you very much for inviting me for this lecture, and I have shared my slides also with you. I think you can also share with the participants.
Sure.
Some references are also there. They can read those papers for more details.
Right. Sure.
Yes, please, if any questions are there, you can ask.
Yes. Participants, if you have any question, please. Hello. Hello, anybody? Yeah, Professor Dilip Kumar, if you want to ask something. Professor Dilip Kumar, are you there? Oh, yes, message something. Let me see.
Yes, I have got a question.
Yes. Yeah, Professor Kaur. Yes, please.
Yes, sir. Sir, you have done the shrinkage into the, you have included the shrinkage source term to allow for this shrinkage. So, can you please tell me where we have to add this shrinkage source term? Is it in the continuity equation or what?
It is part of the continuity equation, but we don't have directly the continuity equation, right? Means at least the way we are solving, I am solving. The continuity equation was solved in this form, del dot u. So ultimately, the del rho del t term, which is there, if we discretize this continuity equation to form the pressure and pressure correction equations in simpler algorithm, that del rho del t terms goes there, and there actually we use the source term in the pressure correction equation and pressure equation, like in terms of density, and it can be checked also that we have to check that whether the flow amount which is coming is equal to the volume of shrinkage or not, because the shrinkage is automatically captured based on the pressure that is generated by the model. We are not saying that this much flow should come. So it has to be verified whether finally the flow which is coming is equal to the shrinkage that is occurring, and that we have verified and is actually
as there is density term in the pressure correction, that's why you are adding, I think, in the pressure correction equation.
Yes, means ultimately, if you remember, if you see, the pressure correction equation is just a derivative of the continuity equation. It was derived from the continuity equation. So that's why this term is.
Yes. Another thing, sir, you have done, I mean, in the shrinkage term, it is rho old. Rho old means it is of previous time step or what?
It is previous time step. This del rho del t term.
Yes, but the shrinkage term depends on the liquid density and solid density.
Correct,
so this source term is not including any type of that solid density and liquid density.
No, it is there. I have not mentioned here. This rho is actually rho p for the pth control volume. The rho is GL rho L plus 1 minus GL rho S. So GL is the volume fraction of liquid, and GL is the volume fraction of liquid. Rho L is the density of liquid. Rho S is the density of solid. So this rho is actually the average rho of the control volume of the pth control. If you remember if you have done using that follow the convention by Patankar, we use pth control volume for the central control volume, and east, west, north, south.
This is basically the mixture density, I guess.
This is the mixture density. Yes.
Okay.
This has the liquid and solid density.
Yes, the right hand side, whatever term is there, that is the final term, I think. That includes the density of solid and density of liquid.
Correct.
Right.
Okay, sir. Hope I am in Bhubaneswar, so I can meet you and discuss the things. And because I have done already the certification, but I have not entered into the species conservation equation. So I want to start to solve this species conservation equation and include in my code.
Yes.
So I can discuss if you can allow me to. Yeah.
Yes, you are most
I will
welcome.
be happy to do that. Yes.
Okay, sir. Thank you. Thank you very much.
Anybody having any other question? So if there are no more questions, then we can end the session here. Thank you very much, Dr. Anirban, for spending such a long time with us out of your